Cantor Audio, a division of Recorded Books, presents Zero, the Biography of a Dangerous Idea, by Charles Seife, narrated by Bob Sauer. Chapter 0, Null and Void. Zero hit the USS Yorktown like a torpedo. On September 21, 1997, while cruising off the coast of Virginia, the billion-dollar missile cruiser shuddered to a halt. Yorktown was dead in the water. Warships are designed to withstand the strike of a torpedo or the blast of a mine. Though it was armored against weapons, nobody had thought to defend the Yorktown from Zero. It was a grave mistake. The Yorktown's computers had just received new software that was controlling the engines. Unfortunately, nobody had spotted the time bomb lurking in the code, a zero that engineers were supposed to remove while installing the software. But for one reason or another, the zero was overlooked, and it stayed hidden in the code. Hidden, that is, until the software called it into memory and choked. When the Yorktown's computer system tried to divide by zero, 80,000 horsepower instantly became worthless. It took nearly 3 hours to attach emergency controls to the engines, and the Yorktown then limped into port. Engineers spent 2 days getting rid of the Zero, repairing the engines, and putting the Yorktown back into fighting trim. No other number can do such damage. Computer failures like the one that struck the Yorktown are just a faint shadow of the power of Zero. Cultures girded themselves against Zero, and philosophies crumbled under its influence, for Zero is different from the other numbers. It provides a glimpse of the ineffable and the infinite. This is why it has been feared and hated and outlawed. This is the story of Zero, from its birth in ancient times to its growth and nourishment in the East, its struggle for acceptance in Europe, its ascendance in the West, and its ever-present threat to modern physics. It is the story of the people who battled over the meaning of the mysterious number, the scholars and mystics, the scientists and clergymen who each tried to understand Zero. It is the story of the Western world's attempts to shield itself unsuccessfully, and sometimes violently, from an Eastern idea. And it is a history of the paradoxes posed by an innocent-looking number, rattling even this century's brightest minds and threatening to unravel the whole framework of scientific thought. Zero is powerful because it is infinity's twin. They are equal and opposite, yin and yang. They are equally paradoxical and troubling. The biggest questions in science and religion are about nothingness and eternity, the void and the infinite, zero and infinity. The clashes over Zero were the battles that shook the foundations of philosophy, of science, of mathematics, and of religion. Underneath every revolution lay a zero and an infinity. Zero was at the heart of the battle between East and West. Zero was at the center of the struggle between religion and science. Zero became the language of nature and the most important tool in mathematics. And the most profound problems in physics, the dark core of a black hole and the brilliant flash of the Big Bang, are struggles to defeat Zero. Yet through all its history, despite the rejection and the exile, Zero has always defeated those who opposed it. Humanity could never force Zero to fit its philosophies. Instead, Zero shaped humanity's view of the universe and of God. Chapter 1, Nothing Doing, The Origin of Zero. There was neither non-existence nor existence then. There was neither the realm of space nor the sky which is beyond. What stirred? Where? The Rig Veda. The story of Zero is an ancient one. Its roots stretch back to the dawn of mathematics, in the time thousands of years before the first civilization, long before humans could read and write. But as natural as Zero seems to us today, for ancient peoples, Zero was a foreign and frightening idea. An Eastern concept born in the Fertile Crescent a few centuries before the birth of Christ, zero not only evoked images of a primal void, it also had dangerous mathematical properties. Within zero there is the power to shatter the framework of logic. The beginnings of mathematical thought were found in the desire to count sheep and in the need to keep track of property and of the passage of time. None of these tasks requires zero. Civilizations functioned perfectly well for millennia before its discovery. Indeed, zero was so abhorrent to some cultures that they chose to live without it. Life without zero. The point about zero is that we do not need to use it in the operations of daily life. No one goes out to buy zero fish. It is, in a way, the most civilized of all the cardinals, and its use is only forced on us by the needs of cultivated modes of thought. Alfred North Whitehead. It's difficult for a modern person to imagine a life without zero, just as it's hard to imagine life without the number 7 or the number 31. However, there was a time where there was no zero, just as there was no 7 and 31. It was before the beginning of history, so paleontologists have had to piece together the tale of the birth of mathematics from bits of stone and bone. From these fragments, researchers discovered that Stone Age mathematicians were a bit more rugged than modern ones. Instead of blackboards, they used wolves. A key clue to the nature of Stone Age mathematics was unearthed in the late 1930s when archaeologist Karl Absalom, sifting through Czechoslovakian dirt, uncovered a 30,000-year-old wolf bone with a series of notches carved into it. Nobody knows whether Gog, the caveman, had used the bone to count the deer he killed, the paintings he drew, or the days he had gone without a bath, but it is pretty clear that early humans were counting something. A wolf bone was the Stone Age equivalent of a supercomputer. Gog's ancestors couldn't even count up to 2, and they certainly did not need 0. In the very beginning of mathematics, it seems that people could only distinguish between 1 and many. A caveman owned 1 spearhead or many spearheads. He had eaten 1 crushed lizard or many crushed lizards. There was no way to express any quantities other than 1 and many. Over time, primitive languages evolved to distinguish between 1, 2, and many, and eventually 1, 2, 3, many, but didn't have terms for higher numbers. Some languages still have this shortcoming. The Siriona Indians of Bolivia and the Brazilian Yanomami people don't have words for anything larger than 3. Instead, these two tribes use the words for many or much. Thanks to the very nature of numbers, they can be added together to create new ones. The number system didn't stop at 3. After a while, clever tribesmen began to string number words in a row to yield more numbers. The languages currently used by the Bakairi and the Bororo peoples of Brazil show this process in action. They have number systems that go 1, 2, 2 and 1, 2 and 2, 2 and 2 and 1, and so forth. These people count by 2s. Mathematicians call this a binary system. Few people count by 2s like the Bakairi and the Bororo. The old wolf bone seems to be more typical of ancient counting systems. Gog's wolf bone had 55 little notches in it, arranged into groups of 5. There was a second notch after the first 25 marks. It looks suspiciously as if Gog was counting by 5s and then tallied groups in bunches of 5. This makes a lot of sense. It is a lot faster to tally the number of marks in groups than it is to count them one by one. Modern mathematicians would say that Gog, the wolf carver, used a 5-based or quinary counting system. But why 5? Deep down, it's an arbitrary decision. If Gog put his tallies in groups of 4 and counted in groups of 4 and 16, his number system would have worked just as well as would groups of 6 and 36. The groupings don't affect the number of marks on the bone, they only affect the way that Gog tallies them up in the end, and he will always get the same answer no matter how he counts them. However, Gog preferred to count in groups of 5 rather than 4, and people all over the world shared Gog's preference. It was an accident of nature that gave humans 5 fingers on each hand, and because of this accident, 5 seemed to be a favorite base system across many cultures. The early Greeks, for instance, used the word fiving to describe the process of tallying. Even in the South American binary counting schemes, linguists see the beginnings of a quinary system. A different phrase in Bororo for 2 and 2 and 1 is, "This is my hand altogether." Apparently, ancient peoples liked to count with their body parts, and 5, a hand, 10, both hands, and 20, both hands and both feet, were the favorites. In English, 11 and 12 seem to be derived from 1 over 10 and 2 over 10, while 13, 14, 15, and so on are contractions of 3 and 10, 4 and 10, and 5 and 10. From this, linguists conclude that 10 was the basic unit in the Germanic proto-languages that English came from, and thus those people used a base 10 number system. On the other hand, in French, 80 is 80, 4 20s, and 90 is 90, 4 20s and 10. This may mean that the people who lived in what is now France used a base 20 or vigesimal number system. Numbers like 7 and 31 belong to all of these systems, quinary, decimal, and vigesimal alike. However, none of these systems had a name for 0. The concept simply did not exist. You never need to keep track of 0 sheep or tally your 0 children. Instead of "we have 0 bananas," the grocer says, "we have no bananas." You don't have to have a number to express the lack of something, and it didn't occur to anybody to assign a symbol to the absence of objects. This is why people got along without 0 for so long. It simply wasn't needed. 0 just never came up. In fact, knowing about numbers at all was quite an ability in prehistoric times. Simply being able to count was considered a talent as mystical and arcane as casting spells and calling the gods by name. In the Egyptian Book of the Dead, when a dead soul is challenged by Aken, the ferryman who conveys departed souls across a river in the netherworld, Aken refuses to allow anyone aboard who does not know the number of his fingers. The soul must then recite a counting rhyme to tally his fingers, satisfying the ferryman. The Greek ferryman, on the other hand, wanted money, which was stowed under the dead person's tongue. Though counting abilities were rare in the ancient world, numbers and the fundamentals of counting always developed before writing and reading. When early civilizations started pressing reeds to clay tablets, carving figures in stone, and daubing ink on parchment and on papyrus, number systems had already been well established. Transcribing the oral number system into written form was a simple task. People just needed to figure out a coding method whereby scribes could set the numbers down in a more permanent form. Some societies even found a way to do this before they discovered writing. The illiterate Incas, for one, used the quipu, a string of colored knotted cords, to record calculations. The first scribes wrote down numbers in a way that matched their base system and predictably did it the most concise way they could think of. Society had progressed since the time of Gog. Instead of making little groups of marks over and over, the scribes created symbols for each type of grouping. In a quinary system, a scribe might make a certain mark for 1, a different symbol for a group of 5, yet another mark for a group of 25, and so forth. The Egyptians did just that. More than 5,000 years ago, before the time of the pyramids, the ancient Egyptians designed a system for transcribing their decimal system, where pictures stood for numbers. A single vertical mark represented a unit, while a heel bone represented 10, a swirly snare stood for 100, and so on. To write down a number with this scheme, all an Egyptian scribe had to do was record groups of these symbols. Instead of having to write down 123 tick marks to denote the number 123, the scribe wrote 6 symbols, 1 snare, 2 heels, and 3 vertical marks. It was the typical way of doing mathematics in antiquity, and like most other civilizations, Egypt did not have or need a zero. Yet the ancient Egyptians were quite sophisticated mathematicians. They were master astronomers and timekeepers, which meant that they had to use advanced math thanks to the wandering nature of the calendar. Creating a stable calendar was a problem for most ancient peoples because they generally started out with a lunar calendar. The length of a month was the time between successive full moons. It was a natural choice. The waxing and waning of the moon in the heavens was hard to overlook, and it offered a convenient way of marking periodic cycles of time. But the lunar month is between 29 and 30 days long. No matter how you arrange it, 12 lunar months only add up to about 354 days, roughly 11 short of the solar year's length. 13 lunar months yield roughly 19 days too many. Since it is the solar year, not the lunar year, that determines the time for harvest and planting, the seasons seem to drift when you reckon by an uncorrected lunar year. Correcting the lunar calendar is a complicated undertaking. A number of modern-day nations, like Israel and Saudi Arabia, still use a modified lunar calendar, but 6,000 years ago the Egyptians came up with a better system. Their method was a much simpler way of keeping track of the passage of the days, producing a calendar that stayed in sync with the seasons for many years. Instead of using the moon to keep track of the passage of time, the Egyptians used the sun, just as most nations do today. The Egyptian calendar had 12 months, like the lunar one, but each month was 30 days long. Being base 10 sort of people, their week, the decade, was 10 days long. At the end of the year, there was an extra 5 days, bringing the total up to 365. This calendar was the ancestor of our own calendar. The Egyptian system was adopted by Greece and then by Rome, where it was modified by adding leap years, and then became the standard calendar of the Western world. However, since the Egyptians, the Greeks, and the Romans did not have zero, the Western calendar does not have any zeros, an oversight that would cause problems millennia later. The Egyptians' innovation of the solar calendar was a breakthrough, but they made an even more important mark on history: the invention of the art of geometry. Even without a zero, the Egyptians had quickly become masters of mathematics. They had to, thanks to an angry river. Every year the Nile would overflow its banks and flood the delta. The good news was that the flooding deposited rich alluvial silt all over the fields, making the Nile Delta the richest farmland in the ancient world. The bad news was that the river destroyed many of the boundary markers, erasing all of the landmarks that told farmers which land was theirs to cultivate. The Egyptians took property rights very seriously. In the Egyptian Book of the Dead, a newly deceased person must swear to the gods that he hasn't cheated his neighbor by stealing his land. It was a sin punishable by having his heart fed to a horrible beast called the devourer. In Egypt, filching your neighbor's land was considered as grave an offense as breaking an oath, murdering somebody, or masturbating in a temple. The ancient pharaohs assigned surveyors to assess the damage and reset the boundary markers, and thus geometry was born. These surveyors, or rope stretchers, named for their measuring devices and knotted ropes designed to mark right angles, eventually learned to determine the areas of plots of land by dividing them into rectangles and triangles. The Egyptians also learned how to measure the volumes of objects, like pyramids. Egyptian mathematics was famed throughout the Mediterranean, and it is likely that the early Greek mathematicians, masters of geometry like Thales and Pythagoras, studied in Egypt. Yet despite the Egyptians' brilliant geometric work, zero was nowhere to be found within Egypt. This was in part because the Egyptians were of a practical bent. They never progressed beyond measuring volumes and counting days and hours. Mathematics wasn't used for anything impractical except their system of astrology. As a result, their best mathematicians were unable to use the principles of geometry for anything unrelated to real-world problems. They did not take their system of mathematics and turn it into an abstract system of logic. They were also not inclined to put math into their philosophy. The Greeks were different. They embraced the abstract and the philosophical and brought mathematics to its highest point in ancient times. Yet it was not the Greeks who discovered zero. Zero came from the East, not the West. The birth of zero. In the history of culture, the discovery of zero will always stand out as one of the greatest single achievements of the human race. Tobias Danzig, Number, the Language of Science. The Greeks understood mathematics better than the Egyptians did. Once they mastered the Egyptian art of geometry, Greek mathematicians quickly surpassed their teachers. At first, the Greek system of numbers was quite similar to the Egyptians. Greeks also had a base 10 style of counting, and there was very little difference in the ways the two cultures wrote down their numbers. Instead of using pictures to represent numbers as the Egyptians did, the Greeks used letters. H, eta, stood for hekaton, 100. M, mu, stood for muriori, 10,000, the myriad, the biggest grouping in the Greek system. They also had a symbol for 5, indicating a mixed quinary decimal system, but overall the Greek and Egyptian systems of writing numbers were almost identical, for a time. Unlike the Egyptians, the Greeks outgrew this primitive way of writing numbers and developed a more sophisticated system. Instead of using 2 strokes to represent 2 or 3 H's to represent 300 as the Egyptian style of counting did, a newer Greek system of writing appearing before 500 BC had distinct letters for 2, 3, 300, and many other numbers. In this way, the Greeks avoided repeated letters. For instance, writing the number 87 in the Egyptian system would require 15 symbols, 8 heels and 7 vertical marks. The new Greek system would need only 2 symbols, pi for 80 and zeta for 7. The Roman system, which supplanted Greek numbers, was a step backward toward the less sophisticated Egyptian system. The Roman 87, LXXXVII, requires 7 symbols with several repeats. Though the Greek number system was more sophisticated than the Egyptian system, it was not the most advanced way of writing numbers in the ancient world. That title was held by another Eastern invention, the Babylonian style of counting. And thanks to this system, zero finally appeared in the East in the Fertile Crescent of present-day Iraq. At first glance, the Babylonian system seems perverse. For one thing, the system is sexagesimal, based on the number 60. This is an odd-looking choice, especially since most human societies chose 5, 10, or 20 as their base number. Also, the Babylonians used only 2 marks to represent their numbers, a wedge that represented 1 and a double wedge that represented 10. Groups of these marks arranged in clumps that summed to 59 or less were the basic symbols of the counting system, just as the Greek system was based on letters and the Egyptian system was based on pictures. But the really odd feature of the Babylonian system was that, instead of having a different symbol for each number like the Egyptian and Greek systems, each Babylonian symbol could represent a multitude of different numbers. A single wedge, for instance, could stand for 1, 60, 3,600, or countless others. As strange as this system seems to modernize, it made perfect sense to ancient peoples. It was the Bronze Age equivalent of computer code. The Babylonians, like many different cultures, had invented machines that helped them count. The most famous was the abacus. Known as the soroban in Japan, the swanpan in China, the счётчик in Russia, the kulba in Turkey, the choreb in Armenia, and by a variety of other names in different cultures, the abacus relies upon sliding stones to keep track of amounts. The words calculate, calculus, and calcium all come from the Latin word for pebble, calculus. Adding numbers on an abacus is as simple as moving the stones up and down. Stones in different columns have different values, and by manipulating them, a skilled user can add large numbers with great speed. When a calculation is complete, all the user has to do is look at the final position of the stones and translate that into a number. A pretty straightforward operation. The Babylonian system of numbering was like an abacus inscribed symbolically onto a clay tablet. Each grouping of symbols represented a certain number of stones that had been moved on the abacus, and like each column of the abacus, each grouping had a different value depending on its position. In this way, the Babylonian system was not so different from the system we use today. Each one in the number 111 stands for a different value. From right to left, they stand for 1, 10, and 100, respectively. Similarly, the symbol wedge in wedge, wedge, wedge stood for 1, 60, or 3600 in the three different positions. It was just like an abacus, except for one problem. How would a Babylonian write the number 60? The number 1 was easy to write, wedge. Unfortunately, 60 was also written as wedge. The only difference was that wedge was in the second position rather than the first. With the abacus, it's easy to tell which number is represented. A single stone in the first column is easy to distinguish from a single stone in the second column. The same isn't true for writing. The Babylonians had no way to denote which column a written symbol was in. Wedge could represent 1, 60, or 3600. It got worse when they mixed numbers. The symbol wedge wedge could mean 61, 3601, 3660, or even greater values. 0 was the solution to the problem. By around 300 BC, the Babylonians had started using two slanted wedges to represent an empty space, an empty column on the abacus. This placeholder mark made it easy to tell which position a symbol was in. Before the advent of 0, wedge wedge could be interpreted as 61 or 3601. But with 0, wedge wedge meant 61. 3601 was written as wedge slanted wedge wedge. 0 was born out of the need to give any given sequence of Babylonian digits a unique, permanent meaning. Though 0 was useful, it was only a placeholder. It was merely a symbol for a blank space in the abacus, a column where all the stones were at the bottom. It did little more than make sure digits fell in the right places. It didn't really have a numerical value of its own. After all, 000002148 means exactly the same thing as 2148. A 0 in a string of digits takes its meaning from some other digit to its left. On its own, it meant nothing. 0 was a digit, not a number. It had no value. A number's value comes from its place on the number line, from its position compared with other numbers. For instance, the number 2 comes before the number 3 and after the number 1. Nowhere else makes any sense. However, the 0 mark didn't have a spot on the number line at first. It was just a symbol. It didn't have a place in the hierarchy of numbers. Even today, we sometimes treat 0 as a non-number, even though we all know that 0 has a numerical value of its own, using the digit 0 as a placeholder without connecting it to the number 0. Look at a telephone or the top of a computer keyboard. The 0 comes after the 9, not before the 1 where it belongs. It doesn't matter where the placeholder 0 sits, it can be anywhere in the number sequence. But nowadays, everybody knows that 0 can't really sit anywhere on the number line because it has a definite numerical value of its own. It is the number that separates the positive numbers from the negative numbers. It is an even number, and it is the integer that precedes 1. 0 must sit in its rightful place on the number line before 1 and after -1. Nowhere else makes any sense. Yet 0 sits at the end of the computer and at the bottom of the telephone because we always start counting with 1. 1 seems like the appropriate place to start counting, but doing so forces us to put 0 in an unnatural place. To other cultures, like the Mayan people of Mexico and Central America, starting with 1 didn't seem like the rational thing to do. In fact, the Mayans had a number system and a calendar that made more sense than ours does. Like the Babylonians, the Mayans had a place value system of digits and places. The only real difference was that instead of basing their numbers on 60, as the Babylonians did, the Mayans had a vigesimal base 20 system that had the remnants of an earlier base 10 system in it. And like the Babylonians, they needed a 0 to keep track of what each digit meant. Just to make things interesting, the Mayans had 2 types of digits. The simple type was based on dots and lines, while the complicated type was based on glyphs, grotesque faces. To a modern eye, Mayan glyph writing is about as alien-looking as you can get. Like the Egyptians, the Mayans also had an excellent solar calendar. Because their system of counting was based on the number 20, the Mayans naturally divided their year into 18 months of 20 days each, totaling 360 days. A special period of 5 days at the end, called Uayeb, brought the count to 365. Unlike the Egyptians, though, the Mayans had a 0 in their counting system, so they did the obvious thing. They started numbering days with the number 0. The first day of the month of Zip, for example, was usually called the installation or seating of Zip. The next day was 1 Zip. The following day was 2 Zip, and so forth until they reached 19 Zip. The next day was the seating of Zots, 0 Zots, followed by 1 Zots, and so forth. Each month had 20 days, numbered 0 through 19, not numbered 1 through 20 as we do today. The Mayan calendar was wonderfully complicated. Along with his solar calendar, there was a ritual calendar that had 20 weeks, each of 13 days. Combined with the solar year, this created a calendar round that had a different name for every day in a 52-year cycle. The Mayan system made more sense than the Western system does. Since the Western calendar was created at a time when there was no 0, we never see a day 0 or a year 0. This apparently insignificant omission caused a great deal of trouble. It kindled the controversy over the start of the millennium. The Mayans would never have argued about whether 2000 or 2001 was the first year in the 21st century. But it was not the Mayans who formed our calendar. It was the Egyptians and later the Romans. For this reason, we are stuck with a troublesome zero-free calendar. The Egyptian civilization's lack of 0 was bad for the calendar and bad for the future of Western mathematics. In fact, Egyptian civilization was bad for math in more ways than one. It was not just the absence of a 0 that caused future difficulties. The Egyptians had an extremely cumbersome way of handling fractions. They didn't think of 3/4 as a ratio of 3 to 4 as we do today. They saw it as the sum of 1/2 and 1/4. With the sole exception of 2/3, all Egyptian fractions were written as a sum of numbers in the form of 1 over n, where n is a counting number, the so-called unit fractions. Long chains of these unit fractions made ratios extremely difficult to handle in the Egyptian and Greek number systems. 0 makes this cumbersome system obsolete. In the Babylonian system, with 0 in it, it's easy to write fractions. Just as we can write 0.5 for 1/2 and 0.75 for 3/4, the Babylonians used the numbers 030 for 1/2 and 045 for 3/4. In fact, the Babylonian base 60 system is even better suited to writing down fractions than our modern-day base 10 system. Unfortunately, the Greeks and Romans hated 0 so much that they clung to their own Egyptian-like notation rather than convert to the Babylonian system, even though the Babylonian system was easier to use. For intricate calculations like those needed to create astronomical tables, the Greek system was so cumbersome that the mathematicians converted the unit fractions to the Babylonian sexagesimal system, did the calculations, and then translated the answers back into the Greek style. They could have saved many time-consuming steps. We all know how fun it is to convert fractions back and forth. However, the Greeks so despised zero that they refused to admit it into their writings, even though they saw how useful it was. The reason? Zero was dangerous. The fearsome properties of nothing. In earliest times did Ymir live. Was nor sea, nor land, nor salty waves, neither earth was there, nor upper heaven, but a gaping nothing, and green things nowhere. The Elder Edda. It is hard to imagine being afraid of a number, yet zero was inexorably linked with the void, with nothing. There was a primal fear of void and chaos. There was also a fear of zero. Most ancient peoples believed that only emptiness and chaos were present before the universe came to be. The Greeks claimed that at first darkness was the mother of all things, and from darkness sprang chaos. Darkness and chaos then spawned the rest of creation. The Hebrew creation myths say that the earth was chaotic and void before God showered it with light and formed its features. The Hebrew phrase is tohu wavohu. Robert Graves linked these tohu to Tiamat, a primitive Semitic dragon that was present at the birth of the universe and whose body became the sky and earth. Bohu was linked to Bahamut, the famed behemoth monster of Hebrew legend. The older Hindu tradition tells of a creator who churns the butter of chaos into the earth, and the Norse myth tells a tale of an open void that gets covered with ice, and from the chaos caused by the mingling of fire and ice was born the primal giant. Emptiness and disorder were the primeval natural state of the cosmos, and there was always a nagging fear that at the end of time disorder and void would reign once more. Zero represented that void. But the fear of zero went deeper than unease about the void. To the ancients, zero's mathematical properties were inexplicable, as shrouded in mystery as the birth of the universe. This is because zero is different from the other numbers. Unlike the other digits in the Babylonian system, zero never was allowed to stand alone for good reason. A lone zero always misbehaves. At the very least, it does not behave the way other numbers do. Add a number to itself and it changes. 1 and 1 is not 1, it's 2. 2 and 2 is 4. But 0 and 0 is 0. This violates a basic principle of numbers called the axiom of Archimedes, which says that if you add something to itself enough times, it will exceed any other number in magnitude. The axiom of Archimedes was phrased in terms of areas. A number was viewed as the difference of two unequal areas. 0 refuses to get bigger. It also refuses to make any other number bigger. Add 2 and 0 and you get 2. It is as if you never bothered to add the numbers in the first place. The same thing happens with subtraction. Take 0 away from 2 and you get 2. 0 has no substance. Yet this substanceless number threatens to undermine the simplest operations in mathematics like multiplication and division. In the realm of numbers, multiplication is a stretch, literally. Imagine that the number line is a rubber band with tick marks on it. Multiplying by 2 can be thought of as stretching out the rubber band by a factor of 2. The tick mark that was at 1 is now at 2. The tick mark that was at 3 is now at 6. Likewise, multiplying by 1/2 is like relaxing the rubber band a bit. The tick mark at 2 is now at 1, and the tick mark at 3 winds up at 1.5. But what happens when you multiply by 0? Anything times 0 is 0, so all the tick marks are at 0. The rubber band has broken. The whole number line has collapsed. Unfortunately, there is no way to get around this unpleasant fact. 0 times anything must be 0. It's a property of our number system. For everyday numbers to make sense, they have to have something called the distributive property, which is best seen through an example. Imagine that a toy store sells balls in groups of 2 and blocks in groups of 3. The neighboring toy store sells a combination pack with 2 balls and 3 blocks in it. 1 bag of balls and 1 bag of blocks is the same thing as 1 combination package from the neighboring store. To be consistent, buying 7 bags of balls and 7 bags of blocks from one toy store has to be the same thing as buying 7 combination packs from the neighboring shop. This is the distributive property. Mathematically speaking, we say that 7 times 2 plus 7 times 3 equals 7 times, open parentheses, 2 plus 3, close parentheses. Everything comes out right. Apply this property to 0 and something strange happens. We know that 0 plus 0 equals 0, so a number multiplied by 0 is the same thing as multiplying by open parentheses 0 plus 0 close parentheses. Taking 2 as an example, 2 times 0 equals 2 times open parentheses 0 plus 0 close parentheses. But by the distributive property, we know that 2 times open parentheses 0 plus 0 close parentheses is the same thing as 2 times 0 plus 2 times 0. But this means 2 times 0 equals 2 times 0 plus 2 times 0. Whatever 2 times 0 is, when you add it to itself, it stays the same. This seems a lot like 0. In fact, that is just what it is. Subtract 2 times 0 from each side of the equation, and we see that 0 equals 2 times 0. Thus, no matter what you do, multiplying a number by 0 gives you 0. This troublesome number crushes the number line into a point. But as annoying as this property was, the true power of 0 becomes apparent with division, not multiplication. Just as multiplying by a number stretches the number line, dividing shrinks it. Multiply by 2 and you stretch the number line by a factor of 2. Divide by 2 and you relax the rubber band by a factor of 2, undoing the multiplication. Divide by a number and you undo the multiplication. A tick mark that had been stretched to a new place on the number line resumes its original position. We saw what happened when you multiply a number by 0. The number line is destroyed. Division by 0 should be the opposite of multiplying by 0. It should undo the destruction of the number line. Unfortunately, this isn't quite what happens. In the previous example, we saw that 2 times 0 is 0. Thus, to undo the multiplication, we have to assume that open parentheses 2 times 0 close parentheses divided by 0 will get us back to 2. Likewise, open parentheses 3 times 0 close parentheses divided by 0 should get us back to 3, and open parentheses 4 times 0 close parentheses divided by 0 should equal 4. But 2 times 0 and 3 times 0 and 4 times 0 each equal 0, as we saw. So, open parentheses 2 times 0 close parentheses divided by 0 equals 0 divided by 0, as do open parentheses 3 times 0 close parentheses divided by 0 and open parentheses 4 times 0 close parentheses divided by 0. Alas, this means that 0 divided by 0 equals 2, but it also equals 3 and it also equals 4. This just doesn't make any sense. Strange things also happen when we look at 1 divided by 0 in a different way. Multiplication by 0 should undo division by 0. So, 1 divided by 0 times 0 should equal 1. However, we saw that anything multiplied by 0 equals 0. There is no such number that, when multiplied by 0, yields 1, at least no number that we've met. Worst of all, if you wantonly divide by 0, you can destroy the entire foundation of logic and mathematics. Dividing by 0 once, just one time, allows you to prove mathematically anything at all in the universe. You can prove that 1 plus 1 equals 42, and from there you can prove that J. Edgar Hoover was a space alien, that William Shakespeare came from Uzbekistan, or even that the sky is polka-dotted. Multiplying by 0 collapses the number line, but dividing by 0 destroys the entire framework of mathematics. There is a lot of power in this simple number. It was to become the most important tool in mathematics, but thanks to the odd mathematical and philosophical properties of 0, it would clash with the fundamental philosophy of the West. Chapter 2. Nothing comes of nothing. The West rejects 0. Nothing can be created from nothing. Lucretius, De Rerum Natura. 0 clashed with one of the central tenets of Western philosophy, a dictum whose roots were in the number philosophy of Pythagoras and whose importance came from the paradoxes of Zeno. The whole Greek universe rested upon this pillar: there is no void. The Greek universe created by Pythagoras, Aristotle, and Ptolemy survived long after the collapse of Greek civilization. In that universe, there is no such thing as nothing. There is no 0. Because of this, the West could not accept 0 for nearly 2 millennia. The consequences were dire. 0's absence would stunt the growth of mathematics, stifle innovation in science, and, incidentally, make a mess of the calendar. Before they could accept 0, philosophers in the West would have to destroy their universe. The origin of Greek number philosophy. In the beginning there was the ratio, and the ratio was with God, and the ratio was God. John chapter 1 verse 1. The Egyptians who had invented geometry thought little about mathematics. For them it was a tool to reckon the passage of the days and to maintain plots of land. The Greeks had a very different attitude. To them, numbers and philosophy were inseparable, and they took both very seriously. Indeed, the Greeks went overboard when it came to numbers. Literally. Hippasus of Metapontum stood on the deck, preparing to die. Around him stood the members of a cult, a secret brotherhood that he had betrayed. Hippasus had revealed a secret that was deadly to the Greek way of thinking, a secret that threatened to undermine the entire philosophy that the brotherhood had struggled to build. For revealing that secret, the great Pythagoras himself sentenced Hippasus to death by drowning. To protect their number philosophy, the cult would kill. Yet, as deadly as the secret that Hippasus revealed was, it was small compared to the dangers of 0. The leader of the cult was Pythagoras, an ancient radical. According to most accounts, he was born in the 6th century B.C. on Samos, a Greek island off the coast of Turkey, famed for a temple to Hera and for really good wine. Even by the standards of the superstitious ancient Greeks, Pythagoras' beliefs were eccentric. He was firmly convinced that he was the reincarnated soul of Euphorbus, a Trojan hero. This helped convince Pythagoras that all souls, including those of animals, transmigrated to other bodies after death. Because of this, he was a strict vegetarian. Beans, however, were taboo as they generate flatulence and are like the genitalia. Pythagoras may have been an ancient New Age thinker, but he was a powerful orator, a renowned scholar, and a charismatic teacher. He was said to have written the constitution for the Greeks living in Italy. Students flocked to him, and he soon acquired a retinue of followers who wanted to learn from the master. The Pythagoreans lived according to the dicta of their leader. Among other things, they believed that it is best to make love to women in the winter, but not in the summer, that all disease is caused by indigestion, that one should eat raw food and drink only water, and that one must avoid wearing wool. But at the center of their philosophy was the most important tenet of the Pythagoreans: all is number. The Greeks had inherited their numbers from the geometric Egyptians. As a result, in Greek mathematics there was no significant distinction between shapes and numbers. To the Greek philosopher-mathematicians, they were pretty much the same thing. Even today we have square numbers and triangular numbers thanks to their influence. In those days, proving a mathematical theorem was often as simple as drawing an elegant picture. The tools of ancient Greek mathematics weren't pencil and paper, they were a straight edge and compasses. And to Pythagoras, the connection between shapes and numbers was deep and mystical. Every number shape had a hidden meaning, and the most beautiful number shapes were sacred. The mystical symbol of the Pythagorean cult was, naturally, a number shape, the pentagram, a five-pointed star. This simple figure is a glimpse at the infinite. Nestled within the lines of the star is a pentagram. Connecting the corners of that pentagram with lines generates a small upside-down five-pointed star, which is exactly the same as the original star in its proportions. This star in turn contains an even smaller pentagon, which contains a tinier star with its tiny pentagon, and so forth. As interesting as this was, to the Pythagoreans the most important property of the pentagram was not in this self-replication, but was hidden within the lines of the star. They contained a number shape that was the ultimate symbol of the Pythagorean view of the universe, the golden ratio. The importance of the golden ratio comes from a Pythagorean discovery that is now barely remembered. In modern schools, children learn of Pythagoras for his famed theorem: the square of the hypotenuse of a right triangle is equal to the sum of the squares of the other two sides. However, this was in fact ancient news. It was known more than 1,000 years before Pythagoras' time. In ancient Greece, Pythagoras was remembered for a different invention, the musical scale. One day, according to legend, Pythagoras was toying with a monochord, a box with a string on it. By moving a sliding bridge up and down the monochord, Pythagoras changed the notes that the device played. He quickly discovered that strings have a peculiar yet predictable behavior. When you pluck the string without the bridge, you get a clear note, the tone known as the fundamental. Putting the bridge on the monochord so it touches the string changes the notes that are played. When you place the bridge exactly in the middle of the monochord, touching the center of the string, each half of the string plays the same note, a tone exactly one octave higher than the string's fundamental. Shifting the bridge slightly might divide the string so that one side has 3/5 of the string and the other has 2/5. In this case, Pythagoras noticed that plucking the string segments creates two notes that form a perfect fifth, which is said to be the most powerful and evocative musical relationship. Different ratios gave different tones that could soothe or disturb. The discordant tritone, for instance, was dubbed the devil in music and was rejected by medieval musicians. Oddly enough, when Pythagoras put the bridge at a place that did not divide the string into a simple ratio, the plucked notes did not meld well. The sound was usually dissonant and sometimes even worse. Often the tone wobbled like a drunkard up and down the scale. To Pythagoras, playing music was a mathematical act. Like squares and triangles, lines were number shapes, so dividing a string into two parts was the same as taking a ratio of two numbers. The harmony of the monochord was the harmony of mathematics and the harmony of the universe. Pythagoras concluded that ratios govern not only music but also all other types of beauty. To the Pythagoreans, ratios and proportions controlled musical beauty, physical beauty, and mathematical beauty. Understanding nature was as simple as understanding the mathematics of proportions. This philosophy, the interchangeability of music, math, and nature, led to the earliest Pythagorean model of the planets. Pythagoras argued that the Earth sat at the center of the universe, and the sun, moon, planets, and stars revolved around the Earth, each pinned inside a sphere. The ratios of the sizes of the spheres were nice and orderly, and as the spheres moved, they made music. The outermost planets, Jupiter and Saturn, moved the fastest and made the highest pitched notes. The innermost ones, like the moon, made the lower notes. Taken all together, the moving planets made a harmony of the spheres, and the heavens are a beautiful mathematical orchestra. This is what Pythagoras meant when he insisted all is number. Because ratios were the keys to understanding nature, the Pythagoreans and later Greek mathematicians spent much of their energy investigating their properties. Eventually, they categorized proportions into 10 different classes, with names like the harmonic mean. One of these means yielded the most beautiful number in the world, the golden ratio. Achieving this blissful mean is a matter of dividing a line in a special way. Divide it in two so that the ratio of the small part to the large part is the same as the ratio of the large part to the whole. In other words, it doesn't seem particularly special, but figures imbued with this golden ratio seem to be the most beautiful objects. Even today, artists and architects intuitively know that objects that have this ratio of length to width are the most aesthetically pleasing, and the ratio governs the proportions of many works of art and architecture. Some historians and mathematicians argue that the Parthenon, the majestic Athenian temple, was built so that the golden ratio is visible in every aspect of its construction. Even nature seems to have the golden ratio in its design plans. Compare the ratios of the size of any two succeeding chambers of the Nautilus, or take the ratio of clockwise grooves to counterclockwise grooves in the pineapple, and you will see that these ratios approach the golden ratio. The pentagram became the most sacred symbol of the Pythagorean brotherhood because the lines of the star are divided in this special way. The pentagram is chock full of the golden ratio, and for Pythagoras, the golden ratio was the king of numbers. The golden ratio was favored by artists and nature alike, and seemed to prove the Pythagorean assertion that music, beauty, architecture, nature, and the very construction of the cosmos were all intertwined and inseparable. To the Pythagorean mind, ratios controlled the universe, and what was true for the Pythagoreans soon became true for the entire West. The supernatural link between aesthetics, ratios, and the universe became one of the central and long-lasting tenets of Western civilization. As late as Shakespeare's time, scientists talked about the revolution of orbs of different proportions and discussed the heavenly music that reverberated throughout the cosmos. Zero had no place within the Pythagorean framework. The equivalence of numbers and shapes made the ancient Greeks the masters of geometry, yet it had a serious drawback. It precluded anyone from treating zero as a number. What shape, after all, could zero be? It is easy to visualize a square with width 2 and height 2, but what is a square with width 0 and height 0? It is hard to imagine something with no width and no height, with no substance at all, being a square. This meant that multiplication by zero didn't make any sense either. Multiplying two numbers was equivalent to taking an area of a rectangle, but what could the area of a rectangle with zero height or zero width be? Nowadays, the great unsolved problems in mathematics are stated in terms of conjectures that mathematicians are unable to prove. In ancient Greece, however, number shapes inspired a different way of thinking. The famous unsolved problems of the day were geometric. With only a straight edge and compasses, could you make a square equal in area to a given circle? Could you use those tools to trisect an angle? Geometric constructions and shapes were the same thing. Zero was a number that didn't seem to make any geometric sense, so to include it, the Greeks would have had to revamp their entire way of doing mathematics. They chose not to. Even if zero were a number in the Greek sense, the act of taking a ratio with zero in it would seem to defy nature. No longer would a proportion be a relationship between two objects. The ratio of zero to anything, zero divided by a number, is always zero. The other number is completely consumed by the zero, and the ratio of anything to zero, a number divided by zero, can destroy logic. Zero would punch a hole in the neat Pythagorean order of the universe, and for that reason it could not be tolerated. Indeed, the Pythagoreans had tried to squelch another troublesome mathematical concept, the irrational. This concept was the first challenge to the Pythagorean point of view, and the Brotherhood tried to keep it secret. When the secret leaked out, the cult turned to violence. The concept of the irrational was hidden like a time bomb inside Greek mathematics. Thanks to the number-shaped duality, to the Greeks, counting was tantamount to measuring a line. Thus, a ratio of two numbers was nothing more than the comparison of two lines of different lengths. However, to make any sort of measurement, you need a standard, common yardstick to compare to the size of the lines. As an example, imagine a line exactly a foot long. Make a mark, say 5.5 inches from one end, dividing the foot into two unequal parts. The Greeks would figure out the ratio by dividing the line into tiny pieces using, for example, a standard or yardstick 1/2 inch long. One line segment contains 11 of those pieces, the other contains 13. The ratio of the two segments, then, is 11 to 13. For everything in the universe to be governed by ratios, as the Pythagoreans hoped, everything that made sense in the universe had to be related to a nice, neat proportion. It literally had to be rational. More precisely, these ratios had to be written in the form of A divided by B, where A and B were nice, neat counting numbers like 1, 2, or 47. Mathematicians are careful to note that B is not allowed to be 0, for that would be tantamount to division by 0, which we know to be disastrous. Needless to say, the universe is not really that orderly. Some numbers cannot be expressed as a simple ratio of A divided by B. These irrational numbers were an unavoidable consequence of Greek mathematics. The square is one of the simplest figures of geometry, and it was duly revered by the Pythagoreans. It had 4 sides corresponding to the 4 elements. It symbolized the perfection of numbers. But the irrational is nestled within the simplicity of the square. If you draw the diagonal, a line from one corner to the opposite corner, the irrational appears. As a concrete example, imagine a square whose sides are 1 foot long. Draw the diagonal. Ratio-obsessed people like the Greeks naturally looked at the side of the square and the diagonal and asked themselves, what is the ratio of the two lines? The first step again is to create a common yardstick, perhaps a tiny ruler 1/2 inch long. The next step is to use that yardstick to divide each of the two lines into equal segments. With a 1/2 inch yardstick, you can divide the foot-long side of the square into 24 segments, each 1/2 inch long. What happens when we measure the diagonal? Using the same yardstick, we see that the diagonal gets, well, almost 34 segments, but it doesn't come out quite evenly. The 34th segment is a wee bit too short. The 1/2 inch ruler juts out a little beyond the corner of the square. We can do better. Let's divide the line into even smaller segments, using, say, a ruler 1/6 of an inch long. The side of the square is partitioned into 72 segments, while the diagonal comes out to more than 101 but fewer than 102 segments. Again, the measurement is not quite perfect. What happens when we try really small segments, measuring in bits 1/millionth of an inch each? The side of the square gets 12 million bits, and the diagonal gets a tad less than 16,970,563 bits. Once again, a ruler doesn't fit both lines exactly. No matter what ruler we choose, our measurement never seems to come out right. In fact, no matter how tiny you make the bits, it is impossible to choose a common yardstick that will measure both the side and the diagonal perfectly. The diagonal is incommensurable with the side. However, without a common yardstick, it is impossible to express the two lines in a ratio. For a square of size 1, this means that we cannot choose counting numbers a and b such that the diagonal of the square can be expressed as a divided by b. In other words, the diagonal of that square is irrational, and nowadays we recognize that number as the square root of 2. This meant trouble for the Pythagorean doctrine. How could nature be governed by ratios and proportions when something as simple as a square can confound the language of ratios? This idea was hard for the Pythagoreans to believe, but it was incontrovertible, a consequence of the mathematical laws that they held so dear. One of the first mathematical proofs in history was about the incommensurability, irrationality of the square's diagonal. Irrationality was dangerous to Pythagoras as it threatened the basis of his ratio universe. To add insult to injury, the Pythagoreans soon discovered that the golden ratio, the ultimate Pythagorean symbol of beauty and rationality, was an irrational number. To keep these horrible numbers from ruining the Pythagorean doctrine, the irrationals were kept secret. Everyone in the Pythagorean Brotherhood was already tight-lipped, nobody was allowed even to take written notes, and the incommensurability of the square root of 2 became the deepest, darkest secret of the Pythagorean order. However, irrational numbers, unlike 0, could not easily be ignored by the Greeks. The irrationals occurred and reoccurred in all sorts of geometrical constructions. It would be hard to keep the secret of the irrational hidden from a people so obsessed with geometry and ratios. One day, someone was going to let the secret out. This someone was Hippasus of Metapontum, a mathematician and member of the Pythagorean Brotherhood. The secret of the irrationals would cause him great misfortune. The legends are very hazy and contain contradictory stories about the betrayal and ultimate fate of Hippasus. Mathematicians to this day tell of the hapless man who revealed the secret of the irrational to the world. Some say that the Pythagoreans tossed Hippasus overboard, drowning him, a just punishment for ruining a beautiful theory with harsh facts. Ancient sources talk about his perishing at sea for his impiety, or alternatively say that the Brotherhood banished him and constructed a tomb for him, expelling him from the world of human beings. But whatever Hippasus's true fate was, there is little doubt that he was reviled by his brothers. The secret he revealed shook the very foundations of the Pythagorean doctrine. But by considering the irrational an anomaly, the Pythagoreans could keep the irrationals from contaminating their view of the universe. Indeed, over time, the Greeks reluctantly admitted the irrationals to the realm of numbers. The irrationals didn't kill Pythagoras. Beans did. Just as the legends of Hippasus's murder are hazy, so too are the legends of Pythagoras's end. Nevertheless, they all imply that the master died in a bizarre way. Some say that Pythagoras starved himself, but the most common versions all say that beans were his undoing. One day, according to a version of the legend, his house was set ablaze by his enemies, who were angry at not being considered worthy to be admitted into Pythagoras's presence, and the brothers in the house scattered in all directions, running for their lives. The mob slaughtered Pythagorean after Pythagorean. The Brotherhood was being destroyed. Pythagoras himself fled for his life, and he might have gotten away had he not run smack into a bean field. There he stopped. He declared that he would rather be killed than cross the field of beans. His pursuers were more than happy to oblige. They cut his throat. Though the Brotherhood was scattered and the leader was dead, the essence of the Pythagorean teachings lived on. It was soon to become the basis of the most influential philosophy in Western history, the Aristotelian doctrine that would live for 2 millennia. 0 would clash with this doctrine, and unlike the irrational, 0 could be ignored. The number-shape duality in Greek numbers made it easy. After all, 0 didn't have a shape and could thus not be a number. Yet it was not the Greek number system that prevented 0's acceptance. Nor was it lack of knowledge. The Greeks had learned about 0 because of their obsession with the night sky. Like most ancient peoples, the Greeks were stargazers, and the Babylonians were the first masters of astronomy. They had learned how to predict eclipses. Thales, the first Greek astronomer, learned how to do this from the Babylonians, or perhaps through the Egyptians. In 585 BC, he was said to have predicted a solar eclipse. With Babylonian astronomy came Babylonian numbers. For astronomical purposes, the Greeks adopted a sexagesimal number system and even divided hours into 60 minutes and minutes into 60 seconds. Around 500 BC, the placeholder 0 began to appear in Babylonian writings. It naturally spread to the Greek astronomical community. During the peak of ancient astronomy, Greek astronomical tables regularly employed 0. Its symbol was the lowercase omicron, O, which looks very much like our modern-day 0, though it's probably a coincidence. Perhaps the use of omicron came from the first letter of the Greek word for nothing, uden. The Greeks didn't like 0 at all and used it as infrequently as possible. After doing their calculations with Babylonian notation, Greek astronomers usually converted the numbers back into clunky Greek-style numerals without 0. 0 never worked its way into ancient Western numbers, so it is unlikely that the omicron is the mother of our 0. The Greeks saw the usefulness of 0 in their calculations, yet they still rejected it. So it was not ignorance that led the Greeks to reject 0, nor was it the restrictive Greek number shape system. It was philosophy. 0 conflicted with the fundamental philosophical beliefs of the West, for contained within 0 are two ideas that were poisonous to Western doctrine. Indeed, these concepts would eventually destroy Aristotelian philosophy after its long reign. These dangerous ideas are the void and the infinite. The infinite, the void, and the West. So, naturalists observe, a flea hath smaller fleas that on him prey, and these have smaller yet to bite him, and so proceed ad infinitum. Jonathan Swift, On Poetry, a Rhapsody. The infinite and the void had powers that frightened the Greeks. The infinite threatened to make all motion impossible, while the void threatened to smash the nutshell universe into 1,000 flinders. By rejecting 0, the Greek philosophers gave their view of the universe the durability to survive for 2 millennia. Pythagoras' doctrine became the centerpiece of Western philosophy. All the universe was governed by ratios and shapes. The planets moved in heavenly spheres that made music as they turned. But what lay beyond these spheres? Were there more and more spheres, each larger than its neighbor? Or was the outermost sphere the end of the universe? Aristotle and later philosophers would insist that there could not be an infinite number of nested spheres. With the adoption of this philosophy, the West had no room for infinity or the infinite. They rejected it outright. For the infinite had already begun to gnaw at the roots of Western thought, thanks to Zeno of Elea, a philosopher reckoned by his contemporaries to be the most annoying man in the West. Zeno was born around 490 BC at the beginning of the Persian Wars, a great conflict between East and West. Greece would defeat the Persians. Greek philosophy would never quite defeat Zeno, for Zeno had a paradox, a logical puzzle that seemed intractable to the reasoning of Greek philosophers. It was the most troubling argument in Greece. Zeno had proved the impossible. According to Zeno, nothing in the universe could move. Of course, this is a silly statement. Anyone can refute it by walking across the room. Though everybody knew that Zeno's statement was false, nobody could find a flaw in Zeno's argument. He had come up with a paradox. Zeno's logical puzzle baffled Greek philosophers, as well as the philosophers who came after them. Zeno's riddles plagued mathematicians for nearly 2,000 years. In his most famous puzzle, the Achilles, Zeno proves that swift Achilles can never catch up with a lumbering tortoise that has a head start. To make things more concrete, let's put some numbers on the problem. Imagine that Achilles runs at 1 foot a second, while the tortoise runs at half that speed. Imagine, too, that the tortoise starts off a foot ahead of Achilles. Achilles speeds ahead, and in a mere second he is caught up to where the tortoise was. But by the time he reaches that point, the tortoise, which is also running, has moved ahead by half a foot. No matter, Achilles is faster, so in half a second he makes up the half foot. But again, the tortoise has moved ahead, this time by a quarter foot. In a flash, a quarter second, Achilles has made up the distance. But the tortoise lumbers ahead in that time by 1/8 of a foot. Achilles runs and runs, but the tortoise scoots ahead each time. No matter how close Achilles gets to the tortoise, by the time he reaches the point where the tortoise was, the tortoise has moved. 1/8 of a foot, a 16th of a foot, a 32nd of a foot, smaller and smaller distances, but Achilles never catches up. The tortoise is always ahead. Everybody knows that in the real world Achilles would quickly run past the tortoise, but Zeno's argument seemed to prove that Achilles could never catch up. The philosophers of his day were unable to refute the paradox. Even though they knew that the conclusion was wrong, they could never find a mistake in Zeno's mathematical proof. The philosophers' main weapon was logic, but logical deduction seemed useless against Zeno's argument. Each step along the way seemed airtight, and if all the steps are correct, how could the conclusion be wrong? The Greeks were stumped by the problem, but they did find the source of the trouble: infinity. It is the infinite that lies at the heart of Zeno's paradox. Zeno had taken continuous motion and divided it into an infinite number of tiny steps. Because there are an infinite number of steps, the Greeks assumed that the race would go on forever and ever, even though the steps get smaller and smaller. The race would never finish in finite time, or so they thought. The ancients didn't have the equipment to deal with the infinite, but modern mathematicians have learned to handle it. The infinite must be approached very carefully, but it can be mastered with the help of zero. Armed with 2,400 years' worth of extra mathematics, it is not hard for us to go back and find Zeno's Achilles heel. The Greeks did not have zero, but we do, and it is the key to solving Zeno's puzzle. It is sometimes possible to add infinite terms together to get a finite result, but to do so, the terms being added together must approach zero. This is the case with Achilles and the tortoise. When you add up the distance that Achilles runs, you start with the number 1, then add 1/2, then add 1/4, then add 1/8, and so on, with the terms getting smaller and smaller, getting closer and closer to zero. Each term is like a step along a journey where the destination is zero. However, since the Greeks rejected the number zero, they couldn't understand that this journey could ever have an end. To them, the numbers 1, 1/2, 1/4, 1/8, 1/16, and so forth aren't approaching anything. The destination doesn't exist. Instead, the Greeks just saw the terms as simply getting smaller and smaller, meandering outside the realm of numbers. Modern mathematicians know that the terms have a limit. The numbers 1, 1/2, 1/4, 1/8, 1/16, and so forth are approaching zero as their limit. The journey has a destination. Once the journey has a destination, it is easy to ask how far away that destination is and how long it will take to get there. It is not that difficult to sum up the distances that Achilles runs. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and so forth and so on, plus 1 divided by 2 to the nth, plus, and so forth and so on. In the same way that the steps that Achilles takes get smaller and smaller and closer to zero, the sum of those steps gets closer and closer to 2. How do we know this? Well, let's start off with 2 and subtract the terms of the sum one by one. We begin with 2 minus 1, which is, of course, 1. Next, we subtract 1/2, leaving 1/2. Then remove the next term. Subtract 1/4, leaving 1/4 behind. Subtracting 1/8 leaves 1/8 behind. We're back to our familiar sequence. We already know that 1, 1/2, 1/4, 1/8, and so forth has a limit of 0. Thus, as we subtract the terms from 2, we have nothing left. The limit of the sum 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so forth and so on, is 2. Achilles runs 2 feet in catching up to the tortoise, even though he takes an infinite number of steps to do it. Better yet, look at the time it takes Achilles to overtake the tortoise. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and so forth and so on, to 2 seconds. Not only does Achilles take an infinite number of steps to run a finite distance, but he takes only 2 seconds to do it. The Greeks couldn't do this neat little mathematical trick. They didn't have the concept of a limit because they didn't believe in zero. The terms in the infinite series didn't have a limit or a destination. They seemed to get smaller and smaller without any particular end in sight. As a result, the Greeks couldn't handle the infinite. They pondered the concept of the void but rejected zero as a number, and they toyed with the concept of the infinite but refused to allow infinity, numbers that are infinitely small and infinitely large, anywhere near the realm of numbers. This is the biggest failure in Greek mathematics, and it is the only thing that kept them from discovering calculus. Infinity, zero, and the concept of limits are all tied together in a bundle. Greek philosophers were unable to untie that bundle, therefore they were ill-equipped to solve Zeno's puzzle. Yet Zeno's paradox was so powerful that the Greeks tried over and over to explain away his infinities. They were doomed to failure, unarmed with the proper concepts. Zeno himself didn't have a proper solution to the paradox, nor did he seek one. The paradox suited his philosophy perfectly. He was a member of the Eleatic school of thought, whose founder, Parmenides, held that the underlying nature of the universe was changeless and immobile. Zeno's puzzles appear to have been in support of Parmenides' argument. In showing that change and motion were paradoxical, he hoped to convince people that everything is one and changeless. Zeno really did believe that motion was impossible, and his paradox was this theory's chief support. There were other schools of thought. The atomists, for example, believed that the universe is made up of little particles called atoms, which are indivisible and eternal. Motion, according to the atomists, was the movement of these little particles. Of course, for these atoms to move, there has to be empty space for them to move into. After all, these little atoms had to move around somehow. If there were no such thing as a vacuum, the atoms would be constantly pressed against one another. Everything would be stuck in one position for eternity, unable to move. Thus, the atomic theory required that the universe be filled with emptiness, an infinite void. The atomists embraced the concept of the infinite vacuum, infinity and zero wrapped into one. This was a shocking conclusion, but the indivisible kernels of matter in atomic theory got around the problem of Zeno's paradoxes. Because atoms are indivisible, there is a point beyond which things could not be divided. Zeno's hair-splitting doesn't go on ad infinitum. After a number of strides, Achilles would be taking tiny steps that can't get any smaller. Eventually, he would have to hurdle an atom that the tortoise doesn't. Achilles would finally catch up to the elusive turtle. Another philosophy vied with the atomic theory, and instead of posing such bizarre concepts as the infinite vacuum, it turned the universe into a cozy nutshell. There was no infinity, no void, just beautiful spheres that surrounded the earth, which was naturally placed at the very center of the universe. This was the Aristotelian system, which was later refined by the Alexandrian astronomer Ptolemy. It became the dominant philosophy in the Western world, and by rejecting zero and infinity, Aristotle explained away Zeno's paradoxes. Aristotle simply declared that mathematicians do not need the infinite or use it. Though potential infinities could exist in the minds of mathematicians, like the concept of dividing lines into infinite pieces, nobody could actually do it, so the infinite doesn't exist in reality. Achilles runs smoothly past the tortoise because the infinite points are simply a figment of Zeno's imagination rather than a real-world construct. Aristotle just wished infinity away by stating that it is simply a construct of the human mind. From that concept comes a startling revelation. Based upon the Pythagorean universe, the Aristotelian cosmos, and its later refinement by the astronomer Ptolemy, had the planets moving in crystalline orbs. However, since there is no infinity, there can't be an endless number of spheres. There must be a last one. This outermost sphere was a midnight blue globe encrusted with tiny glowing points of light, the stars. There was no such thing as beyond the outermost sphere. The universe ended abruptly with that outermost layer. The universe was contained in a nutshell, ensconced comfortably within the sphere of fixed stars. The cosmos was finite in extent and entirely filled with matter. There was no infinite, there was no void. There was no infinity, there was no zero. This line of reasoning had another consequence, and this is why Aristotle's philosophy endured for so many years. His system proved the existence of God. The heavenly spheres are slowly spinning in their places, making a music that suffuses the cosmos. But something must be causing that motion. The stationary Earth cannot be the source of that motive power, so the innermost sphere must be moved by the next sphere out. That sphere, in turn, is moved by its larger neighbor, and on and on. However, there is no infinity. There are a finite number of spheres and a finite number of things that are moving each other. Something must be the ultimate cause of motion. Something must be moving the sphere of fixed stars. This is the prime mover, God. When Christianity swept through the West, it became closely tied to the Aristotelian view of the universe and the proof of God's existence. Atomism became associated with atheism. Questioning the Aristotelian doctrine was tantamount to questioning God's existence. Aristotle's system was extremely successful. His most famous student, Alexander the Great, spread the doctrine as far east as India before Alexander's untimely death in 323 BC. The Aristotelian system would outlast Alexander's empire. It would survive until Elizabethan times, the 16th century. With this long-standing acceptance of Aristotle came a rejection of the infinite and the void, for Aristotle's denial of the infinite required a denial of the void because the void implies the existence of the infinite. After all, there were only two logical possibilities for the nature of the void, and both implied that the infinite exists. First, there could be an infinite amount of void, thus infinity exists. Second, there could be a finite amount of void, but since void is simply the lack of matter, there must be an infinite amount of matter to make sure that there is only a finite amount of void, thus infinity exists. In both cases, the existence of the void implies the existence of the infinite. Void zero destroys Aristotle's neat argument, his refutation of Zeno, and his proof of God. So, as Aristotle's arguments were accepted, the Greeks were forced to reject zero, void, the infinite, and infinity. There was a problem, though. It is not so easy to reject both infinity and zero. Look back through time. Events have happened throughout history, but if there is no such thing as infinity, there cannot be an infinite number of events. Thus, there must be a first event, creation. But what existed before creation? Void? That was unacceptable to Aristotle. Conversely, if there was not a first event, then the universe must have always existed and will always exist in the future. You've got to have either infinity or zero. A universe without both of them makes no sense. Aristotle hated the idea of the void so much that he chose the eternal, infinite universe over one that had a vacuum in it. He said that the eternity of time was a potential infinity, like Zeno's infinite subdivisions. It was a stretch, but many scholars bought the argument. Some even chose the creation story as further evidence for God. Medieval philosophers and theologians were doomed to battle over this puzzle for several hundred years. The Aristotelian view of physics, as wrong as it was so influential that for more than a millennium it eclipsed all opposing views, including more realistic ones. Science would never progress until the world discarded Aristotle's physics, along with Aristotle's rejection of Zeno's infinities. For all his wit, Zeno got himself into serious trouble. Around 435 BC, he conspired to overthrow the tyrant of Elea, Nearchus. He was smuggling arms to support the cause. Unfortunately for Zeno, Nearchus found out about the plot and Zeno was arrested. Hoping to discover who the co-conspirators were, Nearchus had Zeno tortured. Soon, Zeno begged the torturers to stop and promised that he would name his colleagues. When Nearchus drew near, Zeno insisted that the tyrant come closer, since it was best to keep the names a secret. Nearchus leaned over, tilting his head toward Zeno. All of a sudden, Zeno sank his teeth into Nearchus's ear. Nearchus screamed, but Zeno refused to let go. The torturers could only force Zeno to let go by stabbing him to death. Thus died the master of the infinite. Eventually, one ancient Greek surpassed Zeno in matters of the infinite, Archimedes, the eccentric mathematician of Syracuse. He was the only thinker of his day to glimpse the infinite. Syracuse was the richest city on the island of Sicily, and Archimedes was its most famous resident. Little is known about his youth, but it seems that Archimedes was born around 287 BC in Samos, Pythagoras' birthplace. He then immigrated to Syracuse, where he solved engineering problems for the king. It was the king of Syracuse who asked Archimedes to determine whether his crown was pure gold or had been mixed with lead, a task beyond the abilities of all the scientists at the time. However, when Archimedes settled into a tub of water, he noticed that the water flowed over the sides, and he suddenly realized that he could measure the density of the crown and thus its purity by submerging it in a tub of water and measuring how much water it displaced. Elated by the insight, Archimedes leaped out of the tub and ran through the streets of Syracuse shouting, "Eureka! Eureka!" Of course, Archimedes forgot that he was stark naked. Archimedes' talents were useful to the Syracusan military as well. In the 3rd century BC, the era of Greek hegemony was over. Alexander's empire had collapsed into bickering states, and a new power was flexing its muscles in the west, Rome. And Rome had set its sights on Syracuse. According to legend, Archimedes armed the Syracusans with miraculous weapons to defend the city from the Romans: stone throwers, huge cranes that grabbed the Roman warships, lifted them up and dumped them bow first into the water, and mirrors made of such quality that they set Roman ships afire at a great distance by reflecting sunlight. The Roman soldiers were so afraid of these war engines that if they saw so much as a bit of rope or wood sticking over the wall, they would flee for fear that Archimedes was aiming a weapon at them. Archimedes first glimpsed the infinite in the polish of his war mirrors. For centuries, the Greeks had been fascinated with conic sections. Take a cone and cut it up, you get circles, ellipses, parabolas, and hyperbolas, depending on how you slice it. The parabola has a special property. It takes the rays of light from the sun or any distant source and focuses them to a point, concentrating all the light's energy on a very small area. Any mirror that could set ships afire must be in the shape of a parabola. Archimedes studied the properties of the parabola, and it is here that he first started toying with the infinite. To understand the parabola, Archimedes had to learn how to measure it. For instance, nobody knew how to determine the area of a section of a parabola. Triangles and circles were easy to measure, but slightly more irregular curves like the parabola were beyond the ken of the Greek mathematicians of the day. However, Archimedes figured out a way to measure the parabola's area by resorting to the infinite. The first step was to inscribe a triangle inside the parabola. In the two little gaps left, Archimedes inscribed more triangles. This left 4 gaps, which were filled with more triangles, and so on. It's like Achilles and the tortoise, an infinite series of steps, each getting smaller and smaller. The areas of the little triangles quickly approach 0. After a long, involved set of calculations, Archimedes summed the areas of the infinite triangles and divined the area of the parabola. However, any mathematician of the day would have scoffed at this line of reasoning. Archimedes used the tools of the infinite, which were so expressly disallowed by his mathematical colleagues. To satisfy them, Archimedes also included a proof based upon the accepted mathematics of the time that relied upon the so-called axiom of Archimedes, although Archimedes himself mentioned that earlier mathematicians deserved the credit. As you may recall, this axiom says that any number added to itself over and over again can exceed any other number. 0 clearly was not included. Archimedes' proof by triangles was as close as you could come to the idea of limits and calculus without actually discovering them. In later works, Archimedes figured out the volumes of parabolas and circles rotated around a line, which any math student knows are early homework problems in a calculus course. But the axiom of Archimedes rejected 0, which is the bridge between the realms of the finite and the infinite, a bridge that is absolutely necessary for calculus and higher mathematics. Even the brilliant Archimedes occasionally scorned the infinite along with his contemporaries. He believed in the Aristotelian universe. The universe was contained within a giant sphere. On a whim, he decided to calculate how many grains of sand could fit in the spherical universe. In his sand reckoner, Archimedes first calculated how many grains of sand would fit across a poppy seed, and then how many poppy seeds would span a finger's breadth. From finger breadths to the length of a stadium, the standard Greek unit of long distance, and on to the size of the universe, Archimedes figured out that 10 to the 51st grains of sand would fill the entire universe, packed full even unto the outermost sphere of fixed stars. 10 to the 51st is a really, really big number. Take 10 to the 51st molecules of water, for instance. It would take every man, woman, and child now on Earth, each drinking a ton of water a second, over 150 years to drink it all. This number was so large that the Greek system of numeration was unable to handle it. Archimedes had to invent a whole new method of denoting really huge numbers. The myriad was the biggest grouping in the Greek number system, and by counting myriads, the Greeks could denote numbers up to a myriad myriads, 100 million, and a little further. But Archimedes got beyond this limitation by hitting the reset button. He simply started over at a myriad myriads, setting 100 million equal to 1, and counting again, calling these new numbers numbers of the second order. Archimedes did not set 100 million 1 equal to 1 and 100 million equal to 0, which is what a modern mathematician would do. It had never occurred to Archimedes that starting over with 0 would make more sense. The numbers of the second order went from 1 myriad myriads to a myriad 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 myriads. The numbers of the third order went to 1 myriad 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 myriads, 1 septillion, and so forth, until he reached the numbers of the myriad myriadth order, which he called the numbers of the first period. It was a cumbersome way of doing business, but it got the job done and went far beyond what Archimedes needed to solve his thought experiment. Yet as big as those numbers were, they were finite, and were more than enough to fill the universe to overflowing with sand. The infinite was not needed in the Greek universe. Perhaps, given more time, Archimedes might have begun to see the lure of the infinite and of 0. But the sand reckoner was destined to meet his fate while reckoning in the sand. The Romans were too powerful for the Syracusans. Taking advantage of a poorly manned watchtower and an easy-to-climb wall, the Romans managed to get some soldiers inside the city. As soon as they realized that Romans were inside the walls of the city, the Syracusans, wild with fear, could not mount a defense. The Romans poured through the city, but Archimedes was deaf to the panic around him. He sat on the ground, drawing circles in the sand, trying to prove a theorem. A Roman soldier saw the bedraggled 75-year-old and demanded that Archimedes follow him. Archimedes refused, since his mathematical proof was not yet finished. The enraged soldier cut him down. Thus died the greatest mind in the ancient world, slaughtered needlessly by the Romans. Killing Archimedes was one of the biggest Roman contributions to mathematics. The Roman era lasted for about 7 centuries. In all that time, there were no significant mathematical developments. History marched on. Christianity swept through Europe. The Roman Empire fell. The library at Alexandria burned, and the Dark Ages began. It would be another 7 centuries before 0 reappeared in the West. In the meantime, 2 monks created a calendar without 0, damning us to eternal confusion. Blind dates. It is a silly, childish discussion and only exposes the want of brains of those who maintain a contrary opinion to that we have stated. The Times, London, December 26, 1799. This silly, childish discussion, whether the new century begins on the year 00 or the year 01, appears and reappears like clockwork every 100 years. If medieval monks had only known of 0, our calendar would not be in such a muddle. The monks can't be faulted for their ignorance. Indeed, during the Middle Ages, the only Westerners who studied math were the Christian monks. They were the only learned ones left. Monks needed math for 2 things, prayer and money. To count money, they needed to know how to, well, count. To do this, they used an abacus or a counting board, a device similar to an abacus, where stones or other counters get moved around on a table. It was not a very demanding task, but by ancient standards it was the state of the art. To pray, monks needed to know the time and the date. As a result, timekeeping was vital to the monks' rituals. They had different prayers to be said at different hours, day in and day out. Our word noon comes from the word nones, the midday prayer service of medieval clergy. How else would the night watchman know when to roust his fellows out of their comfortable straw beds to begin the day's devotions? And if you didn't have an accurate calendar, you couldn't know when to celebrate Easter. This was a big problem. Calculating the date of Easter was no mean feat, thanks to a clash of calendars. The seat of the church was Rome, and Christians used the Roman solar calendar that was 365 days and change long. But Jesus was a Jew, and he used the Jewish lunar calendar that was only 354 days and change long. The big events in Jesus' life were marked with reference to the moon, while everyday life was ruled by the sun. The two calendars drifted with respect to each other, making it very difficult to predict when a holiday was due. Easter was just such a drifting holiday. So every few generations a monk was drafted to calculate the dates when Easter would fall for the next few hundred years. Dionysius Exiguus was one of these monks. In the 6th century, the Pope, John I, asked him to extend the Easter tables. While translating and recalculating the tables, Dionysius did a little research on the side. He realized that he could figure out just when Jesus Christ was born. After chugging through a bit of math, he decided that the current year was the 525th year since the birth of Christ. Dionysius decided that the year of Christ's birth should thenceforth be the year 1 Anno Domini, or the first year of our Lord. Technically, Dionysius said that Christ's birth happened on December 25th the year before, and he started his calendar on January 1st to match the Roman year. The next year after that was 2 A.D., and the next 3 A.D., and so forth, replacing the two dating systems then most commonly in use. But there was a problem. Make that 2. For one thing, Dionysius got the date of Christ's birth wrong. The sources agree that Mary and Joseph fled the wrath of King Herod, since Herod had heard a prophecy about a newborn Messiah. But Herod died in 3 B.C., years before the supposed birth of Christ. Dionysius was clearly wrong. Today, most scholars believe that the birth of Christ was in 4 B.C. Dionysius was a few years off. In truth, this mistake was not so terrible. When choosing the first year of a calendar, it really doesn't matter which year is chosen, so long as everything is consistent after that. A 4-year error is inconsequential if everyone agrees to make the same mistake, as indeed we have. But there was a more serious problem with Dionysius's calendar: 0. There was no year 0. Normally, this would be no big deal. Most calendars of that day started with the year 1, not the year 0. Dionysius didn't even have a choice. He didn't know about 0. He was brought up after the decline of the Roman Empire. Even during the heyday of Rome, the Romans were not exactly math whizzes. In the year 525, at the start of the Dark Ages, all Westerners clung to the clunky Roman style of numbers, and there was no 0 in that counting system. To Dionysius, the first year of our Lord was naturally the year 1. The next year was year 2. And Dionysius came to this conclusion in the year DXXV, or 525. In most circumstances, this would not have caused any trouble, especially since Dionysius's calendar did not catch on immediately. In 525, there was serious trouble for the intellectuals in the Roman court. Pope John died, and in the ensuing power shift, all the philosophers and mathematicians like Dionysius were kicked out of office. They were lucky to escape with their lives. Others were not so lucky. Anicius Boethius was a powerful courtier who was among the finest medieval Western mathematicians, which makes him worth noting. At about the same time that Dionysius was kicked out of office, Boethius, too, fell from power and was imprisoned. Boethius was not remembered for his math but for his Consolation of Philosophy, a tract in which he comforts himself with Aristotelian-style philosophy. He was clubbed to death soon afterward. In any case, the new calendar languished for years. The lack of a year zero began to cause problems 2 centuries later. In 731 AD, about the time Dionysius's Easter tables were set to run out, Bede, a soon-to-be venerable monk from the northern part of England, extended them again. This is probably how he came to know of Dionysius's work. When Bede wrote a history of the Church in Britain, the ecclesiastical history of the English people, he used the new calendar. The book was a huge success, but it had one significant flaw. Bede started his history with the year 60 BC, 60 years before Dionysius's reference year. Bede didn't want to abandon the new dating system, so he extended Dionysius's calendar backward. To Bede, also ignorant of the number 0, the year that came before 1 AD was 1 BC. There was no year 0. After all, to Bede, 0 didn't exist. At first glance, this style of numbering might not seem so bad, but it guaranteed trouble. Think of the AD years as positive numbers and the BC years as negative ones. Bede's style of counting went -3, -2, -1, 1, 2, 3. 0, whose proper place is between -1 and 1, is nowhere to be seen. This throws everybody off. In 1996, an article about the calendar in the Washington Post told people how to think about the millennium controversy, and casually mentioned that since Jesus was born in 4 BC, the year 1996 was the 2000th year since his birth. That makes perfect sense. 1996 minus -4 equals 2000. But it is wrong. It was actually only 1,999 years. Imagine a child born on January 1st in the year 4 BC. In 3 BC, he turns 1 year old. In 2 BC, he turns 2 years old. In 1 BC, he turns 3 years old. In 1 AD, he turns 4 years old. In 2 AD, he turns 5 years old. On January 1st in 2 AD, how many years has it been since he was born? 5 years, obviously. But this isn't what you get if you subtract the years. 2 minus -4 equals 6 years old. You get the wrong answer because there is no year 0. By rights, the child should have turned 4 years old on January 1st in the year 0 AD, 5 in 1 AD, and 6 in 2 AD. Then all the numbers would come out right, and figuring out the child's age would be a simple matter of subtracting -4 from 2. But it isn't so. You've got to subtract an additional year from the total to get the right answer. Hence, Jesus was not 2,000 years old in 1996, he was only 1,999. It's very confusing, and it gets worse. Imagine a child born in the first second of the first day of the first year, January 1st in 1 AD. In the year 2, he would be 1 year old. In the year 3, he would be 2, and so forth. In the year 99, he'd be 98 years old. And in the year 100, he'd be 99 years old. Now imagine that this child is named Century. The century is only 99 years old in the year 100 and only celebrates its 100th birthday on January 1st in the year 101. Thus, the second century begins in the year 101. Likewise, the third century begins in the year 201, and the 20th century begins in the year 1901. This means that the 21st century and the third millennium begins in the year 2001. Not that you'd notice. Hotels and restaurants around the world were completely booked well in advance for December 31st, 1999. Not so for December 31st, 2000. Everybody celebrated the turn of the millennium on the wrong date. Even the Royal Greenwich Observatory, the official keeper of the world's time and arbiter of all things chronological, planned to be swamped by the revelers. While the atomic precision clocks ticked away in the observatory on the hill, the masses down below awaited a state-sponsored millennium experience, complete with a spectacular opening ceremony that the organizers scheduled for, you guessed it, December 31st, 1999. The exhibit's close on December 31st, 2000 is just when the astronomers on the top of the hill crack open their champagne bottles to celebrate the turn of the millennium. That is, of course, assuming that astronomers care about the date at all. Astronomers can't play with time as easily as everyone else can. After all, they are watching the clockwork of the heavens, a clockwork that does not hiccup on leap years or reset itself every time humans decide to change the calendar. Thus, the astronomers decided to ignore human calendars altogether. They don't measure time in years since the birth of Christ. They count days since January 1st, 4713 BC, a pretty much arbitrary date that the scholar Joseph Scaliger chose in 1583. His Julian date, named after his father Julius rather than Julius Caesar, became the standard way to refer to astronomical events, because it avoided all the weirdness caused by calendars that were constantly under construction. The system has since been modified slightly. Modified Julian date is simply the Julian date less 2,400,000 days and 12 hours, putting the 0 hour at midnight on November 17, 1858. Again, a more or less arbitrary date. Perhaps astronomers will refuse to celebrate 51542 modified Julian date, and the Jews will ignore 23 Tevet 5760 Anno Mundi, and the Muslims will forget about 23 Ramadan 1420 Anno Hejire. On second thought, probably not. They will all know that it is December 31st, 1999, Anno Domini, and there is something very special about the year 2000. It's hard to say just why, but we humans love nice, round numbers with lots of zeros. How many of us remember being a child and going for a ride in a car that was about to top the 20,000-mile mark? Everybody in the car waits silently as 19,999.9 slowly creeps forward, and then, with a click, 20,000. All the children cheer. December 31st, 1999 is the evening when the great odometer in the sky clicks ahead. The zeroth number. Wacław Sierpiński, the great Polish mathematician, was worried that he'd lost one piece of his luggage. "No, dear," said his wife, "all 6 pieces are here." "They can't be true," said Sierpiński. "I've counted them several times. 0, 1, 2, 3, 4, 5. John Conway and Richard Guy, The Book of Numbers. It may seem bizarre to suggest that Dionysius and Bede made a mistake when they forgot to include 0 in their calendar. After all, children count 1, 2, 3, not 0, 1, 2. Except for the Mayans, nobody else had a year 0 or started a month with day 0. It seems unnatural. On the other hand, when you count backward, it is second nature. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, liftoff. The space shuttle always waits for 0 before it blasts into the air. An important event happens at the 0 hour, not the 1 hour. When you drive toward the site where a bomb went off, you're approaching ground zero. If you look carefully enough, you will see that people usually do start counting with 0. A stopwatch starts ticking from 000.00 and only reaches 001.00 after a second has elapsed. A car's odometer comes from the factory set at 00000, though by the time the dealer's done tooling around town, it's probably got a few more miles on it. The military's day officially begins at 0000 hours, but count aloud, and you always start with 1 unless you're a mathematician or a computer programmer. It has to do with order. When we are dealing with the counting numbers, 1, 2, 3, and so on, it is easy to rank them in order. 1 is the first counting number, 2 is the second counting number, and 3 is the third. We don't have to worry about mixing up the value of the number, its cardinality, with the order in which it arrives, its ordinality, since they are essentially the same thing. For years, this was the state of affairs, and everybody was happy. But as 0 came into the fold, the neat relationship between a number's cardinality and its ordinality was ruined. The numbers went 0, 1, 2, 3. 0 came first, 1 was second in line, and 2 was in third place. No longer were cardinality and ordinality interchangeable. This is the root of the calendar problem. The first hour of the day starts at 0 seconds past midnight. The second hour starts at 1 a.m. and the third hour starts at 2 a.m. Though we count with the ordinals, first, second, third, we mark time with the cardinals, 0, 1, 2. All of us have assimilated this way of thinking, whether we appreciate it or not. After a baby finishes his 12th month, we all say that the child is 1 year old. He has finished his first 12 months of life. If the baby turns 1 when she's already lived a year, isn't the only consistent choice to say that the baby is 0 years old before that time? Of course, we say that the child is 6 weeks old or 9 months old instead, a clever way of getting around the fact that the baby is 0. Dionysius didn't have a 0, so he started the calendar with year 1, just as the ancients before him had started theirs. People of those times thought in terms of the old-style equivalents of cardinality and ordinality. That was just fine for them. If 0 never entered their minds, it could hardly be a problem. The gaping void. It was not absolute nothingness. It was a kind of formlessness without any definition. True reasoning convinced me that I should wholly subtract all remnants of every kind of form if I wished to conceive the absolutely formless. I could not achieve this. St. Augustine, Confessions. It's hard to blame the monks for their ignorance. The world of Dionysius Exiguus, Boethius, and Bede was dark indeed. Rome had collapsed, and Western civilization seemed but a shadow of Rome's past glory. The future seemed more horrid than the past. It is no wonder that in the search for wisdom, medieval scholars didn't look to their peers for ideas. Instead, they turned to the ancients like Aristotle and the Neoplatonists. As these medieval thinkers imported the philosophy and science of the ancients, they inherited the ancient prejudices, a fear of the infinite and a horror of the void. Medieval scholars branded void as evil and evil as void. Satan was quite literally nothing. Boethius made the argument as follows: God is omnipotent, there is nothing God cannot do. But God, the ultimate goodness, cannot do evil, therefore evil is nothing. It made perfect sense to the medieval mind. Lurking underneath the veil of medieval philosophy, however, was a conflict. The Aristotelian system was Greek, but the Judeo-Christian story of creation was Semitic, and Semites didn't have such a fear of the void. The very act of creation was out of a chaotic void, and theologians like St. Augustine, who lived in the 4th century, tried to explain it away by referring to the state before creation as a nothing something, that is, empty of form, but yet fall short of utter nothingness. The fear of the void was so great that Christian scholars tried to fix the Bible to match Aristotle rather than vice versa. Luckily, not all civilizations were so afraid of 0. Chapter 3. Nothing ventured. 0 goes east. Where there is the infinite, there is joy. There is no joy in the finite. The Chandogya Upanishad. Though the West was afraid of the void, the East welcomed it. In Europe, 0 was an outcast, but in India and later in the Arab lands it flourished. When we last saw 0, it was simply a placeholder. It was a blank spot in the Babylonian system of numeration. 0 was useful, but was not truly a number on its own. It had no value. It only took its meaning from the digits to its left. The symbol for 0 literally meant nothing if it was by itself. In India, all this changed. In the 4th century BC, Alexander the Great marched with his Persian troops from Babylon to India. It was through this invasion that Indian mathematicians first learned about the Babylonian system of numbers and about 0. When Alexander died in 323 BC, his squabbling generals split his empire into pieces. Rome rose to power in the 2nd century BC and swallowed up Greece, but Rome's power did not extend as far east as Alexander's had. As a result, remote India was insulated from the rise of Christianity and the fall of Rome in the 4th and 5th centuries AD. India was also insulated from Aristotle's philosophy. Though Alexander had been tutored by Aristotle and no doubt introduced India to Aristotelian ideas, the Greek philosophy never took hold. Unlike Greece, India never had a fear of the infinite or of the void. Indeed, it embraced them. The void had an important place in the Hindu religion. Hinduism had started off as a polytheistic religion, a set of tales about warrior gods and battles, similar in many ways to the Greek mythos. However, over centuries before Alexander arrived, the gods began to merge together. While Hinduism retained its popular rituals and devotion to its pantheon, at its core Hinduism became monotheistic and introspective. All the gods became aspects of an all-encompassing god, Brahma. At about the same time that the Greeks were rising in the Western world, Hinduism was becoming less like the Western myths. The individual gods became less distinct and the religion became more and more mystical. The mysticism was patently Eastern. Like many Eastern religions, Hinduism was steeped in the symbolism of duality. Of course, this idea occasionally came up in the Western world, where it was promptly branded as heretical. One example is the Manichaean heresy, which saw the world as being under the influence of equal and opposite sources of good and evil. As with the yin and yang of the Far East and Zoroaster's dualism of good and evil in the Near East, creation and destruction were intermingled in Hinduism. The god Shiva was both creator and destroyer of the world and was depicted with a drum of creation in one hand and a flame of destruction in another. However, Shiva also represented nothingness. One aspect of the deity, Nishkala Shiva, was literally the Shiva without parts. He was the ultimate void, the supreme nothing, lifelessness incarnate. But out of the void the universe was born, as was the infinite. Unlike the Western universe, the Hindu cosmos was infinite in extent. Beyond our own universe were innumerable other universes. At the same time, though, the cosmos never truly abandoned its original emptiness. Nothingness was what the world came from, and to achieve nothingness again became the ultimate goal of mankind. In one story, Death tells a disciple about the soul. Concealed in the heart of all beings is the Atman, the spirit, the self, he says, smaller than the smallest atom, greater than the vast spaces. This Atman, which resides in everything, is part of the essence of the universe and is immortal. When a person dies, the Atman is released from the body and soon enters another being. The soul transmigrates and the person is reincarnated. The goal of the Hindu is to free the Atman entirely from the cycle of rebirth, to stop wandering from death to death. The way to achieve the ultimate liberation through lifelessness is to cease paying heed to the illusion of reality. The body, the house of the spirit, is under the power of pleasure and pain, explains a god. And if a man is ruled by his body, then this man can never be free. But once you are able to separate yourself from the whims of the flesh and embrace the silence and nothingness of your soul, you will be liberated. Your Atman will fly from the web of human desire and join the collective consciousness, the infinite soul that suffuses the universe at once, everywhere, and nowhere at the same time. It is infinity, and it is nothing. So India, as a society that actively explored the void and the infinite, accepted zero. Zero's reincarnation. In the earliest age of the gods, existence was born from non-existence, the Rig Veda. Indian mathematicians did more than simply accept zero. They transformed it, changing its role from mere placeholder to number. This reincarnation was what gave zero its power. The roots of Indian mathematics are hidden by time. An Indian text written the same year that Rome fell, 476 AD, shows the influence of Greek, Egyptian, and Babylonian mathematics brought by Alexander as he penetrated Indian lands. Like the Egyptians, the Indians had rope stretchers to survey fields and lay out temples. They also had a sophisticated system of astronomy. Like the Greeks, they tried to calculate the distance to the sun. That requires trigonometry. The Indian version was probably derived from the system that the Greeks had developed. Sometime around the 5th century AD, Indian mathematicians changed their style of numbering. They moved from a Greek-like system to a Babylonian-style one. An important difference between the new Indian number system and the Babylonian style was that Indian numbers were base 10 instead of base 60. Our numbers evolved from the symbols that the Indians used. By rights, they should be called Indian numerals rather than Arabic ones. Nobody knows when the Indians made the switch to a Babylonian-style place-value number system. The earliest reference to the Hindu numerals comes from a Syrian bishop who wrote, in 662, of how the Indians did calculations by means of 9 signs. 9, not 10. 0 was evidently not among them. But it's hard to tell for sure. It is fairly clear that the Hindu numerals were around before the bishop wrote about them. There is evidence that 0 appeared in some variants of the Indian system by that time, though the bishop hadn't heard about it. In any case, a symbol for 0, the placeholder in the base 10 numbering system, was certainly in use by the 9th century. By then, Indian mathematicians had already made a giant leap. The Indians had borrowed little of Greek geometry. They apparently didn't have a deep interest in the plane figures that the Greeks loved so much. They never worried about whether the diagonal of a square was rational or irrational, nor did they investigate the conic sections as Archimedes had. But they did learn how to play with numbers. The Indian system of numbering allowed them to use fancy tricks to add, subtract, multiply, and divide numbers without using an abacus to help them. Thanks to their place number system, they could add and subtract large numbers in roughly the same way we do today. With training, a person could multiply with Indian numerals faster than an abacist could tally. Contests between the abacists and the so-called algorists who used Indian numerals were the medieval equivalents of the Kasparov versus Deep Blue chess match. Like Deep Blue, the algorists would win in the end. Though the Indian number system was useful for everyday tasks like addition and multiplication, the true impact of Indian numbers was considerably deeper. Numbers had finally become distinct from geometry. Numbers were used to do more than merely measure objects. Unlike the Greeks, the Indians did not see squares in square numbers or the areas of rectangles when they multiplied two different values. Instead, they saw the interplay of numerals, numbers stripped of their geometric significance. This was the birth of what we now know as algebra. Though this mindset prevented the Indians from contributing much to geometry, it had another unexpected effect. It freed the Indians from the shortcomings of the Greek system of thought and their rejection of 0. Once numbers shed their geometric significance, mathematicians no longer had to worry about mathematical operations making geometric sense. You can't remove a 3-acre swath from a 2-acre field, but nothing prevents you from subtracting 3 from 2. Nowadays, we recognize that 2 minus 3 equals -1. However, this was not at all obvious to the ancients. Many times they solved equations only to get a negative result and concluded that their answer had no meaning. After all, if you are thinking in geometric terms, what is a negative area? It simply didn't make any sense to the Greeks. To the Indians, negative numbers made perfect sense. Indeed, it was in India and in China that negative numbers first appeared. Brahmagupta, an Indian mathematician of the 7th century, gave rules for dividing numbers by each other, and he included the negatives. Positive divided by positive or negative by negative is affirmative, he wrote. Positive divided by negative is negative. Negative divided by affirmative is negative. These are the rules that we recognize today. Divide two numbers and the answer is positive if the numbers' signs are the same. Just as 2 minus 3 was now a number, so was 2 minus 2. It was 0. Not just a mere placeholder 0 that represents an empty space on the abacus, but 0 the number. It had a specific value, a fixed place on the number line. Since 0 was equal to 2 minus 2, then it had to be placed between 1, 2 minus 1, and negative 1, 2 minus 3. Nothing else made sense. No longer could 0 sit to the right of 9 just as it does on the top of the computer keyboard. 0 had a position in the number line that was all its own. A number line without 0 could no more exist than a number system without 2. 0 had finally arrived. However, even the Indians thought that 0 was a pretty bizarre number, for all the usual reasons. After all, 0 multiplied by anything is 0. It sucks everything into itself, and when you divide with it, all hell breaks loose. Brahmagupta tried to figure out what 0 divided by 0 and 1 divided by 0 were, and failed. Cipher divided by cipher is naught, he wrote. Positive or negative divided by cipher is a fraction with that for a denominator. In other words, he thought 0 divided by 0 was 0. He was wrong, as we will hear. And he thought that 1 divided by 0 was, well, we don't really know because he doesn't make a whole lot of sense. Basically, he was waving his hands and hoping that the problem would go away. Brahmagupta's mistake did not last for very long. In time, the Indians realized that 1 divided by 0 was infinite. This fraction, of which the denominator is a cipher, is termed an infinite quantity, writes Bhaskara, a 12th century Indian mathematician, who tells of what happens when you add a number to 1 divided by 0. There is no alteration, though many be inserted or extracted, as no change takes place in the infinite and immutable God. God was found in infinity and in 0. The Arab numeral. Does man forget that we created him out of the void? The Quran. By the 7th century, the West had withered with the fall of Rome, but the East was flourishing. India's growth was eclipsed by another Eastern civilization. As the star of the West sank below the horizon, another star was rising, Islam. Islam would take 0 from India, and the West would eventually take it from Islam. 0's rise to preeminence had to begin in the East. One evening in 610 A.D., Muhammad, a 30-year-old native of Mecca, fell into a trance on Mount Hira. According to legend, the angel Gabriel told him, "Recite." Muhammad did, and his divine revelations started a wildfire. A decade after Muhammad's death in 632, his followers had captured Egypt, Syria, Mesopotamia, and Persia. Jerusalem, the holy city of the Jews and the Christians, had fallen. By 700, Islam stretched as far as the Indus River in the east and Algiers in the west. In 711, the Muslims captured Spain, and they advanced as far as France. In the east, they defeated the Chinese in 751. Their empire stretched farther than even Alexander could have imagined. Along the way to China, the Muslims conquered India, and there the Arabs learned about Indian numerals. The Muslims were quick to absorb the wisdom of the peoples that they conquered. Scholars started translating texts into Arabic, and in the 9th century, Caliph al-Mamun founded a great library, the House of Wisdom, at Baghdad. It was to become the center of learning in the Eastern world, and one of its first scholars was the mathematician Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi wrote several important books like Algebra wal Muqabala, a treatise on how to solve elementary equations. The Algebra in the title, which means something like completion, gave us the term algebra. He also wrote a book about the Hindu numeral system, which allowed the new style of numbers to spread quickly through the Arab world, along with algorithms, the tricks for multiplying and dividing Hindu numerals quickly. In fact, the word algorithm was a corruption of al-Khwarizmi's name. Though the Arabs took the notation from India, the rest of the world would dub the new system Arabic numerals. The very word 0 smacks of its Hindu and Arabic roots. When the Arabs adopted Hindu-Arabic numerals, they also adopted 0. The Indian name for 0 was sunya, meaning empty, which the Arabs turned into sifr. When some Western scholars describe the new number to their colleagues, they turn cipher into a Latin-sounding word yielding zephyrus, which is the root of our word zero. Other Western mathematicians didn't change the word so heavily and called zero cifra, which became cipher. Zero was so important to the new set of numbers that people started calling all numbers ciphers, which gave the French their term chiffre, digit. However, when Al-Khwarizmi was writing about the Hindu system of numbers, the West was still far from adopting zero. Even the Muslim world, with its Eastern traditions, was heavily contaminated by the teachings of Aristotle, thanks to the conquests of Alexander the Great. However, as Indian mathematicians had made quite clear, zero was the embodiment of the void. Thus, if the Muslims were to accept zero, they had to reject Aristotle. That was precisely what they did. A 12th century Jewish scholar, Moses Maimonides, described the Kalam, the beliefs of Islamic theologians, with horror. He noted that instead of accepting Aristotle's proof of God, the Muslim scholars turned to the atomists, Aristotle's old rivals, whose doctrine, though out of favor, managed to survive the ravages of time. The atomists, remember, held that matter was composed of individual particles called atoms, and if these particles were able to move about, there had to be a vacuum between them. Otherwise, the atoms would be bumping into one another, unable to get out of one another's way. The Muslims seized upon the atomists' ideas. After all, now that zero was around, the void was again a respectable idea. Aristotle hated the void. The atomists required it. The Bible told of the creation from the void, while the Greek doctrine rejected the possibility. The Christians, cowed by the power of Greek philosophy, chose Aristotle over their Bible. The Muslims, on the other hand, made the opposite choice. I am that I am. Nothing. Nothingness is being, and being nothingness. Our limited mind cannot grasp or fathom this, for it joins infinity. Azrael of Gerona. Zero was an emblem of the new teachings, of the rejection of Aristotle and the acceptance of the void and the infinite. As Islam spread, zero diffused throughout the Muslim-controlled world, everywhere conflicting with Aristotle's doctrine. Islamic scholars battled back and forth, and in the 11th century a Muslim philosopher, Abu Hamid al-Ghazali, declared that clinging to Aristotelian doctrine should be punishable by death. The debate ended shortly thereafter. It's no surprise that zero caused such discord. The Muslims, with their Semitic Eastern background, believed that God created the universe out of the void, a doctrine that could never be accepted where people shared Aristotle's hatred of the void and of the infinite. As zero spread through the Arab lands, the Muslims embraced it and rejected Aristotle. The Jews were the next in line. For millennia, the center of Jewish life had been planted firmly in the Middle East. But in the 10th century, an opportunity for Jews arose in Spain. Caliph Abd al-Rahman III had a Jewish minister who imported a number of intellectuals from Babylonia. Soon a large Jewish community flourished in Islamic Spain. Early medieval Jews, both in Spain and in Babylon, were wed firmly to Aristotle's doctrines. Like their Christian counterparts, they refused to believe in the infinite or the void. However, just as Aristotelian philosophy conflicted with Islamic teachings, it conflicted with Jewish theology. This is what drove Maimonides, the 12th century rabbi, to write a tome to reconcile the Semitic, Eastern Bible with the Greek Western philosophy that permeated Europe. From Aristotle, Maimonides had learned to prove God's existence by denying the infinite. Reproducing the Greek arguments faithfully, Maimonides contended that the hollow spheres that twirled about the earth had to be moved by something, say, the next sphere out. But the next sphere out had to be moved by something, the next sphere in line. However, since there cannot be an infinite number of spheres, because infinity was impossible, something had to be moving the outermost sphere. That was the prime mover, God. Maimonides' argument was indeed a proof of God's existence, something incredibly valuable in any theology. Yet at the same time, the Bible and other Semitic traditions were full of the ideas of the infinite and the void, ideas that the Muslims already embraced. Just like St. Augustine 800 years earlier, Maimonides tried to reshape the Semitic Bible to fit into Greek doctrine that had an unreasonable fear of the void. But unlike the early Christians who had freed themselves to interpret parts of the Old Testament as metaphor, Maimonides was unwilling to Hellenize his religion completely. Rabbinic tradition compelled him to accept the biblical account of the universe's creation from the void. This, in turn, meant contradicting Aristotle. Maimonides argued that there were flaws in Aristotle's proof that the universe had always existed. After all, it conflicted with the scriptures. This, of course, meant that Aristotle had to go. Maimonides stated that the act of creation came from nothing. It was creatio ex nihilo, despite the Aristotelian ban on the vacuum. With that stroke, the void moved from sacrilege to holiness. For the Jews, the years after Maimonides' death became the era of nothing. In the 13th century, a new doctrine spread, Kabbalism, or Jewish mysticism. One centerpiece of Kabbalistic thought is gematria, the search for coded messages within the text of the Bible. Like the Greeks, the Hebrews used letters from their alphabet to represent numbers, so every word had a numerical value. This could be used to interpret the hidden meaning of words. For instance, Gulf War participants might have noticed that Saddam has the following value: Samek 60 plus Aleph 1 plus Daled 4 plus Aleph 1 plus Mem 600 equals 666, a number that Christians associate with the evil beast that appears during the apocalypse. Whether Saddam has 2 Daleds or 1 would make no difference to the Kabbalists, who often used alternate spellings of words to make sums come out right. Kabbalists thought that words and phrases with the same numerical value were mystically linked. For instance, Genesis chapter 49 verse 10 states, "The scepter shall not depart from Judah until Shiloh come." The Hebrew phrase for "until Shiloh come" has a value of 358, exactly the same for the Hebrew word Mashiach, Messiah. Hence the passage presages the coming of the Messiah. Certain numbers were holy or evil according to the Kabbalists, and they looked through the Bible for these numbers and for hidden messages found by scanning through it in various ways. A recent bestseller, The Bible Code, purported to find prophecies by this method. The Kabbalah was much more than number crunching. It was a tradition so mystical that some scholars say that it bears a striking resemblance to Hinduism. For instance, the Kabbalah seized upon the idea of the dual nature of God. The Hebrew term Ein Sof, which meant infinite, represented the creator aspect of God, the part of the deity that made the universe and that permeates every corner of the cosmos. But at the same time, it had a different name, Ayin, or nothing. The infinite and the void go hand in hand and are both part of the divine creator. Better yet, the term ayin is an anagram of and has the same numerical value as the word ani, the Hebrew I. It could scarcely be clearer. God was saying in code, "I am nothing," and at the same time, infinity. As the Jews pitted their Western sensibilities against their Eastern Bible, the same battle was underway in the Christian world. Even as the Christians battled the Muslims during Charlemagne's reign in the 9th century and during the Crusades in the 11th, 12th, and 13th centuries, warrior monks, scholars, and traders began to bring Islamic ideas back to the West. Monks discovered that the astrolabe, an Arabic invention, was a handy tool for keeping track of time in the evening, helping them keep their prayers on schedule. The astrolabes were often inscribed with Arabic numerals. The new numbers didn't catch on, even though a 10th century pope, Sylvester II, was an admirer of them. He probably learned about the numerals during a visit to Spain and brought them back with him when he returned to Italy. But the version he learned did not have a 0, and the system would have been even less popular if it had. Aristotle still had a firm grip on the church, and its finest thinkers still rejected the infinitely large, the infinitely small, and the void. Even as the Crusades drew to a close in the 13th century, St. Thomas Aquinas declared that God could not make something that was infinite any more than he could make a scholarly horse. But that implied that God was not omnipotent, a forbidden thought in Christian theology. In 1277, the Bishop of Paris, Etienne Tempier, called an assembly of scholars to discuss Aristotelianism, or rather, to attack it. Tempier abolished many Aristotelian doctrines that contradicted God's omnipotence, such as, God cannot move the heavens in a straight line because that would leave behind a vacuum. The rotating spheres cause no problem because they still occupy the same space. It is only when you move the spheres in a line that you are forced to have a space to move the heavens into, and you are forced to have a space behind them after they move. God could make a vacuum if he wanted. All of a sudden, the void was allowed because an omnipotent deity doesn't need to follow Aristotle's rules if he doesn't want to. Tempier's pronouncements were not the final blow to Aristotelian philosophy, but they certainly signaled that the foundations were crumbling. The Church would cling to Aristotle for a few more centuries, but the fall of Aristotle and the rise of the void and the infinite were clearly beginning. It was a propitious time for Zeno to arrive in the West. In the mid-12th century, the first adaptations of Al-Khwarizmi's Algebra were working their way through Spain, England, and the rest of Europe. Zeno was on the way, and just as the Church was breaking the shackles of Aristotelianism, it arrived. Zeno's triumph. A profound and important idea which appears so simple to us now that we ignore its true merit. But its very simplicity and the great ease which it lent to all computations put our arithmetic in the first rank of useful inventions. Pierre-Simon Laplace. Christianity initially rejected Zeno, but trade would soon demand it. The man who reintroduced Zeno to the West was Leonardo of Pisa. The son of an Italian trader, he traveled to northern Africa. There, the young man, better known as Fibonacci, learned mathematics from the Muslims and soon became a good mathematician in his own right. Fibonacci is best remembered for a silly little problem he posed in his book Liber Abaci, which was published in 1202. Imagine that a farmer has a pair of baby rabbits. Babies take 2 months to reach maturity, and from then on they produce another pair of rabbits at the beginning of every month. As these rabbits mature and reproduce, and those rabbits mature and reproduce, and so on, how many pairs of rabbits do you have during any given month? Well, during the first month you have 1 pair of rabbits, and since they haven't matured, they can't reproduce. During the second month you still have only 1 pair. But at the beginning of the third month, the first pair reproduces. You've got 2 pairs. At the beginning of the fourth month, the first pair reproduces again, but the second pair is not mature enough, 3 pairs. The next month, the first pair reproduces, the second pair reproduces, since it has reached maturity, but the third pair is too young. That is 2 additional pairs of rabbits, 5 in all. The number of rabbits goes as follows: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so forth and so on. The number of rabbits you have in any given month is the sum of the rabbits that you had in each of the 2 previous months. Mathematicians instantly realize the importance of this series. Take any term and divide it by its previous term. For instance, 8 divided by 5 equals 1.6, 13 divided by 8 equals 1.625, 21 divided by 13 equals 1.61538. These ratios approach a particularly interesting number, the golden ratio, which is 1.61803. Pythagoras had noticed that nature seemed to be governed by the golden ratio. Fibonacci discovered the sequence that is responsible. The size of the chambers of the nautilus and the number of clockwise grooves to counterclockwise grooves in the pineapple are governed by this sequence. This is why their ratios approach the golden ratio. Though this sequence is the source of Fibonacci's fame, Fibonacci's Liber Abaci had a much more important purpose than animal husbandry. Fibonacci had learned his mathematics from the Muslims, so he knew about Arabic numerals, including 0. He included the new system in Liber Abaci, finally introducing Europe to zero. The book showed how useful Arabic numerals were for doing complex calculations, and the Italian merchants and bankers quickly seized upon the new system, zero included. Before Arabic numerals came around, money counters had to make do with an abacus or a counting board. The Germans called the counting board a Rechenbank, which is why we call moneylenders banks. At that time, banking methods were primitive. Not only did they use counting boards, they used tally sticks to record loans. A money value was written along the stick's side, and it was split in two. The lender kept the biggest piece, the stock. After all, he was the stockholder. Italian merchants loved the Arabic numbers. They allowed the bankers to get rid of their counting boards. However, while businessmen saw their usefulness, the local governments hated them. In 1299, Florence banned Arabic numerals. The ostensible reason was that the numbers were easily changed and falsified. A 0 could be turned into a 6 with a simple flourish of a pen, for instance. But the advantages of 0 and the other Arabic numerals were not so easily dispensed with. Italian merchants continued to use them, and even used them to send encrypted messages, which is how the word cipher came to mean secret code. In the end, the governments had to relent in the face of commercial pressure. The Arabic notation was allowed into Italy and soon spread throughout Europe. 0 had arrived, as had the void. The Aristotelian wall was crumbling thanks to the influence of the Muslims and the Hindus, and by the 1400s even the staunchest European supporters of Aristotelianism had their doubts. Thomas Bradwardine, who was to become Archbishop of Canterbury, tried to disprove atomism, Aristotle's old nemesis. At the same time, he wondered whether his own logic was faulty, since he based his arguments on geometry, whose infinitely divisible lines automatically reject atomism. However, the battle against Aristotle was far from over. If Aristotle were to fall, the proof of God, a bulwark of the Church, was no longer valid. A new proof was needed. Worse yet, if the universe were infinite, then there could be no center. How could Earth then be the center of the universe? The answer was found in 0. Chapter 4. The Infinite God of Nothing, the Theology of 0. And new philosophy calls all in doubt. The element of fire is quite put out. The sun is lost, and the earth, and no man's wit can well direct him where to look for it. 'Tis all in pieces, all coherence gone, all just supply and all relation, prince, subject, father, son, are things forgot. John Donne, An Anatomy of the World. 0 and infinity were at the very center of the Renaissance. As Europe slowly awakened from the Dark Ages, the void and the infinite, nothing and everything, would destroy the Aristotelian foundation of the Church and open the way to the scientific revolution. At first, the papacy was blind to the danger. High-ranking clergymen experimented with the dangerous ideas of the void and the infinite, even though the ideas struck at the core of the ancient Greek philosophy that the Church cherished so much. 0 appeared in the middle of every Renaissance painting, and a cardinal declared that the universe was infinite, boundless. However, the brief love affair with 0 and infinity was not to last. When the Church was threatened, it retreated into its old philosophy, turning back toward the Aristotelian doctrine that had supported it for so many years. It was too late. 0 had taken hold in the West, and despite the papacy's objections, it was too strong to be exiled once more. Aristotle fell to the infinite and to the void, and so did the proof of God's existence. Only one option remained for the Church: accept 0 and infinity. Indeed, to the devout, God could be found hidden within the void and the infinite. The nutshell cracked. O God, I could be bounded in a nutshell and count myself a king of infinite space were it not that I have bad dreams. William Shakespeare, Hamlet. At the beginning of the Renaissance, it was not obvious that zero would pose a threat to the Church. It was an artistic tool, an infinite nothing that ushered in the great Renaissance in the visual arts. Before the 15th century, paintings and drawings were largely flat and lifeless. The images in them were distorted and two-dimensional. Gigantic, flat knights peered out of tiny, misshapen castles. Even the best artists could not draw a realistic scene. They did not know how to use the power of zero. It was an Italian architect, Filippo Brunelleschi, who first demonstrated the power of an infinite zero. He created a realistic painting by using a vanishing point. By definition, a point is a zero, thanks to the concept of dimension. In everyday life, you deal with three-dimensional objects. Actually, Einstein revealed that our world is four-dimensional, as we shall hear in a later chapter. The clock on your dresser, the cup of coffee you drink in the morning, the book you're listening to right now, all these are three-dimensional objects. Now imagine that a gigantic hand comes down and squashes the book flat. Instead of being a three-dimensional object, the book is now a flat, floppy rectangle. It has lost a dimension. It has length and width, but no height. It is now two-dimensional. Now imagine that the book turned sideways is crushed once again by the giant hand. The book is no longer a rectangle. It is a line. Again, it has lost a dimension. It has neither height nor width, but it has length. It is a one-dimensional object. You can take away even this single dimension. Squashed along its length, the line becomes a point, an infinitesimal nothing with no length, no width, and no height. A point is a zero-dimensional object. In 1425, Brunelleschi placed just such a point in the center of a drawing of a famous Florentine building, the baptistry. This zero-dimensional object, the vanishing point, is an infinitesimal dot on the canvas that represents a spot infinitely far away from the viewer. As objects recede into the distance in the painting, they get closer and closer to the vanishing point, getting more compressed as they get farther away from the viewer. Everything sufficiently distant, people, trees, buildings, is squashed into a zero-dimensional point and disappears. The zero in the center of the painting contains an infinity of space. This apparently contradictory object turned Brunelleschi's drawing, almost magically, into such a good likeness of the three-dimensional baptistry building that it was indistinguishable from the real thing. Indeed, when Brunelleschi used a mirror to compare the painting and the building, the reflected image matched the building's geometry exactly. The vanishing point turned a two-dimensional drawing into a perfect simulation of a three-dimensional building. It is no coincidence that zero and infinity are linked in the vanishing point. Just as multiplying by zero causes the number line to collapse into a point, the vanishing point has caused most of the universe to sit in a tiny dot. This is a singularity, a concept that became very important later in the history of science. But at this early stage, mathematicians knew little more than the artists about the properties of zero. In fact, in the 15th century, artists were amateur mathematicians. Leonardo da Vinci wrote a guide to drawing in perspective. Another of his books about painting warns, "Let no one who is not a mathematician read my works." These mathematician artists perfected the technique of perspective and could soon depict arbitrary objects in three dimensions. No longer would artists be restricted to flat likenesses. Zero had transformed the art world. Zero was quite literally at the center of Brunelleschi's painting. The Church, too, dabbled with zero and the infinite, though church doctrine was still dependent on Aristotelian ideas. A contemporary of Brunelleschi, a German cardinal named Nicholas of Cusa, looked at infinity and promptly declared, "Terra non est centra mundi." The earth is not the center of the universe. The Church didn't yet realize how dangerous, how revolutionary that idea was. One of the old declarations of the medieval Aristotelian doctrine, as strong as the ban on the vacuum, was the statement that Earth was unique. It was at the universe's very center. Earth's special position at the center of the universe made it the only world capable of containing life, as Aristotle held that all objects sought out their proper place. Heavy objects like rocks or people belonged on the ground. Light objects like air belonged in the heavens. Not only did this imply that the planets in the heavens were made of light, airy stuff, but it also meant that any people in the heavens would naturally fall to earth. Thus, creatures could only inhabit the nut meat in the center of the nutshell cosmos. Having other planets with life on them was as silly as having a sphere with two centers. When Dampier declared that the omnipotent God could create a vacuum if he so desired, Dampier insisted that God could break any Aristotelian law. God could create life on other worlds if he wished. There could be thousands of other Earths, each teeming with creatures. It was certainly within God's power, whether Aristotle agrees or not. Nicholas of Cusa was bold enough to say that God must have done so. The regions of the other stars are similar to this, he said, for we believe that none of them is deprived of inhabitants. The sky was littered with an infinite number of stars. The planets glowed in the heavens. The moon and the sun each glowed with light. Why couldn't the stars in the sky be planets or moons or suns on their own? Maybe Earth glows brightly in their heavens just as they glow in ours. Nicholas was sure that God had indeed created an infinite number of other worlds. Earth was no longer at the center of the universe. Yet Nicholas was not declared a heretic, and the Church didn't react to the new idea. In the meantime, another Nicholas turned Cusa's philosophy into a scientific theory. Nicholas Copernicus showed that Earth is not the center of the universe. It revolves around the sun. A Polish monk and a physician, Copernicus learned mathematics so he could cast astrological tables, the better to cure his patients with. Along the way, Copernicus's dabblings with the planets and stars showed him how complicated the old Greek system of tracking the planets was. Ptolemy's clockwork heavens, with Earth at the center, were extremely accurate. However, they were terribly complex. Planets course around the sky throughout the year, but every so often they stop, move backward, and then shoot ahead once more. To account for the planet's bizarre behavior, Ptolemy added epicycles to his planetary clockwork. Little circles within circles could explain the backward or retrograde motion of the planets. The power of Copernicus's idea was in its simplicity. Instead of placing Earth at the center of the universe filled with epicycle-filled clockworks, Copernicus imagined that the sun was at the center instead, and the planets moved in simple circles. Planets would seem to zoom backward as Earth overtook them. No epicycles were needed. Though Copernicus's system didn't agree with the data completely, the circular orbits were wrong, though the heliocentric idea was correct, it was much simpler than the Ptolemaic system. The Earth revolved around the sun. Terra non est centra mundi. Nicholas of Cusa and Nicholas Copernicus cracked open the nutshell universe of Aristotle and Ptolemy. No longer was the Earth comfortably ensconced in the center of the universe. There was no shell containing the cosmos. The universe went on into infinity, dotted with innumerable worlds, each inhabited by mysterious creatures. But how could Rome claim to be the seat of the one true church if its authority could not extend to other solar systems? Were there other popes on other planets? It was a grim prospect for the Catholic Church, especially since it was beginning to have trouble with its subjects on even its own world. Copernicus published his magnum opus on his deathbed in 1543, just before the Church started clamping down on new ideas. Copernicus's book, De Revolutionibus, was even dedicated to Pope Paul III. However, the Church was under attack. As a result, the new ideas, the questioning of Aristotle, could no longer be tolerated. The attack on the Church began in earnest in 1517, when a constipated German monk nailed a list of complaints to the door of the church in Wittenberg. Luther's constipation was legendary. Some scholars believe that his great revelation about faith came to him when he was sitting on the privy. Luther's release from the constricting bondage of fear corresponded to the release of his bowels, notes one text, commenting on this theory. This was the beginning of the Reformation. Intellectuals everywhere began to reject the authority of the Pope. By the 1530s, in a quest to ensure an orderly succession to the throne, Henry VIII had spurned the authority of the Pope, declaring himself the head of the English clergy. The Catholic Church had to strike back. Though it had been experimenting with other philosophies for several centuries, when threatened with schism it turned orthodox once again. It fell back upon its orthodox teachings, the Aristotelian-based philosophies of scholars like St. Augustine and Boethius, as well as Aristotle's proof of God. No longer could cardinals and clerics question the ancient doctrines. Zero was a heretic. The nutshell universe had to be accepted. The void and the infinite must be rejected. One of the key groups that spread these teachings was founded in the 1530s, the Jesuit order, a collection of highly trained intellectuals well suited to attack Protestantism. The Church had other tools to fight heresy as well. The Spanish Inquisition started burning Protestants in 1543, the same year Copernicus died, and the same year that Pope Paul III issued the Index of Forbidden Books. The Counter-reformation was the Church's attempt to rebuild the old order by crushing the new ideas. An idea embraced by Bishop Etienne Tempier in the 13th century and Cardinal Nicholas of Cusa in the 15th century could mean a death sentence in the 16th century. This is what happened to the unfortunate Giordano Bruno. In the 1580s, Bruno, a former Dominican cleric, published On the Infinite Universe and Worlds, where he suggested, like Nicholas of Cusa, that the earth was not the center of the universe and that there were infinite worlds like our own. In 1600, he was burned at the stake. In 1616, the famous Galileo Galilei, another Copernican, was ordered by the Church to cease his scientific investigations. The same year, Copernicus's De Revolutionibus was placed on the Index of Forbidden Books. An attack on Aristotle was considered an attack upon the Church. Despite the Church's Counter-reformation, the new philosophy wasn't easily destroyed. It got stronger as time went on, thanks to the investigations of Copernicus's successors. In the beginning of the 17th century, another astrologer monk, Johannes Kepler, refined Copernicus's theory, making it even more accurate than the Ptolemaic system. Instead of moving in circles, the planets, including Earth, moved in ellipses around the Sun. This explained the motion of the planets in the heavens with incredible accuracy. No longer could astronomers object that the heliocentric system was inferior to the geocentric one. Kepler's model was simpler than Ptolemy's, and it was more accurate. Despite the Church's objections, Kepler's heliocentric system would prevail eventually, because Kepler was right and Aristotle was wrong. The Church attempted to patch the holes in the old way of thought, but Aristotle, the geocentric world, and the feudal way of life were all mortally wounded. Everything that philosophers had taken for granted for millennia was called into doubt. The Aristotelian system could not be trusted, and at the same time it could not be rejected. What, then, could be taken for granted? Literally, nothing. Zero and the void. I am, in a sense, something intermediate between God and naught. René Descartes, Discourse on Method. Zero and the infinite were at the very center of the philosophical war taking place during the 16th and 17th centuries. The void had weakened Aristotle's philosophy, and the idea of an infinitely large cosmos helped shatter the nutshell universe. The earth could not be at the center of God's creation. As the papacy lost its hold on its flock, the Catholic Church tried to reject zero and the void more strongly than ever, yet zero had already taken root. Even the most devout intellectuals, the Jesuits, were torn between the old Aristotelian ways and the new philosophies that included zero and the void, infinity and the infinite. René Descartes was trained as a Jesuit, and he, too, was torn between the old and the new. He rejected the void, but put it at the center of his world. Born in 1596 in the middle of France, Descartes would bring zero to the center of the number line, and he would seek a proof of God in the void and the infinite. Yet Descartes could not reject Aristotle entirely. He was so afraid of the void that he denied its existence. Like Pythagoras, Descartes was a mathematician-philosopher. Perhaps his most lasting legacy was a mathematical invention, what we now call Cartesian coordinates. Anyone who has taken geometry in high school has seen them. They are the sets of numbers in parentheses that represent a point in space. For instance, the symbol 4, 2 represents a point 4 units to the right and 2 units upward. But to the right and upward of what? The origin, 0. Descartes realized that he could not start his two reference lines or axes with the number 1. That would lead to an error like the one Bede encountered when revamping the calendar. However, unlike Bede, he lived in a Europe where Arabic numerals were common, so he started counting with 0. At the very center of the coordinate system, where the two axes cross, sits a 0. The origin, the point 0, 0, is the foundation of the Cartesian system of coordinates. Descartes' notion was slightly different from what we use today. For one thing, he didn't extend his coordinate system to the negative numbers, though his colleagues would soon do that for him. Descartes quickly realized how powerful his coordinate system was. He used it to turn figures and shapes into equations and numbers. With Cartesian coordinates, every geometric object, squares, triangles, wavy lines, could be represented by an equation, a mathematical relationship. For example, a circle at the origin can be represented by the set of all points where x squared plus y squared minus 1 equals 0. A parabola might be y minus x squared equals 0. Descartes unified numbers and shapes. No longer were the Western art of geometry and the Eastern art of algebra separate domains. They were the same thing, as every shape could simply be expressed as an equation of the form function of x, y equals 0. 0 was at the center of the coordinate system, and 0 was implicit in each geometric shape. To Descartes, 0 was also implicit in God's domain, as was the infinite. Since the old Aristotelian doctrine was crumbling, Descartes, true to his Jesuit training, tried to use naught and infinity to replace the old proof of God's existence. Like the ancients, Descartes assumed that nothing, not even knowledge, can be created out of nothing, which means that all ideas, all philosophies, all notions, all future discoveries already exist in people's brains when they are born. Learning is just the process of uncovering that previously imprinted code of laws about the workings of the universe. Since we have a concept of an infinite perfect being in our minds, Descartes then argued that this infinite and perfect being, God, must exist. All other beings are less than divine. They are finite. They all lie somewhere between God and naught. They are a combination of infinity and 0. Though 0 appeared and reappeared throughout Descartes' philosophy, Descartes insisted unto his death that the void, the ultimate 0, does not exist. A child of the Counter-reformation, Descartes learned about Aristotle at the very moment when the Church was relying upon his principles the most. As a result, Descartes, indoctrinated with the Aristotelian philosophy, denied the existence of the vacuum. It was a difficult position to take. Descartes was certainly mindful of the metaphysical problems of rejecting the vacuum entirely. Later in his life, he wrote about atoms and the vacuum. About these things that involve a contradiction, it can absolutely be said that they cannot happen. However, one shouldn't deny that they can be done by God, namely, if he were to change the laws of nature. Yet, like the medieval scholars before him, Descartes believed that nothing truly moved in a straight line, for that would leave a vacuum behind it. Instead, everything in the universe moved in a circular path. It was a truly Aristotelian way of thinking, yet the void would soon unseat Aristotle once and for all. Even today, children are taught nature abhors a vacuum, while the teachers don't really understand where that phrase came from. It was an extension of the Aristotelian philosophy, vacuums don't exist. If someone would attempt to create a vacuum, nature would do anything in its power to prevent it from happening. It was Galileo's secretary, Evangelista Torricelli, who proved that this wasn't true by creating the first vacuum. In Italy, workmen used a kind of pump which worked more or less like a giant syringe to raise water out of wells and canals. This pump had a piston that fitted snugly in a tube. The bottom of the tube was placed in the water, so when the piston was raised, the water level followed the plunger upward. Galileo heard from a worker that these pumps had a problem. They could only lift water about 33 feet. After that, the plunger kept on going upward, yet the water level stayed the same. It was a curious phenomenon, and Galileo passed the problem on to his assistant Torricelli, who started doing experiments, trying to figure out the reason for the pump's curious limitation. In 1643, Torricelli took a long tube that was closed at one end and filled it with mercury. He upended it, placing the open end in a dish also filled with mercury. Now, if Torricelli had upended the tube in air, everyone would expect the mercury to run out because it would quickly be replaced by air. No vacuum would be created. But when it was upended in a dish of mercury, there was no air to replace the mercury in the tube. If nature truly abhorred a vacuum so much, the mercury in the tube would have to stay put so as not to create a void. The mercury didn't stay put. It sank downward a bit, leaving a space at the top. What was in that space? Nothing. It was the first time in history anyone had created a sustained vacuum. No matter the dimensions of the tube that Torricelli used, the mercury would sink down until its highest point was about 30 inches above the dish, or, looking at it another way, mercury could only rise 30 inches to combat the vacuum above it. Nature only abhorred a vacuum as far as 30 inches. It would take an anti-Descartes to explain why. In 1623, Descartes was 27, and Blaise Pascal, who would become Descartes' opponent, was 0 years old. Pascal's father, Etienne, was an accomplished scientist and mathematician. The young Blaise was a genius equal to his father. As a young man, Blaise invented a mechanical calculating machine named the Pascaline, which is similar to some of the mechanical calculators that engineers used before the invention of the electronic calculator. When Blaise was 23, his father slipped on a patch of ice and broke his thigh. He was cared for by a group of Jansenists, Catholics who belonged to a sect based largely on a hatred of the Jesuit order. Soon, the entire Pascal family was won over, and Blaise became an anti-Jesuit, a counter-reformationist. Pascal's newfound religion was not a comfortable fit for the young scientist. Bishop Jansen, the founder of the sect, had declared that science was sinful. Curiosity about the natural world was akin to lust. Luckily, Pascal's lust was greater than his religious fervor for a time, because he would use science to unravel the secret of the vacuum. About the time of Pascal's conversion, a friend of Etienne's, a military engineer, came to visit and repeated Torricelli's experiment for the Pascals. Blaise Pascal was enthralled and started performing experiments of his own, using water, wine, and other fluids. The result was new experiments concerning the vacuum, published in 1647. This work left the main question unanswered: why would mercury rise only 30 inches and water only 33 feet? The theories of the time tried to save a fragment of Aristotle's philosophy by declaring that nature's horror of the vacuum was limited. It could only destroy a finite amount of vacuum. Pascal had a different idea. In the fall of 1648, acting on a hunch, Pascal sent his brother-in-law up a mountain with a mercury-filled tube. On top of the mountain, the mercury rose considerably less than 30 inches. Was nature somehow perturbed less by a vacuum on top of a mountain than by a vacuum in the valley? To Pascal, this seemingly bizarre behavior proved that it wasn't an abhorrence of the vacuum that drove the mercury up the tube. It was the weight of the atmospheric pressure down on the mercury exposed in the pan that makes the fluid shoot up the column. The atmospheric pressure bearing down on a pan of liquid, be it mercury, water, or wine, will make the level inside the tube rise, just as gently squeezing the bottom of a toothpaste tube will make the contents squirt out the top. Since the atmosphere cannot push infinitely hard, it can only drive mercury about 30 inches up the tube, and at the top of the mountain there is less atmosphere pushing down, so the air can't even push the mercury as high as 30 inches. It is a subtle point. Vacuums don't suck. The atmosphere pushes. But Pascal's simple experiment demolished Aristotle's assertion that nature abhors a vacuum. Pascal wrote, "But until now one could find no one who took this view that nature has no repugnance for the vacuum, that it makes no effort to avoid it, and that it admits vacuum without difficulty and without resistance." Aristotle was defeated, and scientists stopped fearing the void and began to study it. It was also in Zero and the Infinite that Pascal, the devout Jansenist, sought to prove God's existence. He did it in a very profane way. The Divine Wager. What is man in nature? Nothing in relation to the infinite, everything in relation to nothing, a mean between nothing and everything. Blaise Pascal, Pensée. Pascal was a mathematician as well as a scientist. In science, Pascal investigated the vacuum, the nature of the void. In mathematics, Pascal helped invent a whole new branch of the field, probability theory. When Pascal combined probability theory with zero and with infinity, he found God. Probability theory was invented to help rich aristocrats win more money with their gambling. Pascal's theory was extremely successful, but his mathematical career was not to last. On November 23, 1654, Pascal had an intense spiritual experience. Perhaps it was the old Jansenist anti-science creed that was building up in him, but for whatever the reason, Pascal's newfound devotion led him to abandon mathematics and science altogether. He made an exception for a brief time 4 years later, when he was unable to sleep owing to illness. He started doing mathematics, and the pain eased. Pascal believed that this was a sign that God was not displeased with his studies. He became a theologian, but he could not escape his profane past. Even when it came to arguing about God's existence, he kept coming back to those crass, gambling Frenchmen. Pascal argued that it was best to believe in God because it was a good bet, literally. Just as he analyzed the value or expectation of a gamble, Pascal analyzed the value of accepting Christ as Savior. Thanks to the mathematics of zero and infinity, Pascal concluded that one should assume that God exists. Before considering the wager itself, it is easy to analyze a slightly different game. Imagine that there are two envelopes marked A and B. Before you are shown the envelopes, a flip of the coin determined which envelope has money in it. If the coin toss was a heads, A has a brand new $100 bill inside. If the coin came up tails, B has the money. But this time, it's $1 million. Which envelope should you choose? B, obviously. Its value is much greater. It is not difficult to show that using a tool from probability theory called an expectation, which is a measure of how much we expect each envelope to be worth. Envelope A might or might not have a $100 bill in it. It has some value because it might have money in it, but it isn't worth as much as $100 because you're not absolutely sure that it contains anything. In fact, a mathematician would add up all of the possible contents of envelope A and then multiply by the probability of each outcome. 1/2 chance of winning $0. 1/2 times $0 equals $0. 1/2 chance of winning $100. 1/2 times $100 equals $50. Expectation equals $50. The mathematician would conclude that the expected value of the envelope is $50. At the same time, the expected value of envelope B is 1/2 chance of winning $0. 1/2 times $0 equals $0. 1/2 chance of winning $1 million. 1/2 times $1 million equals $500,000. Expectation equals $500,000. So the expected value of B is $500,000, 10,000 times as much as the expected value of envelope A. Clearly, if you are offered a choice between the two envelopes, the smart thing to do is to choose B. Pascal's wager is exactly like this game, except that it uses a different set of envelopes, Christian and atheist. Actually, Pascal only analyzed the Christian case, but the atheist case is the logical extension. For the sake of argument, imagine for the moment that there's a 50-50 chance that God exists. Pascal assumed that it would be the Christian God, of course. Now, choosing the Christian envelope is equivalent to choosing to be a devout Christian. If you happen to choose this path, there are two possibilities. If you are a faithful Christian and there is no God, you just fade into nothingness whenever you die. But if there is a God, you go to heaven and live for eternity in bliss, infinity. So the expected value of being a Christian is 1/2 chance of fading into nothing, 1/2 times 0 equals 0. 1/2 chance of going to heaven, 1/2 times infinity equals infinity. Expectation equals infinity. After all, half of infinity is still infinity. Thus, the value of being a Christian is infinite. Now, what happens if you are an atheist? If you are correct, there is no God, you gain nothing from being right. After all, there is no God, there is no heaven. But if you are wrong and there is a God, you go to hell for an eternity, negative infinity. So the expected value of being an atheist is 1/2 chance of fading into nothing, 1/2 times 0 equals 0. 1/2 chance of going to hell, 1/2 times negative infinity equals negative infinity. Expectation equals negative infinity. Negative infinity. The value is as bad as you can possibly get. The wise person would clearly choose Christianity instead of atheism. But we made an assumption here that there is a 50-50 chance that God exists. What happens if there is only a 1,000th chance? The value of being a Christian would be 999 of 1,000 chance of fading into nothing, 999 of 1,000 times 0 equals 0. 1,000th chance of going to heaven, 1,000th times infinity equals infinity. Expectation equals infinity. It's still the same, infinite, and the value of being an atheist is still negative infinity. It's still much better to be a Christian. If the probability is 1/10,000th or 1/1,000,000th or 1 in a gazillion, it comes out the same. The only exception is 0. If there is no chance that God exists, Pascal's wager, as it came to be known, makes no sense. The expected value of being a Christian would then be 0 times infinity, and that was gibberish. Nobody was willing to say that there was 0 chance that God exists. No matter what your outlook, it is always better to believe in God, thanks to the magic of 0 and infinity. Certainly Pascal knew which way to wager, even though he gave up mathematics to win his bet. Chapter 5. Infinite Zeros and Infidel Mathematicians. Zero and the Scientific Revolution. With the introduction of the infinitely small and infinitely large, mathematics, usually so strictly ethical, fell from grace. The virgin state of absolute validity and irrefutable proof of everything mathematical was gone forever. The realm of controversy was inaugurated, and we have reached the point where most people differentiate and integrate not because they understand what they are doing, but from pure faith, because up to now it has always come out right. Friedrich Engels, Anti-Dühring. 0 and infinity had destroyed the Aristotelian philosophy. The void and the infinite cosmos had eliminated the nutshell universe and the idea of nature's abhorrence of the vacuum. The ancient wisdom was discarded, and scientists began to divine the laws that governed the workings of nature. However, there was a problem with the scientific revolution: 0. Deep within the scientific world's powerful new tool, calculus, was a paradox. The inventors of calculus, Isaac Newton and Gottfried Wilhelm Leibniz, created the most powerful mathematical method ever by dividing by zero and adding an infinite number of zeros together. Both acts were as illogical as adding 1 plus 1 to get 3. Calculus, at its core, defied the logic of mathematics. Accepting it was a leap of faith. Scientists took that leap, for calculus is the language of nature. To understand that language completely, science had to conquer the infinite zeros. The infinite zeros. When, after 1,000-year stupor, European thought shook off the effect of the sleeping powders so skillfully administered by the Christian fathers, the problem of infinity was one of the first to be revived. Tobias Danzig, Number, the Language of Science. Zeno's curse hung over mathematics for 2 millennia. Achilles seemed doomed to chase the tortoise forever, never catching up. Infinity lurked in Zeno's simple riddle. The Greeks were stumped by Achilles' infinite steps. They never considered adding infinite parts together even though Achilles' strides approached zero size. The Greeks could hardly add steps of zero size together without the concept of zero. However, once the West embraced zero, mathematicians began to tame the infinite and ended Achilles' race. Even though Zeno's sequence has infinite parts, we can add all of the steps together and still stay within the realm of the finite. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and so forth and so on, equals 2. The first person to do this sort of trick, adding infinite terms to get a finite result, was the 14th century British logician Richard Sweyseth. Sweyseth took an infinite sequence of numbers, 1/2, 2/4, 3/8, 4/16, and so forth and so on, n divided by 2 to the nth, and so forth and so on, and added them all together, yielding 2. After all, the numbers in the sequence get closer and closer to zero. Naively, one would guess that this would ensure that the sum remains finite. Alas, the infinite is not quite that simple. At about the same time Sweyseth was writing, Nicolas Oresme, a French mathematician, tried his hand at adding together another infinite sequence of numbers, the so-called harmonic series, 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, and so forth and so on. Like the Zeno sequence and Sweyseth's sequence, all the terms get closer and closer to zero. However, when Oresme tried to sum the terms in the sequence, he realized that the sums got larger and larger and larger. Even though the individual terms go to zero, the sum goes off to infinity. Oresme showed this by clumping the terms together. 1/2 plus, open parentheses, 1/3 plus 1/4, close parentheses, plus, open parentheses, 1/5 plus 1/6 plus 1/7 plus 1/8, close parentheses, plus, and so forth and so on. The first group clearly equals 1/2. The second group is greater than, open parentheses, 1/4 plus 1/4, close parentheses, or 1/2. The third group is greater than, open parentheses, 1/8 plus 1/8 plus 1/8 plus 1/8, close parentheses, or 1/2, and so forth. You keep adding 1/2 after 1/2 after 1/2, and the sum gets bigger and bigger and off to infinity. Even though the terms themselves go to zero, they don't approach zero fast enough. An infinite sum of numbers can be infinite, even if the numbers themselves approach zero. Yet this isn't the strangest aspect of infinite sums. Zero itself is not immune to the bizarre nature of infinity. Consider the following series: 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. It's not so hard to show that this series sums to zero. After all, open parentheses 1 minus 1, close parentheses, plus, 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 and so forth and so on, is the same thing as 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus, and so forth, which clearly sums to 0. But beware, group the series in a different way, 1 plus open parentheses negative 1 plus 1 close parentheses, plus open parentheses negative 1 plus 1 close parentheses, plus open parentheses negative 1 plus 1 close parentheses, plus open parentheses negative 1 plus 1 close parentheses, plus open parentheses negative 1 plus 1 close parentheses, plus, and so forth and so on, is the same thing as 1 plus 0 plus 0 plus 0 plus 0 plus 0 plus, and so forth, which clearly sums to 1. The same infinite sum of zeros can equal 0 and 1 at the same time. An Italian priest, Father Guido Grandi, even used this series to prove that God could create the universe, 1, out of nothing, 0. In fact, the sequence can be set to equal anything at all. To make the sum equal 5, start with 5s and negative 5s instead of 1s and negative 1s, and we can show that 0 plus 0 plus 0 plus 0 plus, and so forth and so on, equals 5. Adding infinite things to each other can yield bizarre and contradictory results. Sometimes, when the terms go to 0, the sum is finite, a nice normal number like 2 or 53. Other times, the sum goes off to infinity, and an infinite sum of zeros can equal anything at all and everything at the same time. Something very bizarre was going on. Nobody knew quite how to handle the infinite. Luckily, the physical world made a little more sense than the mathematical one. Adding infinite things to each other seems to work out most of the time so long as you are dealing with something in real life, like finding the volume of a barrel of wine. And 1612 was a banner year for wine. Johannes Kepler, the man who figured out that planets move in ellipses, spent that year gazing into wine barrels, since he realized that the methods that vintners and coopers used to estimate the size of barrels were extremely crude. To help the wine merchants out, Kepler chopped up the barrels, in his mind, into an infinite number of infinitely tiny pieces, and then added them back together again to yield their volumes. This may seem a backward way of going about measuring barrels, but it was a brilliant idea. To make the problem a bit simpler, let us consider a two-dimensional object rather than a three-dimensional one, a triangle. The triangle in Figure 23 has a height of 8 and a base of 8. Since the area of a triangle is half the base times the height, the area is 32. Now imagine trying to estimate the size of the triangle by inscribing little rectangles inside the triangle. For a first try, we get an area of 16, quite a bit short of the actual value of 32. The second try is a bit better. With 3 rectangles, we get a value of 24. Closer, but still not there yet. The third try gives us 28, closer still. As you can see, making smaller and smaller rectangles whose width, denoted by the symbol delta x, go to 0, makes the value closer and closer to 32, the true value for the area of the triangle. The sum of these rectangles is equal to sigma function x delta x, where the Greek sigma represents the sum over an appropriate range, and function x is the equation of the curve that the rectangles strike. In modern notation, as delta x goes to 0, we replace the sigma with a new symbol, integral, and delta x with derivative x, turning the equation into integral function x derivative x, which is the integral. In one of Kepler's lesser-known works, Volume Measurement of Barrels, he does this in 3 dimensions, slicing barrels into planes and summing the planes together. Kepler, at least, wasn't afraid of a glaring problem. As delta x goes to 0, the sum becomes equivalent to adding an infinite number of zeros together, a result that makes no sense. Kepler ignored the problem. Though adding infinite zeros together was gibberish from a logical point of view, the answer it yielded was the right one. Kepler was not the only prominent scientist who sliced objects infinitely thin. Galileo, too, pondered infinity and these infinitely small slices of area. These two ideas transcend our finite understanding, he wrote, the former on account of their magnitude, the latter because of their smallness. Yet despite the deep mystery of the infinite zeros, Galileo sensed their power. Imagine what they are when combined, he wondered. Galileo's student Bonaventura Cavalieri would provide part of the answer. Instead of barrels, Cavalieri cut up geometric objects. To Cavalieri, every area, like that of the triangle, is made up of an infinite number of zero-width lines, and a volume is made up of an infinite number of zero-height planes. These indivisible lines and planes are like atoms of area and volume. They can't be divided any further. Just as Kepler measured the volumes of barrels with his thin slices, Cavalieri added up an infinite number of these indivisible zeros to figure out the area or the volume of a geometric object. For geometers, Cavalieri's statement was troublesome indeed. Adding infinite zero-area lines could not yield a two-dimensional triangle, nor could infinite zero-volume planes add up to a three-dimensional structure. It was the same problem. Infinite zeros make no logical sense. However, Cavalieri's method always gave the right answer. Mathematicians ignored the logical and philosophical troubles with adding infinite zeros, especially since indivisibles, or infinitesimals as they came to be called, finally solved a long-standing puzzle, the problem of the tangent. A tangent is a line that just kisses a curve. For any point along a smooth curve that flows through space, there is a line that just grazes the curve, touching at exactly one point. This is the tangent, and mathematicians realize that it is extremely important in studying motion. For instance, imagine swinging a ball on a string around your head. It's traveling in a circle. However, if you suddenly cut the string, the ball will fly off along that tangent line. In the same way, a baseball pitcher's arm travels in an arc as he throws, but as soon as he lets go, the ball flies off on the tangent. As another example, if you want to find out where a ball will come to rest at the bottom of a hill, you look for a point where the tangent line is horizontal. The steepness of the tangent line, its slope, has some important properties in physics. For instance, if you've got a curve that represents the position of, say, a bicycle, then the slope of the tangent line to that curve at any given point tells you how fast that bicycle is going when it reaches that spot. For this reason, several 17th century mathematicians like Evangelista Torricelli, René Descartes, the Frenchman Pierre de Fermat, famous for his last theorem, and the Englishman Isaac Barrow created different methods for calculating the tangent line to any given point on a curve. However, like Cavalieri, all of them came up against the infinitesimal. To draw a tangent line at any given point, it's best to make a guess. Choose another point nearby and connect the two. The line you get isn't exactly the tangent line, but if the curve isn't too bumpy, the two lines will be pretty close. As you reduce the distance between the points, the guess gets closer to the tangent line. When your points are zero distance away from each other, your approximation is perfect. You have found the tangent. Of course, there's a problem. The most important property of a line is its slope, and to measure this, mathematicians look at how high a line rises in a certain amount of distance. As an example, imagine you are driving east on a hill. For every mile east you drive, you gain half a mile in altitude. The slope of the hill is simply the height, half a mile, over the horizontal distance you have driven, 1 mile. Mathematicians say that the slope of the hill is 1/2. The same thing is true for lines. To measure the slope of a line, you look at how much the line rises, which mathematicians denote by the symbol delta y, in a given horizontal distance, which is denoted by delta x. The slope of the line is delta y divided by delta x. When you try to calculate the slope of a tangent line, 0 wrecks your approximation process. As your approximations of the tangent lines get better and better, the points on the curve you use to create the approximations get closer together. This means that the difference in height, delta y, goes to 0, as does the horizontal distance between the points, delta x. As your tangent approximations get better and better, delta y divided by delta x approaches 0 divided by 0. 0 divided by 0 can equal any number in the universe. Does the slope of the tangent line have any meaning? Every time mathematicians tried to deal with the infinite or with 0, they encountered trouble with illogic. To figure out the volume of a barrel or the area under a parabola, mathematicians added infinite zeros together. To find out the tangent of a curve, they divided 0 by itself. 0 and infinity made the simple acts of taking tangents and finding areas appear to be self-contradictory. These troubles would have ended as an interesting footnote but for one thing. These infinites and zeros are the key to understanding nature. 0 and the mystical calculus. If we lift the veil and look underneath, we shall discover much emptiness, darkness, and confusion. Nay, if I mistake not, direct impossibilities and contradictions. They are neither finite quantities, nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? Bishop Berkeley, The Analyst. The tangent problem and the area problem both ran afoul of the same difficulties with infinities and zeros. It's no wonder, because the tangent problem and the area problem are actually the same thing. They are both aspects of calculus, a scientific tool far more powerful than anything ever seen before. The telescope, for instance, had given scientists the ability to find moons and stars that had never been observed before. Calculus, on the other hand, gave scientists a way to express the laws that govern the motion of the celestial bodies, and laws that would eventually tell scientists how those moons and stars had formed. Calculus was the very language of nature, yet its very fabric was infused with zeros and infinities that threatened to destroy the new tool. The first discoverer of calculus nearly died before he ever took a breath. Born prematurely on Christmas Day in 1642, Isaac Newton squirmed into the world so small that he was able to fit into a quart pot. His father, a farmer, had died 2 months earlier. Despite a traumatic childhood and a mother who wanted him to become a farmer, Newton enrolled in Cambridge in the 1660s and flourished. Within a few years, he developed a systematic method of solving the tangent problem. He could figure out the tangent to any smooth curve at any point. This process, the first half of calculus, is now known as differentiation. However, Newton's method of differentiation doesn't look very much like the one we use today. Newton's style of differentiation was based upon fluxions, the flows of mathematical expressions that he called fluents. As an example of Newton's fluxions, take the equation y equals x squared plus x plus 1. In this equation, the fluents are y and x. Newton supposed that y and x are changing or flowing as time progresses. Their rates of change, their fluxions, are denoted by y and x respectively. Newton's method of differentiation was based on a notational trick. He let the fluxions change, but he only let them change infinitesimally. Essentially, he gave them no time to flow. In Newton's notation, y would change in that instant to open parentheses y plus oy dot close parentheses, while x changes to open parentheses x plus ox dot close parentheses. The letter O represented the amount of time that had passed. It was almost a zero, but not quite, as we shall hear. The equation then becomes open parentheses y plus oy dot close parentheses equals open parentheses x plus ox dot close parentheses squared plus open parentheses x plus ox dot close parentheses plus 1. Multiplying out the open parentheses x plus ox dot close parentheses squared term gives us y plus oy dot equals x squared plus 2x open parentheses ox dot close parentheses plus open parentheses ox dot close parentheses squared plus x plus ox dot plus 1. Rearranging the terms yields y plus oy dot equals open parentheses, x squared plus x plus 1, close parentheses, plus 2x, open parentheses, o x dot, close parentheses, plus 1, open parentheses, o x dot, close parentheses, plus open parentheses, o x dot, close parentheses, squared. Since y equals x squared plus x plus 1, we can subtract y from the left side of the equation and x squared plus x plus 1 from the right side of the equation and leave the system unchanged. That leaves us with OY dot equals 2x open parentheses OX dot close parentheses plus 1 open parentheses OX dot close parentheses plus open parentheses OX dot close parentheses squared. Now comes the dirty trick. Newton declared that since OX dot was really small, open parentheses OX dot close parentheses squared was even smaller. It vanished. In essence, it was 0 and could be ignored. That gives us OY dot equals 2x open parentheses OX dot close parentheses plus 1 open parentheses OX dot close parentheses, which means that OY dot divided by OX dot equals 2x plus 1, which is the slope of the tangent line at any point x on the curve. The infinitesimal time period O drops right out of the equation. OY dot divided by OX dot becomes Y dot divided by X dot, and O need never be thought of again. The method gave the right answer, but Newton's vanishing act was very troubling. If, as Newton insisted, open parentheses OX dot close parentheses squared and open parentheses OX dot close parentheses cubed and higher powers of OX dot were equal to 0, then OX dot itself must be equal to 0. On the other hand, if OX dot was 0, then dividing by OX dot as we do toward the end is the same thing as dividing by 0, as is the very last step of getting rid of the O in the top and bottom of the OY dot divided by OX dot expression. Division by 0 is forbidden by the logic of mathematics. Newton's method of fluxions was very dubious. It relied upon an illegal mathematical operation, but it had one huge advantage. It worked. The method of fluxions not only solved the tangent problem, it also solved the area problem. Finding the area under a curve, or a line, which is a type of curve, an operation we now call integration, is nothing more than the reverse of differentiation. Just as differentiating the curve y equals x squared plus x plus 1 gives you an equation for the slope of the tangent, y equals 2x plus 1, integrating the curve y equals 2x plus 1 gives you a formula for the area under the curve. This formula is y equals x squared plus x plus 1. The area underneath the curve between the boundaries x equals a and x equals b is simply open parentheses b squared plus b plus 1 close parentheses minus open parentheses a squared plus a plus 1 close parentheses, figure 27. Technically, the formula is y equals x squared plus x plus c, where c is any constant you choose. The process of differentiation destroys information, so the process of integration doesn't give you exactly the answer you were looking for unless you add another bit of information. Calculus is the combination of these two tools, differentiation and integration, in one package. Though Newton broke some very important mathematical rules by toying with the powers of 0 and infinity, calculus was so powerful that no mathematician could reject it. Nature speaks in equations. It is an odd coincidence. The rules of mathematics were built around counting sheep and surveying property, yet these very rules govern the way the universe works. Natural laws are described with equations, and equations, in a sense, are simply tools where you plug in numbers and get another number out. The ancients knew a few of these equation laws, like the law of the lever, but with the beginning of the scientific revolution, these equation laws sprang up everywhere. Kepler's third law described the time it takes for planets to complete an orbit. R cubed divided by t squared equals k for time t, distance r, and a constant k. In 1662, Robert Boyle showed that if you take a sealed container with a gas in it, squishing the container would increase the pressure inside. Pressure P times volume V was always a constant. PV equals K for a constant K. In 1676, Robert Hooke figured out that the force exerted by a spring, F, was a negative constant, negative K, multiplied by the distance x that you've stretched it. F equals negative Kx. These early equation laws were extremely good at expressing simple relationships. But equations have limitations, their constancy, which prevented them from being universal laws. As an example, let's take the famous equation we all learned in high school. Rate times time equals distance. It shows how far you get, x miles, when you run with a certain velocity, v, miles per hour, for a time, t hours. Vt equals x. After all, miles per hour times hours equals miles. This equation is very useful when you are calculating how long it will take to get from New York to Chicago on a train that moves exactly 120 miles an hour. But how many things really move at a constant rate, like a train in a math problem? Drop a ball and it moves faster and faster. In this case, x equals vt is quite simply wrong. For the case of a dropped ball, x equals gt squared divided by 2, where g is the acceleration due to gravity. On the other hand, if you've got an increasing force on the ball, x might equal something like t cubed divided by 3. Rate times time equals distance is not a universal law. It doesn't apply under all conditions. Calculus allowed Newton to combine all these equations into one grand set of laws, laws that applied in all cases under all conditions. For the first time, science could see the universal laws that underlie all of these little half-laws. Even though mathematicians knew that calculus was deeply flawed, thanks to the mathematics of zero and infinity, they quickly embraced the new mathematical tools. For the truth is, nature doesn't speak in ordinary equations. It speaks in differential equations, and calculus is the tool that you need to pose and solve these differential equations. Differential equations are not like the everyday equations that we are all familiar with. An everyday equation is like a machine. You feed numbers into the machine and out pops another number. A differential equation is also like a machine, but this time you feed equations into the machine and out pop new equations. Plug in an equation that describes the conditions of the problem. Is the ball moving at a constant rate, or is a force acting on the ball? And out pops the equation that encodes the answer that you seek. The ball moves in a straight line or in a parabola. One differential equation governs all of the uncountable numbers of equation laws. And unlike the little equation laws that sometimes hold and sometimes don't, the differential equation is always true. It is a universal law. It is a glimpse at the machinery of nature. Newton's calculus, his method of fluxions, did just this by tying together concepts like position, velocity, and acceleration. When Newton denoted position with the variable x, he realized that velocity is simply the fluxion, what modern mathematicians call the derivative of x dot. And acceleration is nothing more than the derivative of velocity, x2 dot. Going from position to velocity to acceleration and back again is as simple as differentiating, adding another dot, or integrating, removing a dot. With that notation in hand, Newton was able to create a simple differential equation that describes the motion of all objects in the universe. F equals mx2 dot, where F is the force on an object and m is its mass. Actually, this is not quite a universal law, as the equation only holds when the mass of an object is constant. The more general version of Newton's law is F equals p dot, where p is an object's momentum. Of course, Newton's equations were eventually refined further by Einstein. If you've got an equation that tells you about the force that is being applied on an object, the differential equation reveals exactly how the object moves. For instance, if you have a ball in free fall, it moves in a parabola, while a frictionless spring wobbles back and forth forever, and a spring with friction slowly comes to rest. As different as these outcomes seem, they are all governed by the same differential equation. Likewise, if you know the way an object moves, whether it be a toy ball or a giant planet, the differential equation can tell you what kind of force is being applied. Newton's triumph was taking the equation that described the force of gravity and figuring out the shapes of the planet's orbits. People had suspected that the force was proportional to 1 divided by r squared, and when ellipses popped right out of Newton's differential equations, people began to believe that Newton was correct. Despite the power of calculus, the key problem remained. Newton's work was based on a very shaky foundation, dividing zero by itself. His rival's work had the same flaw. In 1673, an esteemed German lawyer and philosopher visited London. His name was Gottfried Wilhelm Leibniz. He and Newton would tear the scientific world asunder, though neither would solve the problem of the zeros that suffused calculus. Nobody knows whether the 33-year-old Leibniz encountered Newton's unpublished work during his trip to England. But between 1673 and 1676, when Leibniz next visited London, he too had developed calculus, although in a slightly different form. Looking back, it appears that Leibniz formulated his version independently of Newton, though the matter is still being debated. The two had a correspondence in the 1670s, making it very difficult to establish how they influenced each other. However, though the two theories came up with the same answers, their notations and their philosophies were very different. Newton disliked infinitesimals, the little o's in his Fluxian equations that sometimes acted like zeros and sometimes like non-zero numbers. In a sense, these infinitesimals were infinitely small, smaller than any positive number you could name, yet still somehow greater than zero. To the mathematicians of the time, this was a ridiculous concept. Newton was embarrassed by the infinitesimals in his equations, and he swept them under the rug. The O's in his calculations were only intermediaries, crutches that vanished miraculously by the end of the computation. On the other hand, Leibniz reveled in the infinitesimal. Where Newton wrote OX dot, Leibniz wrote dx, an infinitesimally tiny little piece of x. These infinitesimals survived unchanged throughout Leibniz's calculations. Indeed, the derivative of y with respect to x was not the infinitesimal free ratio of Fluxions, y dot divided by x dot, but the ratio of infinitesimals, derivative y divided by derivative x. With Leibniz's calculus, these derivative y's and derivative x's can be manipulated just like ordinary numbers, which is why modern mathematicians and physicists usually use Leibniz's notation rather than Newton's. Leibniz's calculus had the same power as Newton's, and thanks to its notation, even a bit more. Nevertheless, underneath all the mathematics, Leibniz's differentials still had the same forbidden zero divided by zero nature that plagued Newton's Fluxions. As long as this flaw remained, calculus would be based upon faith rather than logic. In fact, faith was very much on Leibniz's mind when he derived new mathematics, such as the binary numbers. Any number can be written as a string of zeros and ones. To Leibniz, this was the creation ex nihilo, the creation of the universe out of nothing, more than God divided by 1 and void divided by 0. Leibniz even tried to get the Jesuits to use this knowledge to convert the Chinese to Christianity. It would be many years before mathematicians began to free calculus from its mystical underpinnings, for the mathematical world was busy fighting over who invented calculus. There is little doubt that Newton came up with the idea first in the 1660s, but he did not publish his work for 20 years. Newton was a magician, theologian, and alchemist as well as a scientist. For instance, he used biblical texts to conclude that the second coming of Christ would occur around 1948, and many of his views were heretical. As a result, he was secretive and reluctant to reveal his work. In the meantime, while Newton sat upon his discovery, Leibniz developed his own calculus. The two promptly accused each other of plagiarism, and the English mathematical community, which backed Newton, pulled away from the continental mathematicians who supported Leibniz. As a result, the English stuck to Newton's Fluxian notation rather than adopting Leibniz's superior differential notation, cutting off their noses to spite their faces. English mathematicians fell far behind their continental counterparts when it came to developing calculus. A Frenchman, not an Englishman, would be remembered for taking the first nibble at the mysterious zeros and infinities that suffused calculus. Mathematicians learn of L'Hopital's rule when they first learn about calculus. Oddly enough, it was not L'Hopital who came up with the rule that bears his name. Born in 1661, Guillaume François Antoine de L'Hopital was a marquis and was thus very wealthy. He had an early interest in mathematics, and though he spent some time in the army, becoming a cavalry captain, he soon turned back to his true love of math. L'Hopital bought himself the best teacher that money could buy, Johann Bernoulli, a Swiss mathematician and one of the early masters of Leibniz's calculus of infinitesimals. In 1692, Bernoulli taught L'Hopital calculus. L'Hopital was so enthralled by the new mathematics that he persuaded Bernoulli to send him all Bernoulli's new mathematical discoveries for the Marquis to use as he desired in return for cash. The result was a textbook. In 1696, L'Hopital's Analyse des infiniments petits became the first textbook on calculus and introduced much of Europe to the Leibnizian version. Not only did L'Hopital explain the fundamentals of calculus in his textbook, he also included some exciting new results. The most famous is known as L'Hopital's rule. L'Hopital's rule took the first crack at the troubling 0 divided by 0 expressions that were popping up throughout calculus. The rule provided a way to figure out the true value of a mathematical function that goes to 0 divided by 0 at a point. L'Hopital's rule states that the value of the fraction was equal to the derivative of the top expression divided by the derivative of the bottom expression. For instance, consider the expression x divided by open parenthesis sine x close parenthesis when x equals 0. X equals 0 as does sine x, so the expression is equal to 0 divided by 0. Using L'Hopital's rule, we see that the expression goes to 1 divided by open parentheses cosine x close parentheses, as 1 is the derivative of x and cosine x is the derivative of sine x. Cosine x equals 1 when x equals 0, so the whole expression equals 1 divided by 1 equals 1. Clever manipulations could also bring L'Hopital's rule to resolve other odd expressions: infinity divided by infinity, 0 to the 0th power, 0 to the infinite power, and infinity to the 0 power. All of these expressions, but especially 0 divided by 0, could take on any value you desire them to have depending on the functions you put in the numerator and denominator. This is why 0 divided by 0 is dubbed indeterminate. It was no longer a complete mystery. Mathematicians could extract some information about 0 divided by 0 if they approached it very carefully. 0 was no longer an enemy to be avoided, it was an enigma to be studied. Soon after L'Hopital's death in 1704, Bernoulli started implying that L'Hopital had stolen his work. At the time, the mathematical community rejected Bernoulli's claims. Not only had L'Hopital proved himself an able mathematician, but Johann Bernoulli had a tarnished reputation. He had previously tried to claim credit for another mathematician's proof. The other mathematician happened to be his brother Jakob. In this case, though, Johann Bernoulli's claim was justified. His correspondence with L'Hopital backs his story. Alas for Bernoulli, the name for L'Hopital's rule stuck. L'Hopital's rule was extremely important for resolving some of the difficulties with 0 divided by 0, but the underlying problem remained. Newton's and Leibniz's calculus depends upon dividing by 0 and on numbers that miraculously disappear when you square them. L'Hopital's rule examined 0 divided by 0 with tools that were built upon 0 divided by 0 to begin with. It is a circular argument. And as physicists and mathematicians all over the world were beginning to use calculus to explain nature, cries of protest emanated from the church. In 1734, 7 years after Newton's death, an Irish bishop, George Berkeley, wrote a book entitled The Analyst, or a discourse addressed to an infidel mathematician. The mathematician in question was most likely Edmund Halley, always a supporter of Newton. In The Analyst, Berkeley pounced on Newton's and Leibniz's dirty tricks with zeros. Calling infinitesimals ghosts of departed quantities, Berkeley showed how making these infinitesimals disappear with impunity can lead to a contradiction. He concluded that he who can digest a second or third fluxion, a second or third difference, need not, methinks, be squeamish about any point in divinity. Though mathematicians of the day sniped at Berkeley's logic, the good bishop was entirely correct. In those days, calculus was very different from other realms of mathematics. Every theorem in geometry had been rigorously proved. By taking a few rules from Euclid and proceeding very carefully step by step, a mathematician could show how a triangle's angles sum to 180 degrees, or any other geometric fact. On the other hand, calculus was based on faith. Nobody could explain how those infinitesimals disappeared when squared. They just accepted the fact because making them vanish at the right time gave the correct answer. Nobody worried about dividing by zero when conveniently ignoring the rules of mathematics explained everything from the fall of an apple to the orbits of the planets in the sky. Though it gave the right answer, using calculus was as much an act of faith as declaring a belief in God. The end of mysticism. A quantity is something or nothing. If it is something, it has not yet vanished. If it is nothing, it is literally vanished. The supposition that there is an intermediate state between these two is a chimera. Jean-Laurent d'Alembert. In the shadow of the French Revolution, the mystical was driven out of calculus. Despite calculus's shaky foundations, by the end of the 18th century, mathematicians all over Europe were having stunning successes with the new tool. Colin Maclaren and Brooke Taylor, perhaps the best British mathematicians in the era of isolation from the continent, discovered how to use calculus to rewrite functions in a totally different form. For instance, after using some tricks in calculus, mathematicians realized that the function 1 divided by open parentheses 1 minus x close parentheses can be written as 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth plus and so forth and so on. Though the two expressions look dramatically different, they are, with some caveats, exactly the same. Those caveats, which stem from the properties of zero and infinity, can become very important, however. The Swiss mathematician Leonhard Euler, inspired by calculus's easy manipulation of zeros and infinities, used similar reasoning as Taylor and Maclaren and proved that the sum 1 divided by x cubed plus 1 divided by x squared plus 1 divided by x plus 1 plus x squared plus x cubed and so forth equals 0. To convince yourself that something fishy is going on, plug in the number 1 for x and see what happens. Euler was an excellent mathematician. In fact, he was one of the most prolific and influential in history, but in this case, the careless manipulation of zero and infinity led him astray. It was a foundling who finally tamed the zeros and infinities in calculus and rid mathematics of its mysticism. In 1717, an infant was found on the steps of the church of Saint-Jean-Baptiste-Laurent in Paris. In memory of that occasion, the child was named Jean Laurent, and he eventually took the surname d'Alembert. Though he was raised by an impoverished working-class couple, his foster father was a glazier, it turns out that his birth father was a general and his mother was an aristocrat. D'Alembert is best known for his collaboration on the famed Encyclopédie of Human Knowledge, a 20-year effort with co-author Denis Diderot. But D'Alembert was more than an encyclopedist. It was D'Alembert who realized that it was important to consider the journey as well as the destination. He was the one who hatched the idea of limit and solved calculus's problems with zeros. Once again, let us consider the story of Achilles and the tortoise, which is an infinite sum of steps that get closer and closer to zero. Manipulating an infinite sum, whether it is in the Achilles problem or in finding the area underneath a curve or finding an alternate form for a mathematical function, caused mathematicians to come up with contradictory results. D'Alembert realized that the Achilles problem vanishes if you consider the limit of the race. In our example, at every step the tortoise and Achilles get closer and closer to the 2-foot mark. No step takes them farther away or even keeps them at the same distance. Each moment brings them closer to that mark. Thus, the limit of that race, its ultimate destination, is at the 2-foot mark. This is where Achilles passes the tortoise. But how do you prove that 2 feet is actually the limit of the race? I ask you to challenge me. Give me a tiny distance, no matter how small, and I will tell you when both Achilles and the tortoise are less than that tiny distance away from the limit. As an example, let's say that you challenge me with a distance of 1/1000th of a foot. Well, a few calculations later, I would tell you that after the 11th step, Achilles is 977 millionths of a foot away from the 2-foot mark, while the tortoise is half that distance away. I have met your challenge with 23 millionths of a foot to spare. What if you challenged me with a distance of 1/1000th of a foot? After 31 steps, Achilles is 931 trillionths of a foot away from the target, 69 trillionths closer than you needed, while the tortoise again is half that distance away. No matter how you challenge me, I can meet that challenge by telling you a time when Achilles is closer to the mark than you require. This shows that, indeed, Achilles is getting arbitrarily close to the 2-foot mark as the race progresses. 2 feet is the limit of the race. Now, instead of thinking of the race as a sum of infinite parts, think of it as a limit of finite subraces. For instance, in the first race, Achilles runs to the 1-foot mark. Achilles has run 1 foot in all. In the next race, Achilles does the first 2 parts, first running 1 foot and then a ½ foot. In total, Achilles has run 1 plus 1/2, 1.5 feet in all. The third race takes him as far as 1 plus 1/2 plus 1/4, 1.75 feet all told. Each of these subraces is finite and well defined. We never encounter an infinity. What D'Alembert did informally, and what the Frenchman Augustin Cauchy, the Czech Bernard Bolzano, and the German Karl Weierstrass would later formalize, was to rewrite the infinite sum, 1 plus 1/2 plus 1/4 plus 1/8 plus, and so forth and so on, plus 1 divided by 2 to the nth, plus, and so forth, as the expression limit, open parentheses, as n goes to infinity, close parentheses, of 1 plus 1/2 plus 1/4 plus 1/8, and so on to 1 divided by 2 to the nth. It is a very subtle change in notation, but it makes all the difference in the world. When you have an infinity in an expression, or when you divide by 0, all the mathematical operations, even those as simple as addition, subtraction, multiplication, and division, go out the window. Nothing makes sense any longer. So when you deal with an infinite number of terms in a series, even the plus sign doesn't seem so straightforward. That is why the infinite sum of +1 and -1 we saw at the beginning of the chapter seems to equal 0 and 1 at the same time. However, by putting this limit sign in front of a series, you separate the process from the goal. In this way, you avoid manipulating infinities and zeros. Just as Achilles' subraces are each finite, each partial sum in a limit is finite. You can add them, divide them, square them, you can do whatever you want. The rules of mathematics still work, since everything is finite. Then, after all your manipulations are complete, you take the limit, you extrapolate and figure out where the expression is headed. Sometimes that limit doesn't exist. For instance, the infinite sum of +1 and -1 does not have a limit. The value of the partial sums flips back and forth between 1 and 0. It's not really heading to a predictable destination. But with Achilles' race, the partial sums go from 1 to 1.5 to 1.75 to 1.875 to 1.9375 and so forth. They get closer and closer to 2. The sums have a destination, a limit. The same thing goes for taking the derivative. Instead of dividing by 0 as Newton and Leibniz did, modern mathematicians divide by a number that they let approach 0. They do the division perfectly legally, since there are no zeros. Then they take the limit. The dirty tricks of making squared infinitesimals disappear and then dividing by zero to get a derivative were no longer necessary. This logic may seem like splitting hairs, like an argument as mystical as Newton's ghosts, but in reality it's not. It satisfies the mathematician's strict requirement of logical rigor. There is a very firm, consistent basis for the concept of limits. Indeed, you can even dispense with the "I challenge you" argument entirely, as there are other ways of defining a limit, such as calling it the convergence of two numbers, the limit superior and limit inferior. I have a wonderful proof of this, but alas, this book is too small to contain it. Since limits are logically airtight, by defining a derivative in terms of limits, it becomes airtight as well and puts calculus on a solid foundation. No longer was it necessary to divide by zeros. Mysticism vanished from the realm of mathematics and logic ruled once more. The peace lasted until the Reign of Terror. Chapter 6. Infinity's Twin, the Infinite Nature of Zero. God made integers, all else is the work of man. Leopold Kronecker. Zero and infinity always look suspiciously alike. Multiply zero by anything and you get zero. Multiply infinity by anything and you get infinity. Dividing a number by zero yields infinity. Dividing a number by infinity yields zero. Adding zero to a number leaves the number unchanged. Adding a number to infinity leaves infinity unchanged. These similarities were obvious since the Renaissance, but mathematicians had to wait until the end of the French Revolution before they finally unraveled zero's big secret. Zero and infinity are two sides of the same coin, equal and opposite, yin and yang, equally powerful adversaries at either end of the realm of numbers. The troublesome nature of zero lies with the strange powers of the infinite, and it is possible to understand the infinite by studying zero. To learn this, mathematicians had to venture into the world of the imaginary, a bizarre world where circles are lines, lines are circles, and infinity and zero sit on opposite poles. The imaginary, a fine and wonderful refuge of the divine spirit, almost an amphibian between being and non-being. Gottfried Wilhelm Leibniz. Zero is not the only number that was rejected by mathematicians for centuries. Just as zero suffered from Greek prejudice, other numbers were ignored as well, numbers that made no geometric sense. One of these numbers, I, held the key to zero's strange properties. Algebra presented another way of looking at numbers, entirely divorced from the Greek geometric ideas. Instead of trying to measure the area inside a parabola, as the Greeks did, early algebraists sought to find the solutions to equations that encode relationships between different numbers. For instance, the simple equation 4x minus 12 equals 0 describes how an unknown number x is related to 4, 12, and 0. The task of the algebra student is to figure out what number x is. In this case, x is 3. Substitute 3 for x in the equation and you will quickly see that the equation is satisfied. 3 is a solution for the equation 4x minus 12 equals 0. In other words, 3 is a zero or a root of the expression 4x minus 12. When you start stringing symbols together to get equations, you can wind up with something unexpected. For instance, take the given equation and change the minus sign into a plus sign. This leaves us with a very innocent-looking equation, 4x plus 12 equals 0. But the solution to that equation is now negative 3, a negative number. Just as Indian mathematicians accepted zero while Europeans rejected it for centuries, the East embraced negative numbers while the West tried to ignore them. As late as the 17th century, Descartes refused to accept negative numbers as roots of equations. He called them false roots, which explains why he never extended his coordinate system to the negative numbers. Descartes was a late holdover, a victim of his success in marrying algebra to geometry. Negative numbers had long been useful to algebraists, even Western algebraists. Negative numbers came up all the time in solving equations, such as quadratic equations. A linear equation like 4x minus 12 equals 0 is extremely simple to solve, and such problems didn't entertain algebraists for very long. So they soon turned to more difficult problems, quadratic equations, equations that begin with an x squared term, like x squared minus 1 equals 0. Quadratic equations are more complicated than regular equations. For one thing, they can have two different roots. For instance, x squared minus 1 equals 0 has two solutions, 1 and negative 1. Substitute negative 1 or 1 for x in the equation and you'll see what happens. Either one of those solutions works. As it turns out, the expression of x squared minus 1 splits into open parentheses x minus 1 close parentheses, open parentheses x plus 1 close parentheses, making it easy to see that if x is 1 or negative 1, the expression goes to 0. Though quadratic equations are more complicated than linear equations, there is a simple way to figure out what the roots of a quadratic equation are. It's the famous quadratic formula, which is the crowning achievement of high school algebra class. The formula for finding the roots of a quadratic equation, ax squared plus bx plus c equals 0, is x equals the fraction with the numerator negative b plus or minus the square root of b squared minus 4ac and denominator 2a. The plus sign gives us one root, while the minus sign gives us the other. The quadratic formula has been known for centuries. The 9th century mathematician Al-Khwarizmi knew how to solve almost every quadratic equation, though he didn't seem to consider negative numbers as roots. Not long after that, algebraists learned to accept negative numbers as valid solutions to equations. Imaginary numbers, though, were a little different. Imaginary numbers never appeared in linear equations, but they began to crop up in quadratic ones. Consider the equation x squared plus 1 equals 0. No number seems to solve the equation. Plugging in negative 1, 3, negative 750, 235.23, or any other positive or negative number you could think of doesn't yield the correct answer. The expression simply will not split. Worse yet, when you try to apply the quadratic equation, you get two silly-sounding answers, plus negative 1 and minus negative 1. These expressions don't seem to make any sense. The Indian mathematician Bhaskara wrote in the 12th century that there is no square root of a negative number, for a negative number is not a square. What Bhaskara and others realized was that when you square a positive number, you get a positive number back. 2 times 2 equals 4, for instance. When you square a negative number, you still get a positive number. Negative 2 times negative 2 also equals 4. When you square 0, you get 0. Positive numbers, negative numbers, and 0 all give you non-negative squares, and those 3 possibilities cover the whole number line. This means that there is no number on the number line that gives you a negative number when you square it. The square root of a negative number seemed like a ridiculous concept. Descartes thought that these numbers were even worse than negative numbers. He came up with a scornful name for the square roots of negatives, imaginary numbers. The name stuck, and eventually the symbol for the square root of negative 1 became I. Algebraists loved I. Almost everyone else hated it. It was wonderful for solving polynomials, expressions like x cubed plus 3x plus 1 that have x raised to various powers. In fact, once you allow I into the realm of numbers, every polynomial becomes solvable. X squared plus 1 suddenly splits into open parentheses x minus I close parentheses, open parentheses x plus I close parentheses. The roots of the equation are plus I and negative I. Cubic expressions like x cubed minus x squared plus x minus 1 split 3 ways, such as open parentheses, x minus 1, close parentheses, open parentheses, x plus I, close parentheses, open parentheses, x minus I, close parentheses. Quartic expressions, ones with a leading x to the fourth power term, always split into four terms, and quintics, ones with a leading x to the fifth power term, split five ways. All polynomials of degree n, those that have a leading term of x to the nth power, split into n distinct terms. This is the fundamental theorem of algebra. As early as the 16th century, mathematicians were using numbers with I included, the so-called complex numbers, to solve cubic and quartic polynomials. And while many mathematicians saw the complex numbers as a convenient fiction, others saw God. Leibniz thought that I was a bizarre mix between existence and non-existence, something like a cross between 1, God, and 0, void, in his binary scheme. Leibniz likened I to the Holy Spirit. Both have an ethereal and barely substantial existence. But even Leibniz didn't realize that I would finally reveal the relationship between 0 and infinity. It would take two important developments in mathematics before the true link was uncovered. Point and counterpoint. One will then see the simplicity with which these concepts lead to properties already known and to an infinity of others which ordinary geometry does not seem to touch easily. Jean-Victor Poncelet. The first development, projective geometry, was born in the turmoil of war. In the 1700s, France, England, Austria, Prussia, Spain, the Netherlands, and other countries were vying for power. Alliances formed and broke over and over again. New territorial disputes erupted over colonies, and countries struggled to dominate trade to and from the New World. France, England, and other countries skirmished throughout the first half of the 18th century, and roughly a quarter century after Newton died, a full-scale war erupted. France, Austria, Spain, and Russia fought England and Prussia for 9 years. In 1763, the French capitulated and the 7 Years' War was over. 2 years of fighting occurred before war was officially declared. The victory made England the preeminent power in the world, but it came at a great cost. Both France and England were exhausted and in debt, and they would both suffer the consequences, revolutions. A little more than a decade after the end of the 7 Years' War, the American Revolution began. The revolt would strip England of its richest colony. In 1789, just as George Washington was sworn into office in the newly founded United States, the French Revolution began. 4 years later, the revolutionaries removed the French king's head. A mathematician, Gaspard Monge, signed the revolutionary government's record of the king's execution. Monge was a consummate geometer, specializing in three-dimensional geometry. He was responsible for the way architects and engineers draw buildings and machines. They project the design onto a vertical plane and a horizontal plane, preserving all the information needed to reconstruct the object. Monge's work was so important to the military that much of it was made into a state secret by the revolutionary government and by the Napoleonic government that succeeded it soon afterward. Jean-Victor Poncelet was a student of Monge's who learned about three-dimensional geometry as he trained to become an engineer for Napoleon's army. Unluckily for Poncelet, he entered the army just as Napoleon set off for Moscow in 1812. While retreating from Moscow, Napoleon's army was whittled down to almost nothing by a harsh winter and an equally harsh Russian army. At the Battle of Krasnoy, Poncelet was left for dead on the battlefield. Still alive, he was captured by the Russians. Moldering in a Russian prison, Poncelet founded a new discipline, projective geometry. Poncelet's mathematics was the culmination of the work begun by the artists and architects of the 15th century, like Filippo Brunelleschi and Leonardo da Vinci, who discovered how to draw realistically in perspective. When parallel lines converge at the vanishing point in a painting, observers are tricked into believing that the lines never meet. Squares on the floor become trapezoids in a painting. Everything gets gently distorted, but it looks perfectly natural to the viewer. This is the property of an infinitely distant point, a zero at infinity. Johannes Kepler, the man who discovered that planets travel in ellipses, took this idea, the infinitely distant point, one step further. Ellipses have two centers or foci. The more elongated the ellipse, the farther apart these foci are, and all ellipses have the same property. If you had a mirror in the shape of an ellipse and you placed a light bulb at one focus, all the beams of light would converge at the other focus, no matter how stretched out the ellipses are. In his mind, Kepler stretched an ellipses out more and more, dragging one focus farther and farther away. Then Kepler imagined that the second focus was infinitely far away. The second focus was a point at infinity. All of a sudden, the ellipse becomes a parabola, and all of the lines that converge to a point become parallel lines. A parabola is simply an ellipse with one focus at infinity. You can see this very nicely with a flashlight. Go into a dark room, stand next to a wall, and point the flashlight directly at it. You will get a nice round circle of light projected on the wall. Now, slowly tilt the flashlight upward. You will see the circle stretch out into an ellipse that gets longer and longer as you increase the tilt. All of a sudden, the ellipse opens up and becomes a parabola. Thus, Kepler's point at infinity proved that parabolas and ellipses are actually the same thing. This was the beginning of the discipline of projective geometry, where mathematicians look at the shadows and projections of geometric figures to uncover hidden truths even more powerful than the equivalence of parabolas and ellipses. However, it all depended upon accepting a point at infinity. Gérard Desargues, a 17th-century French architect, was one of the early pioneers of projective geometry. He used the point at infinity to prove a number of important new theorems, but Desargues' colleagues couldn't understand his terminology and concluded that Desargues was nuts. Though a few mathematicians like Blaise Pascal picked up on Desargues' work, it was forgotten. None of this mattered to Jean-Victor Poncelet. As Monge's student, Poncelet had learned the technique of projecting diagrams onto two planes, and as a prisoner of war he had a lot of spare time on his hands. He used his stay in prison to reinvent the concept of a point at infinity, and combining it with Monge's work, he became the first true projective geometer. Upon his return from Russia, carrying a Russian abacus, by then an archaic oddity, he raised the discipline to a high art. However, Poncelet had no idea that projective geometry would reveal the mysterious nature of zero, because the second important advance, the complex plane, was still needed. We must turn to Germany for this piece of the puzzle. Carl Friedrich Gauss, born in 1777, was a German prodigy, and he began his mathematical career with an investigation of imaginary numbers. His doctoral thesis was a proof of the fundamental theorem of algebra, proving that a polynomial of degree n, a quadratic has degree 2, a cubic has degree 3, a quartic has degree 4, and so on, has n roots. This is only true if you accept imaginary numbers as well as real numbers. Throughout his life, Gauss worked on an incredible variety of topics. His work on curvature would become a key component of Einstein's general theory of relativity, but it was Gauss's way of graphing complex numbers that revealed a whole new structure in mathematics. In the 1830s, Gauss realized that each complex number, numbers that have real and imaginary parts like 1 minus 2i, can be displayed on a Cartesian grid. The horizontal axis represents the real part of the complex number, while the vertical axis represents the imaginary part. This simple construction, called the complex plane, revealed a lot about the way numbers work. Take, for example, the number I. The angle between I and the x-axis is 90 degrees. What happens when you square I? Well, by definition, I squared equals -1, a point whose angle is 180 degrees from the x-axis. The angle has doubled. The number I cubed is equal to -I, 270 degrees from the x-axis. The angle has tripled. The number I to the fourth equals 1. We have gone around 360 degrees, exactly 4 times the original angle. This is not a coincidence. Take any complex number and measure its angle. Raising a number to the nth power multiplies its angle by n. And as you keep raising the number to get higher and higher powers, the number will spiral inward or outward depending on whether the number is on the inside or on the outside of the unit circle, a circle centered at the origin with radius 1. Multiplication and exponentiation in the complex plane became geometric ideas. You could actually see them happening. This was the second big advance. The person who combined these two ideas was a student of Gauss's, Georg Friedrich Bernhard Riemann. Riemann merged projective geometry with the complex numbers, and all of a sudden lines became circles, circles became lines, and 0 and infinity became the poles on a globe full of numbers. Riemann imagined a translucent ball sitting atop the complex plane, with the south pole of the ball touching 0. If there were a tiny light at the north pole of the ball, any figures that are marked on the ball would cast shadows on the plane below. The shadow of the equator would be a circle around the origin. The shadow of the southern hemisphere is inside the circle, and the shadow of the northern hemisphere is outside. The origin, 0, corresponds to the south pole. Every point on the ball has a shadow on the complex plane. In a sense, every point on the ball is equivalent to its shadow on the plane and vice versa. Every circle on the plane is the shadow of a circle on the ball, and a circle on the ball corresponds to a circle on the plane, with one exception. If you've got a circle that goes through the north pole of the ball, the shadow is no longer a circle, it is a line. The North Pole is like the point at infinity that Kepler and Poncelet imagined. Lines on the plane are simply circles on the sphere that go through the North Pole, the point at infinity. Once Riemann saw that the complex plane, with a point at infinity, was the same thing as a sphere, mathematicians could see multiplication, division, and other more difficult operations by analyzing the way the sphere deformed and rotated. For instance, multiplying by the number I was equivalent to spinning the sphere 90 degrees clockwise. If you take a number x and replace it with open parentheses x minus 1 close parentheses divided by open parentheses x plus 1 close parentheses, that is equivalent to rotating the whole globe by 90 degrees so that the north and south poles lie on the equator. Most interesting of all, if you take a number x and replace it with its reciprocal, 1 divided by x, that is equivalent to flipping the sphere upside down and reflecting it in a mirror. The North Pole becomes the South Pole, and the South Pole becomes the North Pole. 0 becomes infinity, and infinity becomes 0. It's all built into the geometry of the sphere. 1 divided by 0 equals infinity, and 1 divided by infinity equals 0. Infinity and 0 are simply opposite poles on the Riemann sphere, and they can switch places in a blink, and they have equal and opposite powers. Take all of the numbers in the complex plane and multiply them by 2. That is like putting your hands on the South Pole and stretching a rubber cover on the sphere away from the South Pole and toward the North Pole. Multiplying by 1/2 has the opposite effect. It is like stretching the rubber cover away from the North Pole and toward the South Pole. Multiplying by infinity is like sticking a needle in the South Pole. The rubber sheet all flings upward toward the North Pole. Anything times infinity is infinity. Multiplying by 0 is like sticking a needle on the North Pole and everything winds up at 0. Anything times 0 is 0. Infinity and 0 are equal and opposite and equally destructive. 0 and infinity are eternally locked in a struggle to engulf all the numbers. Like a Manichaean nightmare, the two sit on opposite poles of the number sphere, sucking numbers in like tiny black holes. Take any number on the plane. For the sake of argument, we'll choose I divided by 2. Square it, cube it, raise it to the 4th power, the 5th, the 6th, the 7th. Keep multiplying. It slowly spirals toward 0 like water down a drain. What happens to 2i? The exact opposite. Square it, cube it, raise it to the 4th power, it spirals outward. But on the number sphere, the two curves are duplicates of each other. They are mirror images. All numbers in the complex plane suffer this fate. They are drawn inexorably toward 0 or toward infinity. The only numbers that escape are the ones that are equally distant from the two rivals, the numbers on the equator like 1, -1, and I. These numbers, pulled by the tug of both 0 and infinity, spiral around on the equator forever and ever, never able to escape the grasp of either. You can see this on your calculator. Enter a number, any number, square it again, do it again and again. The number will quickly zoom toward infinity or toward 0, except if you entered 1 or -1 to begin with. There is no escape. The infinite zero. My theory stands as firm as a rock. Every arrow directed against it will return quickly to its archer. How do I know this? I have studied it. I have followed its roots, so to speak, to the first infallible cause of all created things. Georg Cantor. Infinity was no longer mystical. It became an ordinary number. It was a specimen impaled on a pin, ready for study, and mathematicians were quick to analyze it. But in the deepest infinity, nestled within the vast continuum of numbers, 0 kept appearing. Most appalling of all, infinity itself can be a 0. In the old days, before Riemann saw that the complex plane was really a sphere, functions like 1 divided by x would stump mathematicians. When x goes to 0, 1 divided by x gets bigger and bigger and bigger and finally just blows up and goes off to infinity. Riemann made it perfectly acceptable to go off to infinity, since infinity is just a point on the sphere like any other point. It was no longer something to be feared. In fact, mathematicians started analyzing and classifying the points where a function blows up, singularities. The curve 1 divided by x has a singularity at the point x equals 0, a very simple sort of singularity that mathematicians dubbed a pole. There are other types of singularities as well. For instance, the curve sine (open parentheses 1 divided by x close parentheses) has an essential singularity at x equals 0. Essential singularities are weird beasts. Near a singularity of this sort, a curve goes absolutely berserk. It oscillates up and down faster and faster as it approaches the singularity, whipping from positive to negative and back again. In even the tiniest neighborhood around the singularity, the curve takes on almost every conceivable value over and over and over again. Yet as weird as these singularities behave, they were no longer mysterious to mathematicians who were learning to dissect the infinite. The master anatomist of the infinite was Georg Cantor. Though he was born in Russia in 1845, Cantor spent most of his life in Germany, and it was in Germany, the land of Gauss and of Riemann, where infinity's secrets were revealed. Unfortunately, Germany was also the land of Leopold Kronecker, the mathematician who would hound Cantor into a mental institution. Underneath Cantor's conflict with Kronecker was a vision of the infinite, a vision that can be described with a simple puzzle. Imagine that there is a large stadium filled with people and you want to know whether there are more seats, more people, or an equal number of both. You could count the number of people and count the number of seats and then compare the two numbers, but that would take a lot of time. There's a much cleverer way. Just ask everyone to sit down in a seat. If there are empty seats, then there are too few people. If people remain standing, there are too few seats. If every seat is filled and nobody is left standing, then the number of people and seats are equal. Cantor generalized this trick. He said that two sets of numbers are the same size when one set of numbers can sit on top of another set of numbers, one to a customer, with none left over. For instance, consider the set open brace 1, 2, 3, close brace. It is the same size as open brace 2, 4, 6, close brace because we can make a perfect seating pattern where all the numbers are seated and all the seats are occupied. 1 to 2, 2 to 4, and 3 to 6. But it's not the same size as open brace 2, 4, 6, 8, close brace. 1 to 2, 2 to 4, 3 to 6, but nothing to 8, because 8 is an empty seat. Things get really interesting when you get to infinite sets. Consider the set of whole numbers, open brace 0, 1, 2, 3, 4, 5, and so forth and so on, close brace. Obviously, this set is equal to itself. We can just have each number sit upon itself. 0 to 0, 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, and so forth and so on. There's no trick here. Every set is obviously equal to itself. But what happens when we start removing numbers from the set? For instance, what happens when we remove 0? Oddly enough, removing 0 doesn't change the size of the set at all. By rearranging the seating pattern slightly, we can ensure that everybody has a seat and all the seats are still taken. 1 to 0, 2 to 1, 3 to 2, 4 to 3, 5 to 4, 6 to 5, and so forth and so on. The set is the same size even though we've removed something from it. In fact, we can remove an infinite number of elements from the set of whole numbers. We can delete the odd numbers, for example, and the size of the set remains unchanged. Everybody still has a seat and every seat is filled. 0 to 0, 2 to 1, 4 to 2, 6 to 3, 8 to 4, 10 to 5, and so forth. This is the definition of the infinite. It is something that can stay the same size even when you subtract from it. The even numbers, the odd numbers, the whole numbers, the integers, all of these sets were the same size, a size that Cantor soon dubbed Aleph Not, named after the first letter of the Hebrew alphabet. Since these numbers are the same size as the counting numbers, any set of size Aleph Not is called countable. Of course, you couldn't really count them unless you had an infinite amount of time on your hands. Even the rational numbers, the set of numbers that can be written as a divided by b for integers a and b, were countable. By a clever way of assigning rational numbers to their proper seats, Cantor showed that the rationals were an Aleph Not sized set. But as Pythagoras knew, the rationals aren't everything under the sun. Both the rationals and irrationals make up the so-called real numbers. Cantor discovered that the set of real numbers is much, much bigger than the rationals. His proof was a very simple one. Imagine that we've already got a perfect seating plan for the real numbers. Every real number has a seat and every seat is filled. That means we can make a list of seats showing a seat's number along with the real number that is sitting in it. For instance, our list might sound like the following. Seat 1, real number 0.3125123. Seat 2, real number 0.7843122. Seat 3, real number 0.9999999. Seat 4, real number 0.6261000. Seat 5, real number 0.3671123, etc., etc. The trick came when Cantor created a real number that was not on the list. Look at the first digit of the first number on the list. In our example, it's a 3. If our new number were equal to the first number on the list, it would also have a first digit of 3. But we can easily prevent that from happening. Let's just say that our new number has a first digit of 2. Since the first number on the list starts with a 3 and our new number starts with a 2, we know that the two numbers are different. This is not strictly true. The number 0.30000 is equal to 0.2999999, since there are two ways to write that many rational numbers. But this is a minor point that is easily overcome. For the sake of clarity, we'll ignore that exception. On to the second number. How can we make sure that our new number is different from the second number on the list? Well, we've already determined the first digit in our new number, so we can't pull exactly the same trick, but we can do something just as good. The second number on the list has an 8 for its second digit. If our new number has a 7 for its second digit, we can ensure that our new number is not the same as the second number on the list. Their second digits don't match, so they aren't the same thing. We do the same thing on down the list. Look at the third digit of the third number and change it. Look at the fourth digit on the fourth number and change it, and so on. Seat 1, real number 0.3125123. Our new number's first digit is 2, different from 3. Seat 2, 0.7843122. Our new number's second digit is 7, different from 8. Seat 3, 0.9999999. Our new number's third digit is 8, different from 9. Seat 4, 0.6261000. Our new number's fourth digit is 0, different from 1. Seat 5, 0.3671123. Our new number's fifth digit is 0, different from 1, etc., etc., etc. Yielding a new number, 0.27800, that is different from the first number, their first digits don't match, is different from the second number, their second digits don't match, is different from the third number, their third digits don't match, is different from the fourth number, their fourth digits don't match, and so forth. Going down the diagonal in this way, we create a new number. This process ensures that it's different from all the other numbers on the list. If it is different from all the numbers on the list, it can't be on the list, but we already assumed our list contains all real numbers. After all, it was a perfect seating list. This is a contradiction. The perfect seating list cannot exist. The real numbers are a bigger infinity than the rational numbers. The term for this type of infinity was Aleph 1, the first uncountable infinity. Technically, the term for the infinity of the real line was C, or the continuum infinity. For years, mathematicians struggled to determine whether C was indeed Aleph 1. In 1963, a mathematician, Paul Cohen, proved that this puzzle, the so-called continuum hypothesis, was neither provable nor disprovable, thanks to Gödel's incompleteness theorem. Today, most mathematicians accept the continuum hypothesis as true, though some study non-Cantorian transfinite numbers where the continuum hypothesis is taken to be false. In Cantor's mind, there were an infinite number of infinities, the transfinite numbers, each nested in the other. Aleph naught is smaller than Aleph 1, which is smaller than Aleph 2, which is smaller than Aleph 3, and so forth. At the top of the chain sits the ultimate infinity that engulfs all other infinities, God, the infinity that defies all comprehension. Unfortunately for Cantor, not everyone had the same vision of God. Leopold Kronecker was an eminent professor at the University of Berlin and one of Cantor's teachers. Kronecker believed that God would never allow such ugliness as the irrationals, much less an ever-increasing set of Russian doll infinities. The integers represented the purity of God, while the irrationals and other bizarre sets of numbers were abominations, figments of the imperfect human mind. Cantor's transfinite numbers were the worst of the lot. Disgusted with Cantor, Kronecker launched vitriolic attacks against Cantor's work and made it extremely difficult for him to publish papers. When Cantor applied for a position at the University of Berlin in 1883, he was rejected. He had to settle for a professorship at the much less prestigious University of Halle instead. Kronecker, who was influential at Berlin, was likely to blame. The same year he wrote a defense against Kronecker's attacks. Then, in 1884, the depressed Cantor had his first mental breakdown. It would be little comfort to Cantor that his work was the foundation of a whole new branch of mathematics, set theory. Using set theory, mathematicians would not only create the numbers we know out of nothing at all, they would create numbers that were previously unheard of, infinite infinities that can be added to, multiplied with, subtracted from, and divided by other infinities, just like ordinary numbers. Cantor opened up a whole new universe of numbers. The German mathematician David Hilbert would say, "No one shall expel us from the paradise which Cantor has created for us." But it was too late for Cantor. Cantor was in and out of mental institutions for the remainder of his life, and he died in the mental hospital at Halle in 1918. In the battle between Kronecker and Cantor, Cantor would ultimately prevail. Cantor's theory would show that Kronecker's precious integers and even the rational numbers were nothing at all. They were an infinite zero. There are an infinite number of rationals, and between any two numbers you choose, no matter how close together, there are still an infinite number of rationals. They are everywhere. But Cantor's hierarchy of infinities would tell a different tale. It would show just how little space the rational numbers take up on the number line. It takes a clever trick to do such an intricate calculation. Irregularly shaped objects can be very difficult to measure. For instance, imagine that you've got a stain on your wood floor. How much area does the stain take up? It's not so obvious. If the stain were shaped like a circle or like a square or a triangle, it would be easy to figure out. Just take a ruler and measure its radius or its height and base. But there's no formula for figuring out the area of an amoeba-shaped mess. However, there is another way. Take any rectangular carpet and place it on top of the stain. If the carpet covers the stain entirely, we know that the stain is smaller than the carpet. If the carpet is 1 square foot, then the stain must take up less than 1 square foot. If we use smaller carpets, our approximation gets better and better. Perhaps the stain is covered by 5 carpets of size 1/8 square foot. We would then know that the stain takes up at most 5/8 of a square foot, which is less than our approximation with a 1 square foot carpet. As you make the carpet smaller and smaller, the covering gets better and better, and your total carpet area approaches the true size of the stain. In fact, you can define the size of the stain as the limit as your carpets approach 0 size. Let's do the same thing with the rational numbers, but this time our carpets are sets of numbers. For instance, the number 2.5 is covered by a carpet that includes, for example, all the numbers between 2 and 3, a carpet of size 1. Using this sort of carpet to cover the rational numbers has some very odd consequences, as Cantor soon showed, thanks to his seating chart. That seating chart accounts for all the rational numbers. It assigns each of them a seat, so we can count them off one by one in order based on their seat number. Take the first rational number and imagine it on the number line. Let's cover it with a carpet of size 1. Lots of other numbers are covered by that carpet, but we don't have to worry about that. So long as the first number is covered, we are happy. Now take the second number, cover it with a carpet of size 1/2. Take the third number and cover it with a carpet of size 1/4, and so forth. Go on and on to infinity. Since every rational number is on the seating chart, every rational number will eventually be covered by a carpet. What is the total size of the carpets? It's our old friend, the Achilles sum. Adding up the size of the carpets, we see 1 plus 1/2 plus 1/4 plus 1/8 plus, and so forth and so on, plus 1 divided by 2 to the nth goes on to 2 as n goes to infinity. So we can cover the infinite cohorts of rational numbers in the number line with a set of carpets, and the total size of the carpets is 2. This means that the rational numbers take up less than 2 units of space. Just as we did with the stain, let's make the carpet sizes even smaller to get a better approximation of the size of the rationals. Instead of starting with a carpet of size 1, starting with a carpet of size 1/2 makes the total size of the carpets equal to 1. The rational numbers take up less than 1 unit of space in total. If we start off with an initial carpet that has size 1/1000th, all the carpets in total take up less than 1/500th unit of space. All the rational numbers take up less room than 1/500th unit. If we start with a carpet the size of half an atom, we can cover all the rational numbers on the number line with carpets that in total take up less room than an atom. Yet even those tiny carpets, all of which can fit in the span of an atom, cover all of the rational numbers. We can get smaller and smaller, as small as we want. We can cover the rationals with carpets that, summed together, fit in the size of half an atom, or a neutron, or a quark, or as small as we can possibly imagine. How big are the rational numbers then? We defined size as a limit, the sum of the carpets as the individual sizes go to 0. Yet at the same time, we saw that as the carpets get smaller and smaller, the sum of the cover gets tinier and tinier, smaller than an atom or a quark or a millionth billionth part of a quark, and we can still cover the rationals. What is the limit of something that gets smaller and smaller and smaller without stopping? 0. How big are the rational numbers? They take up no space at all. It's a tough concept to swallow, but it's true. Even though there are rational numbers everywhere on the number line, they take up no space at all. If we were to throw a dart at the number line, it would never hit a rational number. Never. And though the rationals are tiny, the irrationals aren't. Since we can't make a seating chart and cover them one by one, There will always be uncovered irrationals left over. Kronecker hated the irrationals, but they take up all the space in the number line. The infinity of the rationals is nothing more than a zero. Chapter 7. Absolute Zeros, the Physics of Zero. Sensible mathematics involves neglecting a quantity when it is small, not neglecting it because it is infinitely great and you do not want it. P.A.M. Dirac. It was finally unmistakable. Infinity and zero are inseparable and are essential to mathematics. Mathematicians had no choice but to learn to live with them. For physicists, however, zero and infinity seemed utterly irrelevant to the workings of the universe. Adding infinities and dividing by zeros might be a part of mathematics, but it is not the way of nature. Or so scientists had hoped. As mathematicians were uncovering the connection between zero and infinity, physicists began to encounter zeros in the natural world. Zero crossed over from mathematics to physics. In thermodynamics, a zero became an uncrossable barrier, the coldest temperature possible. In Einstein's theory of general relativity, a zero became a black hole, a monstrous star that swallows entire suns. In quantum mechanics, a zero is responsible for a bizarre source of energy, infinite and ubiquitous, present even in the deepest vacuum, and a phantom force exerted by nothing at all. Zero heat. When you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely, in your thoughts, advanced to the stage of science. William Thomson, Lord Kelvin. The first inescapable zero in physics comes from a law that had been in use for half a century. This law was discovered in 1787 by Jacques-Alexandre Charles, a French physicist already famous for being the first to fly aboard a hydrogen balloon. Charles isn't remembered for his aeronautic stunts, but for the law of nature that bears his name. Charles, like many physicists of his time, was fascinated with the very different properties of gases. Oxygen makes embers burst into flame, while carbon dioxide snuffs them out. Chlorine is green and is deadly. Nitrous oxide is colorless and makes people giggle. Yet all these gases have very basic properties in common. Heat them up and they expand, cool them down and they contract. Charles discovered that this behavior is extremely regular and predictable. Take an equal volume of any two different gases and put them in identical balloons. Heat them up by the same amount and they expand by the same amount. Cool them down together and they contract in unison. Furthermore, for each degree up or down you go, you gain or lose a certain percentage of the volume. Charles's law describes the relationship of the volume of a gas to its temperature. In the 1850s, however, William Thomson, a British physicist, noticed something odd about Charles's law, the specter of zero. Lower the temperature and the volume of the balloons gets smaller and smaller. Keep lowering it at a steady pace and the balloons keep shrinking at a constant rate, but they cannot go on shrinking forever. There is a point at which gas, in theory, takes up no space at all. Charles's law says that a balloon of gas must shrink to zero space. Of course, zero space is the smallest possible volume. When a gas reaches this point, it takes up no space at all. It certainly can't take up negative space. If the volume of a gas is related to its temperature, a minimum volume means that there is a minimum temperature. A gas cannot keep getting colder and colder indefinitely. When you can't shrink the balloon any further, you can't lower the temperature any further. This is absolute zero. It is the lowest temperature possible, a little more than 273 degrees Celsius below the freezing point of water. Thomson is better known as Lord Kelvin, and it is for Kelvin that the universal temperature scale is named. In the centigrade scale, 0 degrees is the freezing point of water. In the Kelvin scale, 0 degrees is absolute zero. Absolute zero is the state where a container of gas has been drained of all of its energy. This is, in actuality, an unattainable goal. You can never cool an object to absolute zero. You can get very close. Thanks to laser cooling, physicists can chill atoms to a few millionths of a degree above the ultimate coldness. However, everything in the universe is conspiring to stop you from actually reaching absolute zero. This is because any object that has energy is bouncing around and radiating light. For instance, people are made up of molecules of water and a few organic contaminants. All of these atoms are wiggling about in space. The higher the temperature, the faster the atoms wiggle. These wiggling atoms bump into one another, getting their neighbors to wiggle as well. Say you are trying to cool a banana to absolute zero. To get rid of all of the energy in the banana, you've got to stop its atoms from moving around. You have to put it in a box and cool it down. However, the box the banana is in is made of atoms too. The box's atoms are wiggling around, and they will bump the banana's atoms and set them in motion again. Even if you get the banana to float in a perfect vacuum in the center of the box, you can't stop the wiggling entirely because dancing particles give off light. Light is constantly coming off of the box and striking the banana, getting the banana's molecules to move again. All of the atoms that make up a tweezer, a refrigerator coil, and a tub of liquid nitrogen are moving and radiating, so the banana is constantly absorbing energy from the wiggles and radiation of the box it is in, from the tweezers you use to manipulate the banana, and from the refrigerator coil you use to cool it down. You cannot shield the banana from the box or the tweezer or the coil. The shield, too, is wiggling and radiating. Every object is influenced by the environment it's in, so it's impossible to cool anything in the universe, a banana, an ice cube, a dollop of liquid helium, to absolute zero. It is an unbreakable barrier. Absolute zero was a discovery that had a very different flavor from Newton's laws. Newton's equations gave physicists power. They could predict the orbits of the planets and the motion of objects with great accuracy. On the other hand, Kelvin's discovery of absolute zero told physicists what they couldn't do. They couldn't ever reach absolute zero. This barrier was disappointing news to the physics world, but it was the beginning of a new branch of physics, thermodynamics. Thermodynamics is the study of the way heat and energy behave. Like Kelvin's discovery of absolute zero, the laws of thermodynamics erected impenetrable barriers that no scientist can ever cross, no matter how hard they try. For instance, thermodynamics tells you that it is impossible to create a perpetual motion machine. Avid inventors tend to swamp physics departments and science magazines with blueprints for incredible machines, machines that eternally generate power without any source of energy. However, the laws of thermodynamics state that it is impossible to create such a machine. It is another task that cannot be done no matter how hard you try. It is impossible even to get a machine to run without wasting energy, frittering some of its power into the universe as heat. Thermodynamics is worse than a casino. You can't win no matter how much you work at it. You can't even break even. From thermodynamics came the discipline of statistical mechanics. By looking at the collective motion of groups of atoms, physicists could predict the way matter behaves. For instance, the statistical description of gas explains Charles's law. As you raise the temperature of a gas, the average molecule moves faster and smashes harder into the walls of its container. The gas pushes harder on the walls. The pressure goes up. Statistical mechanics, the theory of wiggles, explains some of the basic properties of matter, and it even seemed to explain the nature of light itself. The nature of light was a problem that had consumed scientists for centuries. Isaac Newton believed that light was composed of little particles that flowed from every bright object. Over time, though, scientists came to believe that light was not, in fact, a particle, but a wave. In 1801, a British scientist discovered that light interferes with itself, apparently putting the matter to rest once and for all. Interference happens with all sorts of waves. When you drop a stone into a pond, you create circular ripples in the water, waves. The water bobs up and down, and crests and troughs spread outward in a circular pattern. If you drop two stones at the same time, the ripples interfere with one another. You can see this more clearly if you dip two oscillating pistons into a tub of water. When a crest from one piston runs into a trough from the other, the two cancel out. If you look carefully at the pattern of ripples, you can see lines of still, wave-free water. The same thing is true of light. If light shines through two small slits, there are areas that are dark, wave-free. You can see a related effect at home. Hold your fingers together. You should have tiny gaps where some light can get through. Gaze through one of those gaps at a light bulb, and you'll see faint, dark lines, especially near the top and bottom of the gap. These lines, too, are due to the wave-like nature of light. Waves interfere in this way, particles do not. Thus, the phenomenon of interference seemed to settle the question of light's nature once and for all. Physicists concluded that light was not a particle, but a wave of electric and magnetic fields. This was the state of the art in the mid-1800s, and it seemed to mesh perfectly with the laws of statistical mechanics. Statistical mechanics tells you how the molecules of matter wiggle. The wave theory of light implied that these molecular wiggles somehow caused ripples of radiation, light waves. Better yet, the hotter the object is, the faster its molecules move. At the same time, the hotter the object, the more energetic the ripples of light it sends out. This works out perfectly. With light, the faster the wave bobs up and down, the higher its frequency, the more energy it has. Also, the higher its frequency, the smaller its wavelength, the distance between two wave crests. Indeed, one of the most important thermodynamic laws, the so-called Stefan-Boltzmann equation, seems to tie the wiggles of molecules to the wiggles of light. It relates the temperature of an object to the total amount of light energy it radiates. This was the biggest victory for statistical mechanics and the wave theory of light. The equation states that the radiated energy is proportional to the temperature raised to the fourth power. It not only tells how much radiation an object gives off, but also how hot an object gets when irradiated with a given amount of energy. This is the law that physicists used, along with a passage in the book of Isaiah, to determine that heaven is more than 500 degrees Kelvin. Unfortunately, the victory would not last for long. At the turn of the century, two British physicists tried to use the wiggle theory to solve a simple problem. It was a fairly straightforward calculation. How much light does an empty cavity radiate? Applying the basic equations of statistical mechanics, which tells how the molecules wiggle, and the equations that describe the way electric and magnetic fields interact, which tells how light wiggles, they came up with an equation that describes what wavelengths of light a cavity radiates at a given temperature. The so-called Rayleigh-Jeans law, named after the physicists Lord Rayleigh and Sir James Jeans, worked fairly well. It did a good job of predicting the amount of large wavelength, low-energy light that comes off a hot object. At high energies, though, the equation faltered. The Rayleigh-Jeans law predicted that an object gives off more and more light at smaller and smaller wavelengths, and thus higher and higher energies. Consequently, at realms close to zero wavelength, the object gives off an infinite amount of high-energy light. According to the Rayleigh-Jeans equation, every object is constantly radiating an infinite amount of energy, no matter what its temperature is. Even an ice cube would be radiating enough ultraviolet rays, X-rays, and gamma rays to vaporize everything around. This was the ultraviolet catastrophe. Zero wavelength equals infinite energy. Zero and infinity conspired to break a nice, neat system of laws. Solving this paradox quickly became the leading puzzle in physics. Rayleigh and Jeans had done nothing wrong. They used equations that physicists thought were valid, manipulated them in an accepted way, and came out with an answer that didn't reflect the way the world works. Ice cubes don't wipe out civilization with bursts of gamma rays, though following the then accepted rules of physics led inexorably to that conclusion. One of the laws of physics had to be wrong. But which one? The quantum zero, infinite energy. To physicists, vacuum has all particles and forces latent in it. It is a far richer substance than the philosopher's nothing. Sir Martin Rees. The ultraviolet catastrophe led to the quantum revolution. Quantum mechanics got rid of the zero in the classical theory of light, removing the infinite energy that supposedly came from every bit of matter in the universe. However, this was not much of a victory. A zero in quantum mechanics means that the entire universe, including the vacuum, is filled with an infinite amount of energy, the zero-point energy. This in turn leads to the most bizarre zero in the universe, the phantom force of nothing. In 1900, German experimenters tried to shed some light on the ultraviolet catastrophe. By making careful measurements of how much radiation came off objects at various temperatures, they showed that the Rayleigh-Jeans formula was, indeed, failing to predict the true amount of light that comes from objects. A young physicist named Max Planck looked at the new data and within hours came up with a new equation that replaced the Rayleigh-Jeans formula. Not only did Planck's formula explain the new measurements, it solved the ultraviolet catastrophe. The Planck formula did not zoom off to infinity as the wavelength decreased. Instead of having the energy get bigger and bigger as the wavelength goes down, it got smaller and smaller again. Unfortunately, though Planck's formula was correct, its repercussions were more troubling than the ultraviolet catastrophe it solved. The problem arose because the ordinary assumptions of statistical mechanics, the laws of physics, did not lead Planck to his formula. The laws of physics had to change to accommodate the Planck formula. Planck later described what he did as an act of desperation. Nothing less than desperation would compel a physicist to make such a seemingly nonsensical change in the laws of physics. According to Planck, molecules are forbidden to move in most ways. They vibrate only with certain acceptable energies called quanta. It is impossible for molecules to have energies in between these acceptable values. This might not seem like such a strange assumption, but it is not the way the world seems to work. Nature doesn't move in jumps. It would seem silly to have 5-foot-tall people and 6-foot-tall people, but nothing in between. It would be ridiculous if cars drove at 30 miles an hour and 40 miles an hour, but never at 33 or 38 miles an hour. However, a quantum car would behave in exactly this way. You might be driving along at 30 miles an hour, but when you step on the gas, all of a sudden you would instantly, pop, be driving 40 miles an hour. Nothing in between is allowed. So to get from 30 to 40 miles an hour, you have to make a quantum leap. In the same way, quantum people could not grow very easily. They would hover at 4 feet for a number of years, and then, in a fraction of a second, pop, they would be 5 feet tall. The quantum hypothesis violates everything our everyday experience tells us. Even though it doesn't agree with the way nature seems to work, Planck's strange hypothesis that molecular vibrations were quantized led to the correct formula for the frequencies of light that come off an object. Even though physicists quickly realized that Planck's equation was right, they did not accept the quantum hypothesis. It was too bizarre to accept. An unlikely candidate would turn the quantum hypothesis from a peculiarity to an accepted fact. Albert Einstein, a 26-year-old patent clerk, showed the physics world that nature worked in quanta rather than in smooth increments. He would later become the chief opponent of the theory he helped create. Einstein didn't seem like a revolutionary. When Max Planck was turning the physics world on its head, Albert Einstein was scrambling for a job. Out of money, he took a temporary position at the Swiss Patent Office, a far cry from the assistantship at a university that he wanted. By 1904, he was married, had a newborn son, and was laboring in the patent office, hardly the path to greatness. However, in March 1905, he wrote a paper that would eventually earn him the Nobel Prize. This paper, which explained the photoelectric effect, brought quantum mechanics into the mainstream. Once quantum mechanics was accepted, so too would the mysterious powers of zero. The photoelectric effect was discovered in 1887 when the German physicist Heinrich Hertz discovered that a beam of ultraviolet light could cause a plate to spark. Electrons quite simply pop out of the metal when a light shines on it. This phenomenon, causing sparks with a beam of light, was very puzzling to classical physicists. Ultraviolet light is light with a lot of energy, so scientists naturally concluded that it took quite a bit of energy to kick an electron out of an atom. But according to the wave theory of light, there is another way to get high-energy light: make it brighter. A very bright blue light, for instance, might have as much energy as a dim ultraviolet beam. Therefore, a bright blue light should be able to kick electrons out of atoms just as a dim ultraviolet beam can. This simply is not the case, as experiments quickly showed. Even a dim beam of ultraviolet, high-frequency light causes electrons to get knocked out of the metal. However, if you lower the frequency just a little bit beyond a critical threshold, making the light a wee bit too red, the sparking stops all of a sudden. No matter how bright the beam is, if the light is the wrong color, all the electrons in the metal stay put. None of them can escape. That's not the sort of thing a light wave would do. Einstein solved this quandary, the puzzle of the photoelectric effect, but his solution was even more revolutionary than Planck's hypothesis. While Planck proposed that molecules' vibrations were quantized, Einstein proposed that light came in little packets of energy called photons. This idea conflicted with the accepted physics of light because it meant that light was not a wave. On the other hand, if light energy is bundled into little packets, then the photoelectric effect is easy to explain. The light is acting like little bullets that get shot into the metal. When a bullet hits an electron, it gives it a nudge. If the bullet has enough energy, if its frequency is high enough, then it knocks the electron free. On the other hand, if a light particle doesn't have enough energy to nudge the electron out, then the electron stays put. The photon skitters away instead. Einstein's idea explained the photoelectric effect brilliantly. Light is quantized into photons, directly contradicting the wave theory of light that had not been questioned for more than a century. Indeed, it turns out that light has both a wave nature and a particle nature. Though light acts like a particle sometimes, it acts like a wave at other times. In truth, light is neither particle nor wave, but a strange combination of the two. It's a hard concept to grasp. However, this idea is at the heart of the quantum theory. According to quantum theory, everything, light, electrons, protons, small dogs, have both wave-like and particle-like properties. But if objects are particles and waves at the same time, what on earth could they be? Mathematicians know how to describe them. They are wave functions, solutions to a differential equation called the Schrödinger equation. Unfortunately, this mathematical description has no intuitive meaning. It is all but impossible to visualize what these wave functions are. Worse yet, as physicists discovered the intricacies of quantum mechanics, stranger and stranger things began to appear. Perhaps the weirdest of all is caused by a zero in the equations of quantum mechanics, the zero-point energy. This strange force is woven into the mathematical equations of the quantum universe. In the mid-1920s, a German physicist, Werner Heisenberg, saw that these equations had a shocking consequence: uncertainty. The force of nothing is caused by the Heisenberg uncertainty principle. The concept of uncertainty pertains to scientists' ability to describe the properties of a particle. For instance, if we want to find a particular particle, we need to determine the particle's position and velocity, where it is, and how fast it is going. Heisenberg's uncertainty principle tells us that we can't do even this simple act. No matter how hard we try, we cannot measure a particle's position and its velocity with perfect accuracy at the same time. This is because the very act of measuring destroys some of the information we are trying to gather. To measure something, you need to prod it. For instance, imagine that you are measuring the length of a pencil. You could run your fingers along it and measure how long it is. However, you'll probably give the pencil a nudge, disturbing the pencil's velocity slightly. A better way would be to place a ruler gently next to the pencil. But in fact, comparing the lengths of the two objects also changes the pencil's speed a tiny bit. You can only look at the pencil when light is bouncing off it. Though the disturbance is very slight, the photons that carry off the pencil nudge it ever so gently, changing the pencil's velocity a tiny bit. No matter what way you think of to measure the pencil, you will give it a tiny nudge in the process. Heisenberg's uncertainty principle shows that there is no possible way to measure the pencil's length or an electron's position and its velocity with perfect accuracy at the same time. In fact, the better you know a particle's position, the less you know about its velocity, and vice versa. If you measure an electron's position with zero error, you know exactly where it is at a given moment. You must have zero information about how fast it is going. And if you know a particle's velocity with infinite precision, zero error, you have infinite error when you measure its position. You know nothing at all about where it is. You can never know both at the same time, and if you have some information about one, you must have some uncertainty about the other. It's another unbreakable law. Heisenberg's uncertainty principle applies to more than just measurements performed by humans. Like the laws of thermodynamics, the principle applies to nature itself. Uncertainty makes the universe seethe with infinite energy. Imagine an extremely tiny volume in space, like a really small box. If we analyze what is going on inside that box, we can make some assumptions. For instance, we know with some precision the position of the particles inside. After all, they can't be outside the box. We know that they are restricted to a certain volume because if they were outside the box, we would not be looking at them. Because we have some information about the particle's position, the Heisenberg uncertainty principle implies that we must have some uncertainty about the particle's velocity, their energy. As we make that box smaller and smaller, we know less and less about the particle's energy. This argument holds everywhere in the universe, in the center of the Earth and in the deepest vacuum of space. This means that in a sufficiently small volume, even in a vacuum, we have some uncertainty about the amount of energy inside. But uncertainty about the energy in a vacuum sounds ridiculous. The vacuum, by definition, has nothing in it, no particles, no light, nothing. Thus, the vacuum should have no energy at all. Yet, according to Heisenberg's principle, we cannot know how much energy there is in a volume of the vacuum at any given time. The energy in a tiny volume of vacuum must be fluctuating constantly. How could the vacuum, which has nothing in it, have any energy at all? The answer comes from another equation, Einstein's famous E equals mc squared. This simple formula relates mass and energy. The mass of an object is equivalent to a certain amount of energy. In fact, particle physicists don't measure the mass of the electron, say in kilograms or pounds or any of the usual units of mass or weight. They say that the electron's rest mass is 0.511 MeV, million electron volts, a lump of energy. The fluctuation in the energy in the vacuum is the same thing as a fluctuation in the amount of mass. Particles are constantly winking in and out of existence, like tiny Cheshire cats. The vacuum is never truly empty. Instead, it is seething with these virtual particles. At every point in space, an infinite number are happily popping up and disappearing. This is the zero-point energy, an infinity in the formulas of quantum theory. Interpreted strictly, the zero-point energy is limitless. According to the equations of quantum mechanics, more power than is stored in all the coal mines, oil fields, and nuclear weapons in the world is sitting in the space inside your toaster. When an equation has an infinity in it, physicists usually assume that there is something wrong. The infinity has no physical meaning. The zero-point energy is no different. Most scientists ignore it completely. They simply pretend that the zero-point energy is zero, even though they know it is infinite. It's a convenient fiction, and it usually doesn't matter. However, sometimes it does. In 1948, two Dutch physicists, Heinrich B.G. Casimir and Dick Polder, first realized that the zero-point energy can't always be ignored. The two scientists were studying the forces between atoms when they realized that their measurements didn't match the forces that had been predicted. In a search for an explanation, Casimir realized that he had felt the force of nothing. The secret to the Casimir force lies with the nature of waves. In ancient Greece, Pythagoras saw the peculiar behavior of waves that traveled up and down a plucked string, how certain notes were allowed and others were forbidden. When Pythagoras strummed a string, the string sounded a clear note, the tone known as the fundamental. When he gently placed his finger in the middle of the string and plucked again, he got another nice clear note, this time 1 octave above the fundamental. 1/3 of the way down yielded another nice tone. But Pythagoras realized that not all notes are allowed. When he placed his finger randomly on the string, he seldom got a clear note. Only certain notes can be played on the string. Most are excluded. Matter waves are not so different from string waves. Just as a guitar string of a given size is not capable of playing every possible note, some waves are forbidden from appearing on the string. Some particle waves are forbidden from being inside a box. Put 2 metal plates close together, for instance, and you can't fit every sort of particle inside. Only those whose waves match the size of the box are allowed in. Casimir realized that the forbidden particle waves would affect the zero-point energy of the vacuum, since particles are everywhere winking in and out of existence. If you put 2 metal plates close together and some of those particles aren't allowed between the plates, then there are more particles on the outside of the plates than on the inside. The undiminished zoo of particles presses on the outside of the plates, and without the full complement on the inside, the plates are crushed together, even in the deepest vacuum. This is the force of the vacuum, a force produced by nothing at all. This is the Casimir effect. Though the Casimir force, a mysterious phantom force exerted by nothing at all, seems like science fiction, it exists. It is a tiny force and very difficult to measure, but in 1995 the physicist Stephen Lamoureux measured the Casimir effect directly. By putting 2 gold-covered plates on a sensitive twist-measuring device, he determined how much force it took to counteract the Casimir force between them. The answer, about the weight of 1 slice of an ant that's been chopped into 30,000 pieces, agreed with Casimir's theory. Lamoureux had measured the force exerted by empty space. The relativistic zero, the black hole. The star, like the Cheshire Cat, fades from view. One leaves behind only its grin, the other only its gravitational attraction. John Wheeler. Zero in quantum mechanics invests the vacuum with infinite energy. A zero in the other great modern theory, relativity, creates another paradox, the infinite nothing of the black hole. Like quantum mechanics, the theory of relativity was born in light. This time it was the speed of light that caused the trouble. Most objects in the universe don't have a speed that every observer can agree on. For instance, imagine a small boy who is throwing stones in all directions. For an observer approaching the boy, the stones seem to be going faster than for an observer who is running away. The velocity of the stones seems to depend on your direction and speed. In the same way, the speed of light should depend on whether you are running toward or running away from the light bulb that's shining on you. In 1887, the American physicists Albert Michelson and Edward Morley tried to measure this effect. They were baffled when they found no difference. The speed of light was the same in every direction. How could this be? Again, it was the young Einstein who had the answer in 1905, and again, very simple assumptions would have enormous consequences. The first assumption Einstein made seems fairly obvious. Einstein stated that if a number of people watch the same phenomenon, say the flight of a raven toward a tree, the laws of physics are the same for each observer. If you compare the notes of a person on the ground and a person on a train moving parallel to the raven, they would disagree about the speed of the raven and the tree. But the eventual outcome of the flight is the same. After a few seconds, the raven arrives at the tree. Both observers agree on the final result, though they might disagree about some of the details. This is the principle of relativity. In the special theory of relativity which we are discussing here, there are restrictions on the kind of motion that is allowed. Each observer must be moving with constant velocity in a straight line. In other words, they can't feel an acceleration. With the general theory of relativity, the restrictions are removed. The second assumption is a little more troubling, especially since it seems to contradict the principle of relativity. Einstein assumed that everybody, no matter at what speed they are traveling, agrees about the speed of light in a vacuum, about 300 million meters per second, a constant denoted by the letter c. If someone shines a flashlight at you, the light rushes at you at a speed of c. It doesn't matter whether the person holding the flashlight is standing still, running toward you, or running away. The beam of light always travels at a speed of c from your point of view and everybody else's. This assumption challenged everything physicists had assumed about the motion of objects. If the raven were acting like a photon, then an observer on the train and the person standing still would have to agree on the value for the raven's speed. That would mean that the two observers would disagree about when the raven meets the tree. Einstein realized that there is one way around this. The flow of time changes depending on an observer's speed. The clock on the train must tick more slowly than the stationary clock. 10 seconds for the observer on the ground might seem like only 5 seconds for somebody on the train. It's the same thing for a person who zooms away at great speed. Every tick of his stopwatch takes more than a second from a stationary observer's point of view. If an astronaut took a 20-year journey, according to his pocket watch, at 9/10 of the speed of light, he would come back to Earth having aged 20 years as expected. But everyone who stayed behind would have aged 46 years. Not only does time change with speed, so do length and mass. As objects speed up, they get shorter and heavier. At 9/10 of the speed of light, for instance, a yardstick would only be 0.44 yards long, and a 1-pound bag of sugar would weigh nearly 2.3 pounds, from a stationary observer's point of view. Of course, this doesn't mean that you would be able to bake more cookies with the same bag of sugar. From the bag's point of view, its weight stays the same. This variability in the flow of time might be hard to believe, but it has been observed. When a subatomic particle travels very fast, it survives longer than expected before it decays because its clock is slow. Also, a very precise clock has been observed to slow down ever so slightly when flown in an airplane at great speed. Einstein's theory works. There was a potential problem, though: zero. When a spaceship approaches the speed of light, time slows down more and more and more. If the ship were to travel at the speed of light, every tick of the clock on board would equal infinite seconds on the ground. In less than a fraction of a second, billions and billions of years would pass. The universe would have already met its ultimate fate and burned itself out. For an astronaut aboard the spaceship, time stops. The flow of time is multiplied by 0. Luckily, it is not so easy to stop time. As the spaceship goes ever faster, time slows down more and more, but at the same time, the spaceship's mass gets greater and greater. It is like pushing a baby carriage where the baby grows and grows. Pretty soon, you are pushing a sumo wrestler. Not so easy. If you manage to push the carriage even faster, the baby becomes as massive as a car, and then a battleship, and then a planet, and then a star, and then a galaxy. As the baby gets more massive, your push has less and less effect. In the same way, you can take a spaceship and accelerate it, getting it closer and closer to the speed of light. But after a while, it gets too massive to push any longer. The spaceship, or for that matter any object with mass, never quite reaches the speed of light. The speed of light is the ultimate speed limit. You cannot reach it, much less exceed it. Nature has defended itself from an unruly zero. However, zero is too powerful even for nature. When Einstein extended the theory of relativity to include gravity, he did not suspect that his new equations, the general theory of relativity, would describe the ultimate zero and the worst infinity of them all, the black hole. Einstein's equations treat time and space as different aspects of the same thing. We are already used to the idea that if you accelerate, you change the way you move through space. You can speed up or slow down. What Einstein's equations showed was that just as acceleration changes the way you move through space, it changes the way you move through time. It can speed up the way time flows or slow it down. Thus, when you accelerate an object, when you subject it to any force, be it gravity or be it the push of a gigantic cosmic elephant, you change its motion through space and through time, through space-time. It's a difficult concept to grasp, but the easiest way to approach space-time is through an analogy. Space and time are like a gigantic rubber sheet. Planets, stars, and everything else sit on that sheet, distorting it slightly. That distortion, the curvature caused by objects sitting on the sheet, is gravity. The more massive the object that is sitting on the sheet, the more the sheet gets distorted, and the larger the dimple around that object. The pull of gravity is just like the tendency of objects to roll into the dimple. The curvature of the rubber sheet is not only a curvature of space, but a curvature of time as well. Just as space gets distorted close to a massive object, time does too. It gets slower and slower as the curvature gets greater and greater. The same thing happens with mass. As you get into greatly curved regions of space, bodies' masses effectively increase, a phenomenon known as mass inflation. This analogy explains the orbits of the planets. Earth is simply rolling around in the dimple that the sun makes in the rubber sheet. Light doesn't go in a straight line, but in a curved path around stars, an effect that the British astronomer Sir Arthur Eddington went on an expedition in 1919 to observe. Eddington measured the position of a star during a solar eclipse and spotted the curvature that Einstein had predicted. Einstein's equations also predicted something much more sinister, the black hole, a star so dense that nothing can escape its grasp, not even light. A black hole begins, like all stars, as a big ball of hot gas, mostly hydrogen. If left to its own devices, a sufficiently large ball of gas would collapse under the weight of its own gravity. It would crush itself into a tiny lump. Luckily for us, stars don't collapse because there is another force at work, nuclear fusion. As a cloud of gas collapses, it gets hotter and denser, and hydrogen atoms slam into one another with increasing force. Eventually, the star gets so hot and dense that the hydrogen atoms stick to one another and fuse, creating helium and releasing large quantities of energy. This energy shoots out from the center of the star, causing it to expand a little bit. During most of its life, a star is in an uneasy equilibrium. The propensity to collapse under its own gravity is balanced by the energy that comes from the fusing hydrogen in its center. This equilibrium cannot last forever. The star has only a limited amount of hydrogen fuel to burn. After a while, the fusion reaction dims and the equilibrium is upset. How long this process takes depends on how big the star is. Ironically, the bigger the star, the more hydrogen it has, the shorter its life because it burns much more violently. The Sun has about 5 billion years of fuel left, but don't let that make you complacent. The Sun's temperature will increase gradually before that, boiling off the oceans and turning Earth into an uninhabitable desert like Venus. We should count ourselves lucky if we have a mere billion years left of life on Earth. After a drawn-out series of death throes, the precise sequence of events depends again on the mass of the star. The star's fusion engine fails and the star begins to collapse under its own gravity. A quantum mechanical law called the Pauli exclusion principle keeps matter from smashing itself into a point. Discovered in the mid-1920s by German physicist Wolfgang Pauli, the exclusion principle states roughly that no two things can be in the same place at the same time. In particular, no two electrons of the same quantum state can be forced into the same spot. In 1933, the Indian physicist Subrahmanyan Chandrasekhar realized that the Pauli exclusion principle had only a limited ability to fight against the squeeze of gravity. As pressure in the star increases, the exclusion principle states that electrons inside must move faster and faster to avoid one another. But there's a speed limit. Electrons cannot move faster than the speed of light, so if you put enough pressure on a lump of matter, electrons cannot move fast enough to stop the matter from collapsing. Chandrasekhar showed that a collapsing star that has about 1.4 times the mass of our Sun will have enough gravity to overwhelm the Pauli exclusion principle. Above this Chandrasekhar limit, a star's gravity will pull on itself so strongly that electrons can't stop its collapse. The force of gravity is so great that the star's electrons give up their struggle once and for all. The electrons smash into the star's protons, creating neutrons. The massive star winds up being a gigantic ball of neutrons, a neutron star. Further calculations showed that when collapsing stars are a little more massive than the Chandrasekhar limit, the pressure of the resulting neutrons, similar to the pressure of electrons, can stave off collapse for a little while. This is what happens in a neutron star. At this point, the star is so dense that every teaspoon weighs hundreds of millions of tons. There is a limit, though, to even the pressure that neutrons can bear. Some astrophysicists believe that a little more squeezing makes the neutrons break down into their component quarks, creating a quark star. But that is the last stronghold. After that, all hell breaks loose. When an extremely massive star collapses, it disappears. The gravitational attraction is so great that physicists know of no force in the universe that can stop its collapse. Not the repulsion of its electrons, not the pressure of neutron against neutron or quark against quark. Nothing. The dying star gets smaller and smaller and smaller, then zero. The star crams itself into zero space. This is a black hole, an object so paradoxical that some scientists believe that black holes can be used to travel faster than light and backward in time. The key to a black hole's strange properties is the way it curves space-time. A black hole takes up no space at all, but it still has mass. Since the black hole has mass, it causes space-time to curve. Normally, this would not cause a problem. As you approach a heavy star, the curvature gets greater and greater, but once you have passed the outer edge of the star itself, the curvature decreases again, bottoming out at the center of the star. In contrast, a black hole is a point. It takes up zero space, so there is no outer edge, no place where space begins to flatten out again. The curvature of space gets greater and greater as you approach a black hole, and it never bottoms out. The curvature goes off to infinity because the black hole takes up zero space. The star has torn a hole in space-time. The zero of a black hole is a singularity, an open wound in the fabric of the universe. This is a very troublesome concept. The smooth, continuous fabric of space-time might have tears in it, and nobody knows quite what happens in the region of those tears. Einstein was so disturbed by the idea of singularities that he denied the existence of black holes. He was wrong. Black holes do exist. However, the singularity of a black hole is so ugly, so dangerous, that nature tries to shield it, preventing anyone from seeing the zero at the center of a black hole and returning to tell the tale. Nature has a cosmic censor. The censor is gravity itself. If you toss a rock upward, it will curve back down, pulled back by the Earth's gravity. But if you throw a rock fast enough, it won't curve back down to Earth. It will zoom out of the Earth's atmosphere and escape the Earth's gravitational pull. This is roughly what NASA does when it sends a spacecraft to Mars. The minimum speed you need to throw the rock to enable it to escape is called, naturally enough, the escape velocity. Black holes are so dense that if you get too close, past the so-called event horizon, the escape velocity is faster than the speed of light. Past the event horizon, the pull of a black hole's gravity is so strong and space is so curved that nothing can escape, not even light. Even though a black hole is a star, none of the light it shines ever escapes past the event horizon. That's why it's black. The only way to view a black hole's singularity is to go beyond the event horizon and see for yourself. However, even if you had an impossibly strong spacesuit that kept you from being stretched into a piece of astronaut spaghetti, you could never tell anybody about what you saw. Once you pass the event horizon, signals you broadcast can't escape the black hole's pull. Neither can you. Traveling beyond the edge of the event horizon is like stepping off the edge of the universe. You will never return. This is the power of the cosmic sensor. Even though nature tries to shield the singularities of black holes, scientists know that black holes exist. In the direction of the constellation Sagittarius, at the very center of our galaxy, sits a supermassive black hole that weighs as much as 2.5 million suns. Astronomers have watched stars dance around an invisible partner. The star's motions reveal the presence of the black hole, even if the black hole is not visible. However, though scientists can detect black holes, they still haven't spotted the zeros at their centers, since the ugly singularities are shielded by the event horizon. This is a good thing. If there were no event horizon, no cosmic sensor that shields the singularity from the rest of the universe, very strange things might happen. In theory, a naked singularity with no event horizon might allow you to travel faster than light or backward in time. This could be done with a structure known as a wormhole. Back in the rubber sheet analogy, a singularity is a point of infinite curvature. It is a hole in the fabric of space and time. Under certain circumstances, that hole can be stretched out. For instance, if a black hole is spinning or has an electric charge, mathematicians have calculated that the singularity is not a point, a pinpoint hole in space-time, but a ring. Physicists have speculated that two of these stretched-out singularities might be linked with a tunnel, a wormhole. A person who travels through a wormhole will emerge at another point in space and perhaps in time. Just as wormholes can, in theory, send you halfway across the universe in the blink of an eye, they can send you backward and forward in time. You might even be able to track down your mother and kill her before she meets your father, preventing you from being born and causing a terrible paradox. A wormhole is a paradox caused by a zero in the equations of general relativity. Nobody truly knows whether or not wormholes exist, but NASA is hoping that they do. Something for nothing? There's no such thing as a free lunch, the second law of thermodynamics. NASA hopes that zero might hold the secret to traveling to distant stars. In 1998, NASA held a symposium entitled Physics for the Third Millennium, where scientists debated the merits of wormholes, warp drives, vacuum energy engines, and other far-out ideas. The problem with space travel is that there is nothing to push against. When you swim through a pool, you push against the water, forcing it backward and pushing you forward. When you walk on the ground, your feet are pushing against the floor, providing the force to drive you forward. In space, there is nothing to push backward. You can paddle all you want, but you'll get nowhere. Rockets bring their own supply of stuff to push against. Rocket fuel burns in the engine and is sent out the back of the rocket, driving the spaceship forward, just as the rush of air out of a balloon sends it flying around the room. But tossing away fuel is an expensive and cumbersome way to go places, and even modern improvements on the chemical engine, such as engines that use electricity to throw stuff out the back of a rocket, are unable to provide the fuel efficiency to send probes to distant stars in a reasonable amount of time. To get even to the nearest star, you would need an enormous amount of fuel to jettison out the back of a rocket, a tremendous waste. Physicist Mark Millis heads NASA's Breakthrough Propulsion Project and hopes to overcome this problem with the physics of zero. Unfortunately, the zeros of black holes, singularities, look like unlikely candidates in the short term. Not only is it extremely difficult to create a naked singularity that a wormhole needs, but it also appears that even a naked singularity will tear space travelers to shreds. In 1998, two physicists from the Hebrew University in Jerusalem showed that even a spinning or charged black hole with a nice ring-shaped singularity will kill an astronaut thanks to mass inflation. As you fall toward the singularity, the black hole's mass appears to grow and grow to infinity. The gravitational tug is so strong that you'd be torn apart in a fraction of a second. Wormholes would be hazardous to your health. Even if the zeros at the center of black holes don't provide an easy way to travel through space, the zero of quantum mechanics provides an alternative. The zero-point energy might be the ultimate fuel. It is here that the mainstream of physics ends and the fringe begins. According to Millis, astronauts might harness the energy in the vacuum to push a spaceship, just as mariners harnessed the wind to drive a frigate. I'm making an analogy to the Casimir effect, where you can push plates together with a noticeable radiation pressure from the vacuum, he says. If there were any way to get asymmetric forces out of that, where you get force in one direction and not the other, you'd get a propulsive force. Unfortunately, so far the Casimir effect seems to be symmetric. Both plates collapse and pull each other together. The action of one has an equal and opposite reaction on the other. But if there were some sort of quantum sail, a one-way mirror that reflected virtual particles on one side but let them pass unhindered through the other, the vacuum energy would push the whole object toward the unreflective half of the sail. Millis admits that nobody has any clue how to do this. There are no theories how to engineer the device, he says sadly. The problem is that the laws of physics say you can't get something for nothing. Just as the frigate lowers the speed of the wind, the quantum sail would have to lower the energy of the vacuum. How can you modify nothing? Harold Puthoff, the director of the Institute for Advanced Studies in Austin, Texas, believes that a quantum sail would simply alter the properties of the vacuum. Puthoff is best known for his 1974 paper in Nature that purported to prove that Uri Geller and other psychics could view objects remotely without their eyes. This conclusion was not in the mainstream of science. The vacuum decays to a slightly lower state, says Puthoff. If so, then quantum sails are just the beginning. It would be possible to make engines that run solely on zero-point energy. Their only drawback would be that the fabric of the universe would fall apart. Slowly. We'd never make a dent. It's like scooping up cupfuls of water from the ocean, says Puthoff. It might also destroy the universe. There is no question that the vacuum has energy. The Casimir force is witness to that fact. But is it possible that the energy of the vacuum is truly the lowest possible energy? If not, danger might be lurking in the vacuum. In 1983, two scientists suggested in Nature that tinkering with the energy of the vacuum might cause the universe to self-destruct. The paper argued that our vacuum might be a false vacuum in an unnaturally energetic state, like a ball perched precariously on the side of a hill. If we give the vacuum a big enough nudge, it might start rolling down the hill, settling into a lower energy state, and we would not be able to stop it. We would release a huge bubble of energy that expands at the speed of light, leaving a vast trail of destruction in its wake. It might be so bad that every one of our atoms would be torn apart during the apocalypse. Luckily, this is an extremely unlikely scenario. Our universe has lasted billions of years, and it's improbable that we are living in such a precarious state. Cosmic ray collisions would probably already have sparked the vacuum with enough energy to cause such a disaster were it possible. This hasn't stopped some believers, physicists included, from picketing high-energy laboratories like Fermilab. They believe that a high-energy collision could cause a spontaneous collapse of the vacuum. Even if those concerns were valid, it seems all but impossible to propel a spaceship with zero-point energy. However, Puthoff believes he has a way to extract energy from the void. In theory, scientists can get energy from the Casimir effect even at absolute zero in the bleakest part of the vacuum of space. Two plates generate heat when they smack together, heat that can be converted to electricity. Alas, the plates have to be pried apart again, which requires more energy than was initially produced. Most scientists believe that this fact kills the idea of making a perpetual motion machine that runs on vacuum energy. But Puthoff thinks he sees several ways around this dilemma. One is to use plasmas instead of plates. A plasma, a gas of charged particles, is just like a metal plate as far as the Casimir effect is concerned. A conducting cylinder-shaped gas would be compressed by the zero-point fluctuations just as plates are forced together. The collapse would heat the plasma, releasing energy. Unlike metal plates, plasmas could be made easily with a bolt of electricity, according to Puthoff, and instead of having to pry the plates apart again, the plasma ash is discarded. Puthoff gingerly claims to have gotten out 30 times more energy with this method than was put in. There's some evidence we've even got a patent, he says. However, Puthoff's device is one in a long line of free energy machines, none of which in the past have withstood scientific scrutiny. It is unlikely that his device to harness the zero-point energy will be any different. According to quantum mechanics and general relativity, the power of zero is infinite, so it's no surprise that people are hoping to tap its potential. But for the time being, it appears that nothing will come of nothing. Chapter 8. 0 hour at ground zero. 0 at the edge of space and time. Alien they seemed to be. No mortal eye could see the intimate welding of their later history. Thomas Hardy, The Convergence of the Twain. Modern physics is a struggle of two titans. General relativity holds sway in the realm of the very, very big, the most massive objects in the universe, such as stars, solar systems, and galaxies. Quantum mechanics rules the domain of the very, very small, atoms and electrons and subatomic particles. It would seem that these two theories could live in harmony together, each dictating the rules of physics for different aspects of the universe. Unfortunately, there are objects that lie in both realms. Black holes are very, very massive, so they are subject to the laws of relativity. At the same time, black holes are very, very tiny, so they are in the domain of quantum mechanics. And, far from agreeing, the two sets of laws clash at the center of a black hole. Zero dwells at the juxtaposition of quantum mechanics and relativity. Zero lives where the two theories meet, and zero causes the two theories to clash. A black hole is a zero in the equations of general relativity. The energy of the vacuum is a zero in the mathematics of quantum theory. The Big Bang, the most puzzling event in the history of the universe, is a zero in both theories. The universe came from nothing, and both theories break down when they try to explain the origin of the cosmos. To understand the Big Bang, physicists must marry quantum theory with relativity. In the past few years, they have begun to succeed, creating a monster theory that explains the quantum mechanical nature of gravity, allowing them to peer at the very creation of our universe. All they had to do was banish zero. The theory of everything is, in truth, a theory of nothing. Zero banished. String theory. The problem is, when we try to calculate all the way down to zero distance, the equation blows up in our face and gives us meaningless answers, things like infinity. This caused a lot of trouble when the theory of quantum electrodynamics first came out. People were getting infinity for every problem they tried to calculate. Richard Feynman. General relativity and quantum mechanics were bound to be incompatible. The universe of general relativity is a smooth rubber sheet. It is continuous and flowing, never sharp, never pointy. Quantum mechanics, on the other hand, describes a jerky and discontinuous universe. What the two theories have in common, and what they clash over, is zero. The infinite zero of a black hole, mass crammed into zero space, curving space infinitely, punches a hole in the smooth rubber sheet. The equations of general relativity cannot deal with the sharpness of zero. In a black hole, space and time are meaningless. Quantum mechanics has a similar problem, a problem related to the zero-point energy. The laws of quantum mechanics treat particles such as the electron as points, that is, they take up no space at all. The electron is a zero-dimensional object, and its very zero-like nature ensures that scientists don't even know the electron's mass or charge. This seems like a silly statement. It has been nearly a century since scientists measured the electron's mass and charge. How could physicists not know something that has been measured? The answer lies with zero. The electron that scientists see in the laboratory, the electron that physicists, chemists, and engineers have known and loved for decades, is an impostor. It is not the true electron. The true electron is hidden in a shroud of particles made up of the zero-point fluctuations, those particles that constantly pop in and out of existence. As an electron sits in the vacuum, it occasionally absorbs or spits out one of these particles, such as a photon. The swarm of particles makes it difficult to get a measurement of the electron's mass and charge because the particles interfere with the measurement, masking the electron's true properties. The true electron is a bit heavier and carries a greater charge than the electron that physicists observe. Scientists might get a better idea of the true mass and charge of the electron if they could get a little closer, if they could invent a tiny device that could get a short distance inside the cloud of particles, they would be able to see more clearly. According to quantum theory, as the measuring device gets past the first few virtual particles on the rim of the cloud, scientists would see the mass and charge of the electron go up. And as the probe gets closer and closer to the electron, it would pass more and more virtual particles, so the observed mass and charge go up and up. As the probe approaches zero distance from the electron, the number of particles it passes goes up to infinity, so the probe's measurements of the mass and charge of the electron also go to infinity. According to the rules of quantum mechanics, the zero-dimensional electron has infinite mass and infinite charge. As with the zero-point energy, scientists learn to ignore the infinite mass and charge of the electron. They don't go all the way to zero distance from the electron when they calculate the electron's true mass and charge. They stop short of zero at an arbitrary distance. Once a scientist chooses a suitably close distance, all the calculations using the true mass and charge agree with one another. This is a process called renormalization. It is what I would call a dippy process, wrote physicist Richard Feynman, even though Feynman won his Nobel Prize for perfecting the art of renormalization. Just as zero punches a hole in the smooth sheet of general relativity, zero smooths and spreads out the sharp point charge of the electron, covering it in a fog. However, since quantum mechanics deals with zero-dimensional particle points such as the electron, technically all particle-particle interactions in quantum theory deal with infinities. They are singularities. When two particles merge, for instance, they meet at a point, a zero-dimensional singularity. This singularity makes no sense in quantum mechanics or in general relativity. Zero is the wrench in the works of both great theories. So physicists simply got rid of it. It is not obvious how to get rid of zero, as zero appears and reappears throughout time and space. Black holes are zero-dimensional, as are particles such as the electron. Electrons and black holes are real things. Physicists can't simply will them away. But scientists can give black holes and electrons an extra dimension. This is the reason for string theory, which was created in the 1970s when physicists began to see the advantages of treating every particle as a vibrating string rather than as a dot. If electrons and black holes are treated as one-dimensional, like a loop of string, instead of as zero-dimensional, like a point, the infinities in general relativity and quantum mechanics miraculously disappear. For instance, the renormalization trouble, the infinite mass and charge of the electron, vanishes. A zero-dimensional electron has an infinite mass and charge because it is a singularity. As you get closer and closer to it, your measurements zoom off to infinity. However, if the electron is a loop of string, the particle is no longer a singularity. This means that the mass and charge don't go off to infinity because you are no longer passing an infinite cloud of particles as you approach the electron. Furthermore, as two particles merge, no longer do they meet at a point-like singularity. They form a nice, smooth, continuous surface in space-time. In string theory, different particles are really the same type of string, just wiggling in different ways. Everything in the universe is made up of these strings, which are about 10 to the minus 33rd centimeters across. Comparing the size of a string to the size of a neutron is like comparing the size of a neutron to the size of our solar system. From the perspective of beings as large as we are, the loops look like points because they are so tiny. Distances and times smaller than the size of the loops no longer matter. They don't make any physical sense. In string theory, zero has been banished from the universe. There is no such thing as zero distance or zero time. This solves all the infinity problems of quantum mechanics. Banishing zero also solves the infinity problems in general relativity. If you imagine a black hole as a string, no longer do objects fall through a rip in the fabric of space-time. Instead, a particle loop approaching a black hole loop stretches out and touches the black hole. The two loops tremble, tear, and form one loop, a slightly more massive black hole. Some theorists believe that the act of merging a particle to a black hole creates bizarre particles such as tachyons, particles with imaginary mass that travel backward in time and move faster than light. Such particles might be admissible in certain versions of string theory. Removing zero from the universe might seem like a drastic step, but strings are much more tractable than dots. By eliminating zero, string theory smooths out the discontinuous particle-like nature of quantum mechanics and mends the gashes torn in general relativity by black holes. With these problems patched over, the two theories are no longer incompatible. Physicists began to think that string theory would unify quantum mechanics with relativity. They believed that it would lead to the theory of quantum gravity, the theory of everything that explains every phenomenon in the universe. However, string theory had some problems. For one thing, it required 10 dimensions to work. For most people, 4 dimensions are one too many. It is easy to see 3 of them. Left, right, front, back, and up, down represent the 3 dimensions we can move in. The 4th arrived when Einstein showed that time was similar to these 3 dimensions. We are constantly moving through time like a car that's speeding down a highway. The theory of relativity shows that just as we can change how quickly we rush down a highway, we can change the rate at which we move through time. The faster we go through space, the quicker we move through time. To understand Einstein's universe, we have to accept the idea that time is the 4th dimension. 4 is reasonable, but 10? We can measure 4 dimensions, but what happened to the other 6 dimensions? According to string theory, they are rolled up like little balls, too tiny to see. When you pick up a piece of paper, it seems two-dimensional. It has length and breadth, but it doesn't seem to have any depth at all. Nevertheless, if you take a magnifying glass and gaze at the edge of the piece of paper, you begin to see that it has a wee bit of depth. You need a tool to help you see it, but that 3rd dimension is there, too tiny to see under normal conditions. The same is true with those extra 6 dimensions. In everyday life, they are way too tiny to see. They are too small to detect even with the most powerful equipment that we could possibly manufacture in the near future. What do these 6 extra dimensions mean? Nothing, really. They don't measure anything that we are accustomed to, like length, breadth, width, or time. They are simply mathematical constructs that make the mathematical operations in string theory work in the manner that they have to. Like imaginary numbers, we can't see them or feel them or smell them, even though they are necessary for doing calculations. Though it is a strange concept physically, it is the predictive power of the equations that interests scientists rather than their comprehensibility, and an extra 6 dimensions do not constitute an insurmountable problem mathematically. Spotting them might. 10 seems small nowadays. In the past few years, physicists realized that the many competing varieties of string theory are actually, in a sense, the same thing. Scientists realize now that these theories are dual to each other, just as Poncelet realized that lines and points were dual to each other. Scientists now believe that there is a monster theory that underlies all of these competing theories, the so-called M theory, which lives in 11 dimensions, not 10. Strings, or their more general counterparts, branes, a term for multidimensional membranes, are so tiny that no instrument can hope to spot them, at least until our civilization becomes much more advanced. Particle physics look at the subatomic realm with particle accelerators. They use magnetic fields or other means to get tiny particles moving very fast. When these particles collide with one another, they spit off fragments. Particle accelerators are the microscopes of the subatomic world, and the more energy you put into those particles, the more powerful the microscope, the smaller the objects you can see. The superconducting supercollider, a multi-billion-dollar project that was contemplated until the early 1990s, was going to be the most powerful particle accelerator ever built. It was to have more than 10,000 magnets arranged in a loop 54 miles around, about the size of the Beltway highway that circles Washington, D.C. This is still not nearly powerful enough to see strings or curled-up dimensions. Viewing strings would require a particle accelerator about 6 quadrillion miles around. Even traveling at the speed of light, a particle would take 1,000 years to make the circuit. No instrument currently imaginable will give scientists the power to observe strings directly. Nobody can think of an experiment that will give physicists evidence about whether black holes and particles are indeed strings. This is the chief objection to string theory. Because science is based upon observation and experiment, some critics argue that string theory is not science but philosophy. A recent set of theories proposes that some of these rolled-up dimensions might be 10 to the minus 19 centimeters or even larger, which would put them within the realm of experimentation. But at the moment, these theories are considered rogues, interesting ideas, but very long shots at best. Newton's laws of motion and gravitation gave physicists an explanation for the way planets and objects move through the universe. Whenever a new comet was discovered, it gave additional support to Newton's calculations. There were a few problems. Mercury's orbit, for instance, wobbled in a way that disagreed with what Newton predicted. But on the whole, Newton's theories were tested again and again, and they usually passed. Einstein's theories corrected Newton's errors. They explained Mercury's wobble, for instance. These theories also made testable predictions about the way gravity works. Eddington observed the bending of starlight during a solar eclipse, confirming one of those predictions. String theory, on the other hand, ties together a number of existing theories in a very pretty way and makes a number of predictions about the way black holes and particles behave. But none of those predictions are testable or observable. While string theory might be mathematically consistent and even beautiful, it is not yet science. For the foreseeable future, banishing zero from the universe with string theory is a philosophical idea rather than a scientific one. String theory might well be correct, but we may never have the means to find out. Zero has not yet been banished. Indeed, zero seems to be what created the cosmos. The 0th hour. The Big Bang. Hubble's observations suggested that there was a time, called the Big Bang, when the universe was infinitesimally small and infinitely dense. Under such conditions, all the laws of science and therefore all ability to predict the future would break down. Stephen Hawking, A Brief History of Time. The universe was born in zero. Out of the void, out of nothing at all, came a cataclysmic explosion that created all the matter and energy that the entire universe is made of. This event, the Big Bang, was a horrible idea to many scientists and philosophers. It took a long time before astrophysicists came to agree that our universe was finite, that it did in fact have a beginning. The prejudice against a finite universe is ancient. Aristotle rejected the creation of the universe out of the void because he believed that the void could never exist. But this caused a paradox. If the universe could not spring forth from the void, then something had to be floating about before the birth of the universe. There had to be a universe before the universe was born. To Aristotle, the only possible way out of this quandary was to assume that the universe was eternal. It had always existed in the past and would always exist. Western civilization eventually had to make a choice between Aristotle and the Bible, which says that the finite universe sprang forth from the void and prophesies its ultimate destruction. Though the Semitic biblical cosmos toppled the Aristotelian one, the idea of an eternal, unchanging universe was not expunged completely, enduring even to the 20th century. It led Einstein to what he called the greatest mistake of his career. To Einstein, the general theory of relativity had a crucial flaw. It foretold the end of the universe. According to the equations of general relativity, the universe was unstable. There were only two choices, and both were equally unpleasant. One possibility was that the universe would collapse under its own gravity. As the universe gets smaller and smaller, it heats up more and more. It burns brightly with radiation, destroying all life and eventually destroying the atoms that make up matter. It would be death by fire. Eventually, the universe would crunch itself into a zero-dimensional point, like a black hole, and would disappear forever. The other possibility is, if anything, more grim. The universe would expand forever. Galaxies would become ever more distant from one another, and the star stuff that drives all the energetic reactions in the universe would become more rarefied. Stars would burn out as they exhausted their fuel, and galaxies would become darker and darker, and then cold and silent. The cold, dead matter of the stars would decay away, leaving nothing but a smear of radiation that spreads equally throughout the universe. The cosmos would be a cold soup of dimming light. It would be death by ice. To Einstein, these ideas were abhorrent. Like Aristotle, he implicitly assumed that the universe was static, constant, and eternal. The only way out was to correct his equations of general relativity to stave off the impending destruction. He did this by adding a cosmological constant, an as yet undetected force that counteracts the force of gravity. The cosmological constant's push would balance out gravity's pull. Instead of collapsing, the universe could stay in a steady balance, neither collapsing nor expanding. Postulating the existence of such a mysterious force was a desperate act. I have again perpetuated something about gravitation theory which somewhat exposes me to the danger of being confined in a madhouse, wrote Einstein, but he was so worried about the impending destruction of the universe that he was forced to take such a dramatic step. Einstein wasn't bundled off to an asylum. Einstein had proposed stranger things and had been entirely right. However, this time he was not so lucky. The stars themselves destroyed Einstein's vision of a static eternal cosmos. In 1990, the Milky Way was the known universe. Astronomers had little idea that anything lay beyond our own dusty little disk of stars. Though astronomers had spotted some glowing, swirly clouds, there was little reason to believe that they were anything but glowing gas inside our galaxy. In the 1920s, that all changed, thanks to an American astronomer named Edwin Hubble. A special type of star called a Cepheid variable had a property that allowed Hubble to measure the distance to faraway objects. Cepheid stars pulsate, getting brighter and dimmer in a very predictable way. The way they pulsate is closely related to how much light they put out. They are standard candles, objects of known brightness, and became a key tool for Hubble. They were like the headlights of a train. If you watch a train coming at you, you will see that its headlight gets brighter and brighter as it approaches. If you know how much light the headlight puts out, if the headlight is a standard candle, you can tell how bright the headlight will appear at any given distance. The closer it gets, the brighter it seems. The same logic works in reverse. If you know how much light a train's headlight emits, you can measure its apparent brightness and calculate the train's distance from you. Hubble did the exact same thing with Cepheid stars. Most stars he saw were tens or hundreds or thousands of light years away. But when he found a Cepheid blinking in one of these swirly clouds, the Andromeda Nebula, as it was then called, he measured the light and calculated that the nebula was 1,000,000 light years away, far beyond the outer reaches of our galaxy. Andromeda was not a cloud of glowing gas. It was a cloud of stars so distant that they looked like a smear rather than individual points of light. Other swirly galaxies were even more distant. Today, astronomers suspect that the universe is about 15 billion light-years across and peppered everywhere with clusters of galaxies. This was an astounding discovery. The universe was millions of times bigger than previously suspected. As amazing as this observation was, it was not what Hubble is best remembered for. Hubble's second discovery was what shattered Einstein's eternal universe. Hubble measured the distance to galaxy after galaxy with his Cepheid stars, but soon began to notice an alarming pattern. All the galaxies were fleeing with high speed, shooting away from the Milky Way at speeds of hundreds of miles a second or more. The galaxies were so distant that even these great velocities were not directly measurable. The only way to clock the speed of a galaxy is by using the Doppler effect, the same principle used in state troopers' radar guns. You might have noticed that when a train zooms by, the pitch of its horn changes. As the train approaches, its horn is high-pitched, but as it passes you, all of a sudden its pitch drops dramatically. This happens because the motion of the train crushes the sound waves in front of it, making a higher frequency, higher pitched tone, and stretches out the waves behind it, making a lower frequency, lower pitched tone. This is the Doppler effect, and it works with light too. If a star is moving toward Earth, the light is crushed and has a higher frequency than normal. It is shifted toward the blue end of the spectrum, blue shifted. If a star is moving away, the opposite happens. The light is stretched out and red shifted. Police can tell how fast a car is going by testing how light, in the form of radio waves, reflected off the speeding vehicle gets shifted. In the same way, by looking at how a star's light spectrum gets shifted, astronomers can deduce how fast the star is moving, toward us or away. Hubble combined the distance data with Doppler speed data and found something shocking. Not only were galaxies speeding away from us in all directions, the farther away the galaxies were, the faster they were going away. How could this be? Imagine a polka-dotted balloon. The polka dots are like galaxies, while the balloon itself is the fabric of space-time. As the balloon inflates, the dots get farther and farther apart from one another. From any one dot's perspective, the other dots are all rushing away, and the more distant dots are rushing faster than the close dots. Figure 57. The universe seemed to be expanding like a balloon. The balloon analogy has one flaw. Unlike the polka dots, which also get bigger as the balloon expands, the galaxies are staying about the same size, held together by their own gravity. As time runs forward, the universe expands and expands. Looking at it another way, if you had a film of the universe's history and ran the film backward, the universe would shrink and shrink. At some point, the balloon would shrivel and wither, getting smaller and smaller, and then eventually disappear as a point, the singularity at the beginning of time and space. This is the primal zero, the birthplace of the universe, the Big Bang, a furious explosion that created the cosmos. It is from this singularity that all the matter and energy in the universe spewed forth, creating all the galaxies, stars, and planets that have ever and will ever exist. The universe had a beginning about 15 billion years in the past, and space has been expanding ever since. Einstein's hope for a steady eternal universe was all but dead. One glimmer of hope remained, one alternative to the Big Bang, steady-state theory. Some astronomers proposed that there were fountains that spat out matter, and the galaxies moved away from these founts, aging and dying. Though the individual galaxies zoomed away and died, the entire universe as a whole never changed. It was always in equilibrium, constantly replenishing itself. Aristotle's eternal universe still survived. For a time, Big Bang theory and steady-state theory lived side by side, alternatives that astronomers chose between depending on their philosophy. In the mid-1960s, that all changed. Steady-state theory was killed by what scientists had mistaken for pigeon droppings. In 1965, several astrophysicists at Princeton University were calculating what would have happened right after the Big Bang. The entire universe must have been incredibly hot and dense. It would have been glowing with bright light. That light would not have disappeared as the balloon universe expanded. It would instead have gotten stretched out as the rubber fabric of space-time stretched. A few calculations later, the Princeton physicists realized that this light had to be in the microwave region of the spectrum and had to be coming from all directions. This cosmic background radiation was the afterglow of the Big Bang. It would give physicists the first direct evidence that the Big Bang was correct and that steady state was wrong. The Princeton scientists did not have long to wait before their prediction was confirmed. At Bell Labs in nearby Murray Hill, New Jersey, 2 engineers had been testing out sensitive microwave detecting equipment. For all their tinkering, they could not get the equipment to work just right. There was a background hiss of microwave noise, like static on a radio program, that they could not get rid of. At first, they thought that pigeons defecating in their antenna were to blame. But after chasing away the birds and cleaning out the droppings, the hiss remained. They tried everything they could think of to get rid of the noise, but nothing worked. Then, when the engineers heard of the Princeton group's work, they realized that they had found the cosmic background radiation. The noise wasn't pigeon droppings, it was the scream of light from the Big Bang stretched and distorted into a whisper's hiss. For their discovery, the engineers, Arno Penzias and Robert Wilson, got the Nobel Prize. The Princeton physicists, notably Bob Dickey and P.J.E. Jim Peebles, got nothing. Hardly fair in many scientists' opinions. The Nobel Committee tends to reward painstaking and careful experiments more than important theory. The Big Bang had been spotted. The myth of the static universe was dead. As unappealing as the idea of a finite universe was, physicists gradually accepted the Big Bang and agreed that the universe had a beginning. However, there were still problems with the theory. For one thing, the universe is somewhat lumpy. Knots of dense galaxies are separated by vast voids. At the same time, the universe is not too lumpy. It looks roughly the same in all directions, so all the matter did not wind up in one huge glob. If the universe had come from a singularity, with all probability the energy from the Big Bang should have covered the entire balloon fairly evenly, or wound up in one big lump. The balloon should be evenly shaded, or it should have one giant spot rather than being polka-dotted. Something had to account for that just right amount of lumpiness. More troubling still, where did the singularity of the Big Bang come from? Zero holds the secret. The zero of the vacuum might explain the lumpiness of the universe. Since the vacuum everywhere in the universe is seething with a quantum foam of virtual particles, the fabric of the universe is filled with infinite zero-point energy. Under the right conditions, this energy is able to push objects around. In the early universe, it might have pushed objects apart. In the 1980s, physicists suggested that the zero-point energy in the early universe was greater than it is today. That extra energy would try to expand in all directions, pushing the fabric of space-time outward with great speed. It would inflate the balloon with a huge burst of power, smoothing out the lumpiness of the universe in the same way a breath of air smooths out the wrinkles of a balloon. This explains why the universe is relatively smooth. But the vacuum of the first few moments is a false vacuum. Its zero-point energy is unnaturally large. The higher energy state of the zero-point energy makes it inherently unstable, and very quickly, in less than a millionth of a millionth of a millionth of a millionth of a second, the false vacuum would collapse, reverting to the true vacuum with its everyday zero-point energy that we observe in our universe. It was like a pot of water that was instantly flash-heated to a huge temperature. Little bubbles of true vacuum would have formed and expanded at the speed of light. Our observable universe sits inside one of these bubbles, or several of them that got linked together. The asymmetry of the universe could be explained by the asymmetrical nature of these expanding bubbles that formed and merged. According to this theory of inflation, it is the non-zero zero-point energy that created the stars and galaxies. Zero might also hold the secret of what created the cosmos. Just as the nothingness of the vacuum and the zero-point energy spawn particles, they might spawn universes. The froth of quantum foam, the spontaneous birth and death of particles, might explain the origin of the cosmos. Perhaps the universe is just a quantum fluctuation on a grand scale, an enormous singular particle that came into existence out of the ultimate vacuum. This cosmic egg would explode, inflate, and create the space-time of our universe. It may be that our universe is simply one of many fluctuations. Some physicists believe that the singularities at the center of black holes are windows into the primordial quantum foam before the Big Bang, and the froth of foam at the center of the black hole, where time and space have no meaning, is constantly creating countless numbers of new universes that bubble off, inflate, and create their own stars and galaxies. Zero might hold the secret to our existence and the existence of an infinite number of other universes. Zero is so powerful because it unhinges the laws of physics. It is at the 0 hour of the Big Bang and the ground zero of the black hole that the mathematical equations that describe our world stop making sense. However, zero cannot be ignored. Not only does zero hold the secret to our existence, it will also be responsible for the end of the universe. Chapter Infinity. Zero's Final Victory. End Time. This is the way the world ends, not with a bang, but a whimper. T.S. Eliot, The Hollow Men. While some physicists are trying to eliminate zero from their equations, others are showing that zero may have the last laugh. Even though scientists might never unlock the secrets of the universe's birth, they are on the brink of understanding its death. The ultimate fate of the cosmos lies with zero. Einstein's gravitational equations didn't allow for a static, unchanging universe. They did, however, allow for several other fates, which depend on the amount of mass in the cosmos. In the case of a light universe, the balloon of space-time could expand forever, getting bigger and bigger. The stars and galaxies would wink out one by one. The universe grows cold and dies a heat death. However, if there is enough mass, galaxies, galaxy clusters, and unseen dark matter, the initial push given by the Big Bang wouldn't be enough to allow the balloon to inflate forever. The galaxies would tug on one another, eventually pulling the fabric of space-time together. The balloon would begin to deflate. The deflation would get faster and faster, the universe would get hotter and hotter, and it would eventually end in a backward Big Bang, the Big Crunch. Which will be our fate, Big Crunch or heat death? The answer is at hand. When astronomers peer at a distant galaxy, they are looking backward in time. A nearby galaxy might be 1,000,000 light-years away. A light beam leaving that galaxy now will take 1,000,000 years to make its trip to Earth. The light reaching our eyes now left that galaxy 1,000,000 years ago. The more distant the objects that astronomers look at, the farther back they are looking in time. The universe's fate hinges on how well our space-time balloon is expanding. If the expansion is slowing down rapidly, then it's a good sign that the energy from the Big Bang is nearly spent. Our universe would be heading for a big crunch. On the other hand, if the universe's expansion isn't slowing down very much, the energy of the Big Bang might have given the fabric of space-time enough of a kick to let it expand for eternity. Astronomers have begun to measure the change in the universe's expansion. A certain type of supernova, exploding star, called a type Ia, is a standard candle like Hubble's Cepheid stars. The Ia supernovas explode in roughly the same way and with the same brightness. But, unlike Hubble's dim Cepheids, supernovas are visible halfway across the universe. In late 1997, astronomers announced that they had used these supernovas to measure the distance to some very dim and ancient galaxies. The distance of the galaxy yields its age, and its Doppler shift yields its velocity. By comparing how fast galaxies were receding at different eras in the past, the astronomers were able to track how fast space-time was expanding. The answer they got was an odd one. The expansion of the universe isn't slowing down. It might even be speeding up. The supernova data implied that the universe is getting bigger and bigger, faster and faster. If this is the case, there is little chance of a big crunch because something is opposing the force of gravity. Once again, physicists are talking about the cosmological constant, the mysterious term that Einstein added to his equations to balance the push of gravity. Einstein's biggest blunder might not have been a blunder after all. The mysterious force once again might be the force of the vacuum. The tiny particles that seethe through space-time exert a gentle outward push, stretching the fabric of space-time imperceptibly. Over billions of years, that stretch adds up, and the universe inflates faster and faster. The fate of our universe will not be a big crunch, but an eternal expansion, cooling and heat death, thanks to the zero-point energy, a zero in the equations of quantum mechanics that imbues the vacuum with an infinity of particles. Astronomers are still cautious. These supernova results are preliminary, but they are getting more solid with each observation. Other studies which analyze plumes of gas or the number of gravitational lenses in a given field of view also support the supernova results, implying that the cosmos will expand forever. The universe will die a cold death, not a hot one. The answer is ice, not fire, thanks to the power of zero. To infinity and beyond. However, if we do discover a complete theory, it should in time be understandable in broad principle by everyone, not just a few scientists. Then we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of the question of why it is that we and the universe exist. If we find the answer to that, it would be the ultimate triumph of human reason, for we would know the mind of God. Stephen Hawking. Zero is behind all of the big puzzles in physics. The infinite density of the black hole is a division by zero. The Big Bang creation from the void is a division by zero. The infinite energy of the vacuum is a division by zero. Yet dividing by zero destroys the fabric of mathematics and the framework of logic and threatens to undermine the very basis of science. In Pythagoras' day, before the age of zero, pure logic reigned supreme. The universe was predictable and orderly. It was built upon rational numbers and implied the existence of God. Zeno's troubling paradox was explained away by banishing infinity and zero from the realm of numbers. With the scientific revolution, the purely logical world gave way to an empirical one, based upon observation rather than philosophy. For Newton to explain the laws of the universe, he had to ignore the illogic within his calculus, an illogic caused by a division by zero. Just as mathematicians and physicists managed to overcome the division by zero problem in the calculus and set it once more upon a logical framework, zero returned in the equations of quantum mechanics and general relativity and, once again, tainted science with the infinite. At the zeros of the universe, logic fails. Quantum theory and relativity fall apart. To solve the problem, scientists set out to banish zero yet once more and unify the rules that govern the cosmos. If scientists succeed, they will understand the laws of the universe. We would know the physical laws that dictate everything to the edges of space and time, from the beginning of the cosmos to its end. Humans would understand the cosmic whim that created the Big Bang. We would know the mind of God. But this time, zero might not be so easy to defeat. The theories that unify quantum mechanics and general relativity, that describe the centers of black holes and explain the singularity of the Big Bang, are so far removed from experiment that it might be impossible to determine which are correct and which are not. The arguments of string theorists and cosmologists might be mathematically precise and at the same time be as useless as the philosophy of Pythagoras. Their mathematical theories might be beautiful and consistent and might seem to explain the nature of the universe, and be utterly wrong. All that scientists know is the cosmos was spawned from nothing and will return to the nothing from whence it came. The universe begins and ends with zero. This concludes Zero by Charles Seife, narrated by Bob Sauer. Copyright 2000 by Charles Seife. This unabridged audiobook is published by arrangement with Charles Seife and was produced in the year 2020 by Cantor Media Incorporated, a division of Recorded Books which holds the copyright thereto. Please visit tantor.com for more information on our growing library of unabridged audiobooks.